Do you know how a file system is stored on your device? The files and the folders form hierarchical data and are stored in the form of trees. Hi, my name is Prateek, and in this tutorial I'll be teaching you the fundamentals of binary trees and the various operations that you can perform on trees. But before we move on, make sure you check out free masterclasses on Scaler's event page and learn from industry leading experts. Also, subscribe the channel if you haven't already. Let's dive right in. Let us start the topic by understanding what is tree data structure. So in computer science, a tree represents a hierarchical structure with a set of connected nodes, right? So for example, if you look at this diagram, this actually represents a tree, and this node, it is the starting of the tree. It is called as the root node, right? We will discuss where it can be useful. So in this structure, each node in the tree can be connected to many children. So this is a non-linear data structure. The first non-linear data structure that we are covering is a tree. So far we have talked about array, we have talked about linked list. All of those data structures were linear data structures because they were following a sequence. Here there is no sequence, here there is a hierarchy, right? So each node can be connected to many children. So 2 is connected with 7 and 5. It is connected with 2 children. So 7 and 5, they are children of 2, but must be connected to exactly one parent. So each node must have one parent. I cannot say 7 will have 2 parents. No, 7 will have only one parent, that is 2. 5 has only one parent, that is 2. 2 has only one parent, that is 7. 10 has only one parent, that is also 7, right? So except for the root node, which has no parent. So root node has no parent. Rest all the nodes, they have one parent, right? Now because of this property, there will be an interesting observation. Suppose you are creating a tree in which you are going to have n nodes. Okay, for example, I have 3 nodes here. So how many edges you will have? So except for the root node, for every node that you will have, that you will add, there will be an edge. So there will be, of course, n minus 1 edges in the tree, right? So in any tree that you are going to create, irrespective of is it a binary tree or not, each node that you add will add a edge in the tree except the root node. Okay, so root node does not add any edge in the tree except the root node. If there are n nodes in the tree, there would be n minus 1 edges. Okay, because root node has no parent, rest all the nodes that you add, they must be connected to a parent through an edge, right? So this is an interesting observation you can note. So in every tree there will be n nodes and there would be n minus 1 edges in the tree, right? So that is tree data structure. Now let us talk about where this data structure can be used, how it can be helpful in computer science. Okay, basically trees are used to represent or manipulate hierarchical data in applications such as file systems or directory structure, right? So all of you have worked with a file system. So what happens in a file system? You say, okay, I have my PC. In this, I have certain drives: C drive, D drive, E drive, right? And then inside this, I have folders: F1, F2, F3, F4. Right? And here also I have folders. Then I have subfolders, right? Maybe I have photos here. Maybe I have some documents here, right? Now we often do operations like that. Okay, I want to move these photos from here to here, right? So what is going to happen? You're not going to copy this data. You're going to say, okay, I'll cut and paste. So if you simply want to move this photos from here to here, what you need to do? You do not need to copy this information to some other part of the disk. You only need to change the reference, right? That okay, earlier this reference was stored by F4. Now this reference is stored by F2. Basically the links, right? The links to the folders and subfolders, they can be easily changed if the data structure is implemented using a tree, right? This is something we will discuss, right? The file system is a good example of a tree data structure, right? Multiple inheritance trees in programming. So this is used when you're using object oriented programming concepts and you have a class C which is going to inherit from a class A. It is also going to inherit some methods from class B, right? So this is not exactly a tree, I would say, because this node, this is inheriting from two different classes. So irrespective of that fact, basically the trees are internally used by the compilers to see what methods would be part of the class that you have implemented using inheritance. Okay, then again, in natural language processing, basically whenever you have a sentence, for example, I am going for a party, right? Now this sentence can be broken down into certain components. Maybe you have a verb, maybe you have a subject, maybe you have a predicate, or you have even for language parsers. Okay, so what are your parsers? Whenever you write code, it goes through a language parser so that compiler can figure out if there is any error in the code, is it is having the correct syntax or not. So they again form a parse tree of that code, right? So again, it's an interesting concept that you will learn in compilers, right? So again, they are used a lot in understanding of the language. Okay, then in HTML there is a DOM tree. So whenever you open up a website, right, you see there is a HTML code, right? Inside HTML code there are a lot of tags. There is head, there is body, right? Inside body there is a paragraph, there is a div, there is an image, right? So if you look carefully, this whole document forms a DOM tree. So inside DOM tree you have head, you have body, right? Then you have certain elements, you have div, you have paragraph, here you might have image, you might have some text, right? Now what is happening? You want to say, okay, I want to click this particular button, and on clicking this button, this div will change its color, right? So how do you fetch elements from this huge web page? So there are methods like document.getElementById, by id, document.getElementBy by tag name. So what it is doing, it is traversing this DOM tree. It is a tree of objects. Okay, it is a tree of objects in your web browser. Again, it's behind the scenes. So it is doing some kind of search operation on this tree, and it is trying to manipulate this tree, right? For example, you scroll your web page and a new item is added from the bottom. So maybe it is adding something in the list, right? So your tree is getting modified, right? Then of course there are trees which are used in search operations like binary search tree. There are trees which are used to implement data structure like map, self-balancing trees. Okay, so they are used to perform faster searches and keeping data ordered. We will talk about BSTs in the coming class. In machine learning, there is a concept called as hierarchical clustering. So it is a part of a clustering technique, okay, where I want to group together similar items. So it comes under a part of unsupervised learning. So there also the tree data structure is used, right? So we see lot of applications are there, and that becomes very important for us to understand the tree data structure. So in this video, we'll be talking more about binary trees in general, because that they are the most common ones that are widely used. Okay, so let us start with binary trees. So let us start by understanding what is a binary tree. So as I discussed, it is the most commonly used tree structure in which you can have at max 2 children. Okay, so it constrains the number of children for each parent to at most 2. That means a node can have 0 children. For example, in this case, the nodes D, E, F, G, they don't have any children. They are also called as leaf nodes. The nodes which don't have any children, they are called as leaf nodes. Node can also have one child, right? Or it can have 2 children, right? It cannot have more than 2 children. For example, if I draw a few structures, you have to tell me whether it is a binary tree or not. Is it a binary tree? The answer is yes. Each node has 0 child, 1 child, or 2 children, right? Okay, is this a binary tree? The answer is yes. So this node, the node C, it has 1 child. A and B, they have 2 children, and D, E, F, they don't have any children. Hence, in this case, we have 3 leaf nodes. So this is again an example of a binary tree, right? Now what we are going to learn in this tutorial, we are going to learn about different operations. How do we create a binary tree? How does the node structure look like? How do we perform search or update operation on a binary tree? How do we display a binary tree? And there are 4 popular ways to do it. pre-order traversal, in-order traversal, post-order traversal, level order traversal. Okay, so we are going to look at all these things one by one, and we'll be starting with creation of tree first. Let's begin with that. Let us talk about creating the tree. So first of all, we need to understand the structure of the node that is going to create the tree, right? So in this tree, if you look carefully, there are so many nodes, and this box represents one particular node. Okay, that is the root node, right? So I have the root node. Now what is this root node going to contain, or any node going to contain? It is going to store three things. One is your data, one is the address of the left node, one is the address of the right node. Okay, in Java we also call it as reference, right? Now suppose this object B, it is created at some memory address, let's say 250, right? This is the location of B in the heap where it is created. So A's left is going to store 250. Let's say this is created at some location 380. So A's right is going to store 380, right? A itself is created at some location, let's say 400. The root is going to store 400. Okay, so root is not a node, root is just a reference to the root node. Okay, so root variable is holding the address of the root node, right? Now B is left is referring to D, so D is created at some location, let's say 560. So here we will have 560. Now D is left and right, they are null, they don't refer to anyone because D is a leaf node, right? So D is a leaf node, E is a leaf node, F is also a leaf node, so they are left and right, they are null. Now B is a node with a single child, right? Because it does not have any right child, hence this value is also null. And here I will store the address of E, here I will store the address of F, right? So I hope you are understanding the structure of the node. So I need to implement a class called node, in which I will have three things. One is my integer data. Data can take any type. Just to keep it simple, I'm taking it as an integer. One will be my node left, a reference of the next left node, and node right, a reference to the right node. If the left and right node does not exist, then I will set this value to null, right? Now let us see in the code how can I implement this node class. So let us go to IntelliJ. Now I am going to implement the tree data structure. I have a class called binary tree. I have a class called binary tree test. Both are empty classes as of now. In order to build binary tree class, I need to define that what is node, right? So node will have three things. One is my data, one is my left, and one is my right. Apart from it, I also need to give a constructor here, that whenever a new node is constructed, what data it should take. Else, okay, data I will know, but at the time of construction of new node, I do not know what node will go into the left, what node will go into the right. So I will simply say that my data, this is equal to D, and left and right, they will be set to null by default. So whenever you're creating a new node, you do not know the left and right nodes. So these will be set later, right? Now comes the binary tree class. Now suppose we want to create a tree like this, okay, or let me take up another example in which I have numeric data. So I can say, okay, let me create a tree like this, 1 connected with 2, and then it is connected with 3, right? Let's say very simple tree, 3 nodes. Now how you will read this tree? The first thing is, how do I read this tree, right? So the first input I will get is the root node. Okay, user will enter 1. I will say fine, input is 1, let me read this, create a node called a root node, and root node is going to point to this node, right? And in the left of this, I will again read from the user, right? The user says okay fine, the next node is 2. So I'll say fine, I'll create a node called 2. I will attach it in the left of 1 like this. Okay, and now what is the next node I will read, right? Now it can happen that I have something in the left of 2, or I have something in the right of 2, or I have something in the right of 1, right? So I do not know. The way we are going to do it is, we are going to read now what is there in the left of 2. Okay, so if the left of 2 is null, right, I will input -1. So -1 in the input will denote that near is nothing here. So I will simply set this value to be null, right? What is right of 2? I'm again going to say it is -1. So I will set this value to null, right? Now this option is gone. I've read it. This option is gone. Now I can only read this. So I'll come back here. I'll say fine. This 2 is done. Now try to read what is there in the right of 1, right? So I'll say, okay, the next input is 3. I will create a new node and I will attach it, of course, here. But before that, I will read what is in the left of 3, right? So attach part will happen a little later, right? I'll read what is in the left of 3. So this value would be minus 1, minus 1. What is there in the right of 3? Again, I say minus 1. Now this node is constructed, or in a way I can say this subtree has been constructed. So once it is constructed, I will return it back to the parent. So the parent is 1. It will get connected here, right? So this will become more clear once I write the code. The idea is, I will of course do it for a bigger tree as well. This is little tricky, right? So what the idea is, we are going to build a tree recursively. We are going to build recursively, right? Now how we are going to build a tree recursively? Many tree operations, they are recursive in nature, right? So I'll say, okay, fine, I will build the root node. That is 1. Then I will build the complete left subtree. In the above example, the left subtree has only 1 node, so it looks easy, right? I will build the complete right subtree, right? Okay, I will build the complete left subtree and I will attach it here. That is part 1. I will build the complete right subtree and then I will attach it in the right of 1, right? So we will do it for a bigger tree as well. So let us jump into the code first and try to see how this can be written. Of course, I will do a dry run and explain you how you can build a more complicated tree like this with the same code. Okay, so let us go into the binary tree class. One thing is for sure, that every tree must know what is the root node. What is the root node? So this is something that will be the property of the tree. Every tree must know what is the root node. Just like in a linked list, every linked list knows what is the head of the linked list, what is the tail of the linked list. So in case of tree, you must know that what is the root node, right? So one thing is there, I am going to read this tree. So user will input will come through the user, right? So let us see the tree construction part. So in this binary tree class, what I'm going to do, I'm going to first define the data members of the tree. So I have only one data member, that is the root of the tree, right? Now this root should be initialized. Where it should be initialized? Of course, when the tree is created. So when the tree is created, it is created when the constructor is called. I need to define a constructor called binary tree, right? Now in this constructor, what I need to do, I need to take input from the user. So in order to take input, I will need a scanner object. I will say scanner sc, this is equal to new scanner system.in. So scanner object is used in Java to read inputs. So I have imported the scanner, right? Now the building of the tree is recursive in nature. So I will create a helper function to do it. So I can say fine node, let's say create tree, and to this create tree method, I'm going to supply the scanner object so that this method will actually read from the user. Okay, so I will say fine, the root should be initialized by calling the create tree method. So create tree is a helper method getting called in the constructor that will read the tree from the command line, right? Now I'm going to pass the scanner object here so that I can use it to read data from the user, right? I don't want to create this object again and again inside this method. Okay, so I'm creating it once and that object is being circulated across all the recursive function calls that are going to happen, right? Now suppose I read something, right? I can say okay, data that I'm going to read is scanner dot next int. So I'm going to read something. All right, now I have read something from the user. Let's say this data is 1, right? What I want to do, okay, this data can also be -1, right? I'm asking, okay, tell me what is the next data. So I will actually have a two types of case. One will be my base case. If my data is -1, then what should I return? Right? I will return a null. That means, okay, I don't want to attach any node here. That subtree is just null. So I will return null. But if it is not -1, if it is something else, basically I'm talking about the recursive case. For example, if my input is 1, what I will do, I will create a new node. I'll say fine, I'll call it a node root. This is equal to new node, and I give it the value data, right? So if root is confusing to you, just call it as n, right? I create a node called n, which is initialized with this data. So suppose my input is 1, right? So I say, okay, n is a new node. Now what should I do? I need to read the left subtree. Basically, I need to create a left subtree here and attach it here, right? So what I can say that in the left of n dot left should refer to a new tree, which is equal to create tree. Again, scanner will get passed. What should n dot right point to? N dot right should also refer to a new tree called create, that is returned by the create tree method. And again, the scanner is going to get passed. And then I can return n. What I'm saying that n dot right should also point to a new tree. So left subtree, right subtree, right? This is the recursive way of constructing the tree. Now you might ask, okay, how does this method will actually work? I will show you it will actually work. Let's see how it's going to work, right? So let us take an example of a more complicated tree, or let's first start with a simple tree, right? Let's say I have a tree like this, 1, 2, 3, right? Now for this tree, what is my input going to look like? So input will be 1, then it will be 2, then it will be left and right of 2, which is -1, -1, then it will be 3, and left and right of 3, which will be -1, -1. So given this input, I actually want to create this kind of a structure. Let's see how it's going to happen, right? So I said fine, root is equal to create tree. I call this method create tree. It reads something from the user. So one integer it's going to read. So it's going to read 1. So data is not -1. Fine, I come here. Node n, this is equal to new node. So basically I have a stack call in which n is going to say n is a new node where the data is 1. Fine. Now n dot left, it makes a new call. N dot left, right? So I said fine. In the left of 1, I want to create tree. So again, create tree is called. If you come again in this function, you read something from the user. So you read 2. Fine. You said fine, I create a new node n. Okay, a new node n is created. So earlier n was here, now the new n is here, right? It's a local variable. It is created in every stack call, right? It is here. This is equal to new node where the data is 2. Fine. Now n dot left, this is equal to create tree, right? So again I make a function call, create tree, go and do something, right? So I've made a call for here, right? Now if I go and read what is the next number, it is -1. So I return null. Basically what happens? So 2's left made a call and it got a value that is null. So 2's left starts pointing to null. Now what is the next call that is going to happen? We are in this stack and I make a call that 2's right, this is equal to create tree. So I make another call here and this value is also null, right? Once these two calls are over, this one and this one, I return n. So I return this n back where I return it to the place from where it was called. So who called it? 1 called it. So 1 gets to know that my left should refer to this node. So by returning this n, this answer goes back to the previous function and once left is now connected with. Now what is the next call we are going to make? So once left is now created. So this call is over. Once left is now created, right? Now one says, okay, fine, my left is created. I'm pointing to 2. I will make a call to update my right. So n dot right, this is equal to create tree, right? So this was already read. Again, a new function call is made. You read the next number, that is 3. You create a new node from line number 29. You said the new node is 3. N dot left, this is equal to create tree. So 3 is left, makes a call to create tree, which again reads a data that is -1. So you return a null. So 3 is left says, okay, make a call. That call says I will return null. Now 3 is right says make a call to create tree. It goes and reads a number that is -1. Again, it returns a null, right? And then you return n. So now n is this, right? So it returns 3 back. When you return 3 back, what happens? Who called 3? So one's right made a call to create this tree. So one's right is now going to store the address of 3. So it gets connected here. From here, if you return n, where does it go? It goes back to the constructor because this made a call to create t. Finally, root is referring to the address of 1, right? Okay, I'll hide myself so that you can see. The root is referring to this one, right? So this is how it is happening, right? So this is a small example demonstrating how this small tree is constructed using this code, right? Now I will run this code on a bigger example as well. Now some of you might not be convinced that whether this code will work for a bigger tree or not. So let us rerun this code on a bigger example. Okay, so this is the method create tree that again I am explaining with a big example. So let's say I have a tree which should be built like this. Let's say I have 1, I have 2, I have 3, I have 4, I have 5, and maybe I have 6. Now what input should I give? So first of all, I will give the root node. Okay, so input will be 1. Then I will go left. Input will be 2. Then again I will go left. The input will be 4. Then I will go left of 4, which is -1. I will go right of 4, which is also -1. Okay, then I will come back because 4 is done. I will come back. I will go in the right of 2. So right of 2 is again -1. Then I will go back. 2's left is done, 2's right is done, right? So I'll go in the right of 1. So right of 1 is 3. Then I will go in the left of 3, which is 5. I will go in the left of 5, which is -1. Right of 5, which is also -1. Then I will go back. I will go in the right of 3, which is 6. Then left of 6, right of 6. -1, -1, right? So the goal is, given this input, I want to create this tree structure in the output. From this input, I want to create this tree structure, right? Now let us see how we are going to do it. So again, I'm going to read some data. So I will read the first number, that is 1. I will say fine, data is equal to scanner.nextInt. It's not -1. So I create a new node n, right? So fine, let's create a new node n that is having data 1. Let me draw the stack as well side by side. So n is referring here, right? Now so if you want to learn what is the function that is currently executing, so that is at the top of the stack. So n is created. Now you make a call, n.left equal to create tree. So you're making a call to create something in the left of 1, right? So 1 makes a call for the left part. So again, you go call this function, you read data. So data is the next number, that is 2. Fine. You again create a new node. Now this function is paused. This function is paused here. You said fine, I'm going to create a new node and that node is 2. That node is 2. Right node is not connected. It's not connected with 1. Right? And again, you say I want to connect something in the left of 2. What will be that something? Again, you make a function called to create tree. So again, this is paused and it is expecting to build its left tree. So you again call the function create tree, you read the data. So now you're going to read 4. So you read 4. You read 4. Now 4 says, okay, I'm a new node and I will create something in my left. A 4's left makes a call to create tree. The 4's left again makes a call to create tree. And in this case, you read data. The data comes out to be -1. And if the data is -1, you return null. The 4's left gets to know that my value is null. Right? So a null is returned from this function, which is attached with left of 4. And then you hit this line for the first time in this function call, right? N.write, this is equal to create tree. Now you say, okay, I will again call create tree. I will read this number. This number is again -1. it returns a null in the right also. 4's left and right, they are null. That means the subtree of 4 has been created. This subtree is finished. I will return n. So this is null and I will return n. So n is this. Now where this return value will go? It will go back to the place from where it was called. So who called it? 2's left called it. So 2's left is now connected with 4 and this function call is over, right? So 2's left is connected with 4, right? Now this is the point where this connection has been established, right? So 2 made a call to 4. 4 said, okay, I will build myself. I will build my left and right, which are null. And now I will return myself, right? So 2's left is over. Now what will happen? 2 will make a call on the right subtree. So 2 makes a call here, n dot right, this is equal to create tree. Now what do I read next? Again, it is -1. So I return a null. I return a null from here. So 2's right is null. So 2's right is null. It's not referring to anything, right? So this value is null. Now 2's left is done, 2's right is done. I say return n. So return n means what is the function that is at the top? At the top, I have this function. So I'm going to return this subtree, this whole subtree back to 1. So basically, 1 will get to know that my left points to this n, and hence the left subtree of 1 has been built. Now I will build the right subtree, right? Okay. So 1 will say, okay, fine, my left subtree has been built. This is over from the call stack. So once 1 is now connected with 2 and 4, right? This tree. 1 will say, okay, now it is my turn to call the right. So once left is done, it will execute this line. N dot right, this is equal to create tree. Now you again make a call. Next number you read is 3. So you create a new node called n. This is the new node. So 3 is created. And then you again make a call to the left. So you read a number, 5 is created. This is new node. Then you again make a call to the left, -1. So 5's left is null. Again you make a call on the right. So 5's left is null. Again you read -1. So 5's right is also null. Then you return n. So you return 5. So 5 gets attached in the left of 3. So 5 is returned. It gets attached in the left of 3. So 5 goes here. Right? Then again, what's going to happen? You will say, okay, I want to build something on the right of 3. So 3's left is done. 3's right's done. So I'll again make a call. It will read 6. A new node will be created 6. Okay. And again, you say, okay, I will read the left, which is -1. I'll read the right, which is also -1. And then I will return n. When you return n, this 6 is returned back to the right of 3. So this 6 is being attached here. Right? And then you say, okay, I'm going to return n. So when you return n, you return this 3 back to 1. So once right is going to point to this subtree 3, 5, and this subtree is attached with 1. So finally, when you are here, this call is over, right? So you will return n. So n will be this node, and it is returned back here, root equal to create tree. This becomes the root of the tree. So root is a data member of the class, and hence root of the tree gets updated. I hope you are now convinced that how this structure can be made so easily with this recursive function. Okay, with this recursive function. Okay, now this way of building the tree, it is called as pre-order, right? Pre-order means first we are building the root node, then we are building the left subtree, and then we are building the right subtree. Then we are building the right subtree, right? So right now we have built the tree using a pre-order recursive build tree function, right? Or create tree function, right? Next we will look at how we can print this tree in a similar way. Now let us talk about tree traversals. Okay, so tree traversal is a way to iterate over all the nodes of the tree, right? Now this traversal can be helpful if you want to perform operations like counting the number of nodes, searching for a given node, updating a given node, right? So in order to do all these operations, we must know how to traverse a given tree, right? So a tree has been built, a tree has been created. We want a way to go to each and every node of the tree, right? So as I discussed, if you want to do a tree traversal, there are two broad techniques, right? So tree traversal, right? So one is your recursive technique, that okay, you start with the root node, then you iterate recursively on the left tree and the right tree, right? There is a recursive way of doing it. There is a iterative way of doing it, right? So we will discuss all these ways now, right? So in recursive way, again, there are it depends upon the ordering. Okay, the way is same. We basically recursively iterate on the left and right subtrees, but based upon ordering, there are three different ways. One is called as pre-order traversal, one is called as in-order traversal, and one is called as post-order traversal. We will be looking at all of them. In iterative, there is only one way, that is called as level order traversal, right? So all of these traversals, they are going to travel all the nodes, but the order in which you will see the output, it will be different. So let us start with the pre-order traversal, given this as the tree, right? 1 2 3 4 5 6. So I will just redraw this tree. 1 2 3 4 5. Now what does this pre-order traversal says? That fine, what I will do, I will travel the root node, then I will recursively traverse the left subtree. Okay, this will be a recursive call, and I will recursively travel the right subtree, again a recursive call. Okay, it is very similar to the build function, what we are doing in the build function also. If you look carefully, we are first building the root node, and then we are recursively building the left tree, and then we are recursively building the right tree, right? So if you see in this case, the output will be very similar to the order in which you have built the tree. So if you start traversing, you will say fine, I will start with the root node, I will print 1, I will go to the left subtree. So this whole is my left subtree. So I will print the root node, that is 2, and then I will go to the left subtree. So left of 2 is 4. So I will print 4 and I will go to the left. Now left is null. So I come back. I will go to the right. Right is null. I come back. Now 4 is done. This whole tree has been printed. So I come back to 2. So I will go to the right of 2. Again it is null. I'll come back. So this whole tree has been printed. I go back. Now left of 1 has been printed. So I go to the right of 1. So I come to 3. I will print 3. I will go left. Now I'll print 5. I will go left. I'll print right of 5. Again null. So 5 is done. So this whole tree has been printed. I'll go back. So at 3 I'll say okay, let's go right. I'll print 6. I'll go left. I'll go right. Nothing happens. This whole tree has been printed. I come back. Now 3 has been printed. So root has been done. Left of 3 has been done. Right of 3 has been done. So I'll return. So this whole tree has been printed. I come back. And at 1 I see 1 has been printed already, because before printing left and right I print 1. This output is called as pre-order output, in which before printing left and right nodes I print the root node, right? So 1 2 4 3 5 6. This will be the pre-order output for this tree, right? Now let us see this thing in our code as well. Let's write a pre-order print method. Let's write a method called void display, and this is going to be the method that will display the tree, right? So inside this logic can be changed. I can display a tree in a pre-order way or in a level order way or any other way, right? So I'll again create one more helper method. So I will say void pre-order. So void pre-order print. Now this is a recursive function, so I have to tell at what node I'm currently at. So I will start with the some node, that is root node. Okay. So what I will do, I'll say fine, I will have a base case. What will be my base case? What is the smallest tree I can get? That the tree is null, the root is null. In that case, I don't need to print anything. I will simply return. Otherwise, what I will do, I'll print the root data and I will go on the left and the right tree. So I'll say fine sout root dot data, go and print the left subtree recursively. So pre-order print root dot left, then pre-order print root dot right. That's it. And in the display method, I can call pre-order print with the root of the. Now let's do one thing. Let us test our binary tree, because we have the create method, we have the print method. Now I can create a binary tree and try to print it. So I can say fine, I want to create a binary tree object. This is equal to new binary tree. I have defined the class. Now as soon as this constructor is called, your tree will start getting built, because we call the create tree method here, right? Now I can call t.display, right? Now think of any tree that you want to make. We will give it as an input here. Sorry, I should run this file. Now this is waiting for the input, right? So let me draw a tree. Let's say tree is 1, 2, 3, 4, 5, 6, right? Now how this tree will be given as input? So you will input 1, then 2, then 4, then left of 4 minus 1, right of 4 minus 1, right of 2 minus 1, then 3, then you will input 5, left of 5, right of 5, right of 6, right of 3, that is 6, left of 6, and right of 6. Okay, the same input that I have shown you in the example also, this input is given. And now I'm saying that let me print this tree. What I'm getting, I'm printing 1, I go here, then I go to 2, fine, then I go to 4, fine, then I go to 3, I come back, I go here, yes, then I go here 5, then I go here 6. Absolutely correct, right? So if you look at, this was a pre-order build, right? And this is actually a pre-order print. So if you see, the output will be exactly same. 1, 1, 2, 2, 4, 4. Minus 1 I'm not printing. Skip, skip, skip. Then 3, 5, 3, 5. Absolutely correct. Minus 1 I'm not printing. 6, 6, right? That means my both functions are working fine. Tree is getting built correctly and tree is also getting printed correctly as well, right? Now I will show you two more variations of this print method, that is called in order print and post order print. So now let us discuss the next type of recursive printing that we call as in order print. Okay, so I hope pre-order is clear. Now we are moving to in order. So nothing is going to change, the order of printing is going to change. Okay, so earlier it was root, left subtree and right subtree. Now what we are going to do, in order means root will be printed in between. So before you print the root, you will print the left subtree. Okay, and after you print the root, you will print the right subtree. That is what the in order printing would mean. Now let us dry run this logic on our code and see what do we get in order. So what I want to do, so I will start from the root node. I want to print this root node, but before that I will have to print the left subtree, right? Now at the left subtree, again, if I am at 2, I have to print the left subtree. So that means I will have to print 4. So 4 will be the first output that I will get. Now I will print the root. So what is the root? The root is 2. All right. Then I will print the right subtree. So right subtree of 2 is null, right? Then I can go back to 1. So for 1, I have seen the left subtree is already printed. Then I can print the root. So I will print 1. And then I will print the right subtree. Now I am at 3, right? Before I print 3, I will have to print the left subtree. So only one node, I will print 5. Then I can print the root node, that is 3. Then I can print the right subtree, that is 6, right? This will be the output we can expect by traversing this tree in a in order fashion. So let us jump into the code and see what we will change, right? Just like the pre-order print method, what I will do, I will create one more method called as in order print. So in this case, the root will be printed in the middle, and this call will be now in order print root dot left, and this will be now in order print root dot right. Okay, now in the display method, instead of calling pre-order print, maybe let's just call in order print this time. I want to display the tree using in order print. I will pass the root of the tree as a parameter here, right? So let us give the input for this tree and see what output we get. We are getting 421536. Is it the expected output? 421536. The answer is yes, right? Now you might be interested in doing a call stack analysis of this, right? So let us see how we can do the call stack analysis as well, right? So in the beginning, what is happening? Let me also copy paste the code. This is the code, right? Let us do the call stack analysis. This is the method that we are calling, right? So the call stack is empty, so we called in order print where the root node is 1. So I say root is 1, but I'm not going to print it. So root is not null. I will just call on the left. So I make a call here, right? So that means root is now 2. I'm at this node, but I'm not going to print it. Again, I make a call on the left. That means root is 4. Okay. I'm not going to print it because root is not null. Again, I make a call on the left. When you make a call on the left of 4, you actually come here. This is null. So if this is null, you return. Okay. So you return. Then you make a call. Then you print the root data. So that means you print 4. This is the top of the stack, and this is the root that we are talking about. So you will print 4. Then what's going to happen? You will say, okay, I'll go right. So right is null. Again, you make a call to null and you return. So you come back. So again, you are here. Now for 4, you have done all the 3 things. Left is done, root is done, right is done. So you return. So from here, you go back, and this is gone from the stack, right? Now what is the new top, right? How do we come back to 2? This is how we come back to the 2. So the new top is this. Now this is the root node that is currently we are talking about. Have I printed the left? Yes. Have I printed root dot data? No. I will print it now. Have I printed the right? No. So I make a call on the right of 2, that is null, and I again return. Then this is done. So I come back. Now what is the top node? The top node is 1. So have I printed left? Yes. Have I printed root dot data? No. So I will print 1, and I will make a call on the right. So I make a call on this tree, right? So again, you do a similar process. You come at 3, right? So root is 3. Then you make a call on the left. That is root is 5. So 5 left is null. So you print 5. 5 right is null. You come back. So 5 is done. Then you go back. The new top is now 3, right? It was 5. Now it is 3. So 3 says, okay, my left is done. I will print myself, and then I will go right. So root will be 6. So you come here, right? So you went here, then you came here. 6. Now root is 6, left and right they are null, so 6 will get printed. Right is null, right? And then 6 will be popped off, right? Then so for 3, right is also done. So this call is over, right? And you come back at 1. So for 1, left is done, root is done, right is done. So this call is also over, right? Finally, the call stack will be empty, and this is the output that you will get, right? So I hope you have understood the in order traversal. Now make a bigger tree and try to generate the output for that particular tree, right? And next I will discuss post order traversal. Let us talk about post order print. So as the name suggests, post means the word after. Okay, in this case, what we do, we print root in the last. So first we print the left subtree, then we print the right subtree recursively, of course, and after then we print the root, right? So if this is the tree, once again, what I will do, I start with 1, but I have to first go in the left subtree, then I have to go in the right subtree, and then print 1, right? So at 2, I again have to print left subtree. That means I will print 4. Right? Then I will print the right subtree. So right of true is null. Then I will print 2. So I will print 2. Right? Then at 1, I have to print left, which is done. I have to print right subtree, and then I will print 2. So at 3, I will say, okay, print left subtree, which is 5. Then print the right subtree, which is 6. Then print the root, that is 3. Now for 1, left subtree is done, right subtree is done. Then I can print the root, that is 1. Right? So this is what the post order output would look like, right? You might be asking, why do we need so many traversals? Okay, for examples, what happens in certain problems is, in certain problems you are expecting that you are expecting output from the left and right subtree. For example, given a tree, I want to calculate the height of the tree, right? For example, I want to calculate what is the height of this tree, right? So in order to calculate height, what you will need? You will need to know that what is the height of the left subtree. Let's say this height is 3. What is the height of the right subtree? This height is 2. Then can you say recursively at this root node, the height is nothing but it is the maximum of left and right. Okay, maximum of the answer that you're getting from left comma right, and one more than that. So can I say the height will be 4? What is this? This is the answer from the left subtree. What is this? This is the answer from right subtree. So what I'm trying to claim is, in order to build the answer at the root node, you need the answers for the left subtree and right subtree, and hence in problems like these, you would of course need a post order traversal, right? So that is the idea. When you need answer from the child subtrees to calculate the answer at the root node, you will definitely need post order traversal there, right? So now let us write the code, and then we will do the dry run of that code, right? So writing code is very easy. So I'm in this class. So if root is null, I will return, right? Then what I will do, I'll go on the right, left, post order root dot left. Then I can say post order print root dot right, and then I will print the root node. So s out root dot data, right? Now let us go and call post order print in our display method, right? So I can just pass the root here. So t dot display, it's calling the post order print method. Now for the same input, let's copy this input, and we will see what output do we really get. Now we have given the input. I'm getting 425631. Is it the same output as we have got? 425631. Absolutely yes. Now let us do a quick call stack analysis of this method as well. So I'll copy the code. I'll put it here, and let us do a quick call stack analysis. Let's say this is my call stack. In the beginning, I give 1 as my root node. The root is 1. Then I say, okay, make a call on the left. So my root is 2. I make a call here. Now code is paused. Right call will happen later. Again, at 2, I make a call on the left. I come here. Root is 4. 4 makes a call on the left. So left is null. I return. Then 4 makes a call on the right. Right is null. Again, I make a call and return. Now I can say print root dot data. I will print root dot data. This is the top of my stack. I will print 4, right? Then if 4 is gone from the stack, what is the new top? The new top is 2, right? That means I am in this function. I am at 2. So I'm printed the left. I make a call on the right. So 2 says, okay, go and print the right. Right subtree is null. I return. Then what happens? Left and right, they are done. I will print root dot data. That means I will print 2, right? Now 2 is also gone. We are done. So 1 is at the top of the stack. Now at 1, I said, okay, go left, which is already done. Left is done. Go right. I come here, right? So now 1 makes a call to 3, right? Now 3 says, okay, go left. So 3 makes a call to 5. R5 goes here. and R5 says okay, go left, which is null, go right, which is null, and hence you print 5. So you will get 5 as the next output, right? Now once 5 is gone, you're back again at 3. 3 says okay, my left is done, this is done, I will go right. So I go to root node, that is 6, right? The root becomes 6 in this call. So this is the top. 6 says go left, null, go right, null, and hence you will print 6, right? And then 6 is also gone from the call stack. Then what happens? You are at 3. 3 says okay, my left is done, right is done, I will print root dot data. So I will print 3. I will get print 3. So 3 is also gone from the stack, and now top is at 1. So for 1, left is done, right is done, and hence you will print the root dot data, that is 1, right? So this is the output of the post order print. I hope you have understood post order traversal. Next we are going to discuss the level order traversal. Okay, let us jump into the iterative traversal, which is also known as level order traversal. Okay, so that means we won't be using recursion, we would be using some kind of iteration to iterate on the tree. Okay, some kind of loop, right? So let us take this example of tree once again. And idea is, instead of going in a depth first manner, okay, so in all the traversals that we have done so far, what is happening? We are starting from the root node, we are going here, then we are going here. So all these traversals, they are depth first traversals. That means you first go deeper into the tree, and then that's how you iterate. Okay, so your pre-order, post-order, and in order, they are depth first traversal, right? But now the traversal that we are going to do now, it will be a breadth first traversal. That means if I have a tree like this, I will be going across the breadth of each level, this level, this level, this level, right? That means I can expect an output that is 1, 2, 3, and 4, 5, 6, right? So level order traversal. So this is my level 1, then I am printing level 2, and then I am printing level 3. Okay, what is a level? All the nodes which are at same distance from root node. So level 1, all the nodes are only one node, it is at distance 0 from the root node, or let's say level 0. Level 1, all the nodes are distance 1 from the root node, and this is my level 2. All the nodes are at distance 2 from the root node. Okay, so this is also known as breadth first traversal, right? Breadth first traversal, right? Now let us see how we can achieve this kind of a traversal, right? So let's draw this tree once again. Now if you look carefully, if you start doing any traversal, that is a recursive traversal, right? So from 1 you come to 2, right? And at 2 you do not have a direct way of going to 3, right? So that means with recursion it will be very difficult for us from 2 to go directly to 3, right? And if we go to 3, we don't know a way to come to 4, right? So we cannot go back and forth, right? So how this is achieved? This is achieved by using a concept of a queue data structure. Okay, so what we will do, we will create a queue. Queue, you know, it is a P4 data structure, first in first out. So in the beginning I will push this node in the queue, fine, right? And then I will say okay, like queue dot push root. Now I will pop one node from the queue, so I will pop this node and I will push the children of this node into the queue. So I will print it, output will be 1. This is popped. And what are the children of 1? Children of 1 are 2 and 3, right? Now how do I know the children? Because I'm not going to store an integer value here, I'm going to store the reference of this node, right? So I'm going to say okay, this root is, the address of this node is stored here. So if you know the address, you also know the child values, right? So you know the children are root dot left, root dot right. I will push the reference of 2 and 3 in the queue, right? Next I will again pop one node. I'll say okay, let's remove 2, let us print it, and let us push the children of 2 in the queue. So 2 has only one child, so 4 will be pushed into the queue, right? Again repeat this process, pop one node. So now you're going to see that okay, 1 is done, 2 is done, the next node is coming is 3, right? So I will pop it, I will print it, and I will push the children of this 3, okay, into the queue. So I will push 5, 6. So you look carefully. When the second level or the first level is popped, the next level is already in the queue, right? The next level is already in the queue. Let's say I have some more nodes. Let's say I have 7, 8, and 9, right? So let us just extend this example a little bit. Now I will pop 4, I will print 4, this will be removed. 4 does not have any children, so nothing will be pushed. Next I will pop 5, I will print 5, and I will push the children of 5 into the queue. So I will push 7 and 8 into the queue, right? Next I will pop 6, I will print 6, and I will push the children of 6 into the queue. So 9 will get into the queue. Next I will pop 7, I will print 7, and no children, so nothing will happen. Next I will pop 8, print 8, no children, nothing will happen. I will pop 9, print 9, and the queue is empty, right? So no children, so queue is now empty. This will be my output of level order traversal, right? I hope you're convinced that this is the correct output for this tree, right? Now let us look at this implementation in our code as well. Let us discuss the implementation of level order print. So I'm going to create a method called as void level order print, and first of all I will need a queue object, right? And I also need to pass the root here. So I'll say okay, fine, I'll need a queue of node called queue. This is equal to new linked list. So in Java, queue is an interface and linked list is a class that implements the methods of the queue, right? We need to import this from the util package. Okay, so linked list is imported, queue interface is also imported. So to start with, you can say okay, queue dot offer, that is your add operation, right? And I can offer root inside the queue, that means I can add queue, right? Now I said you will do some work while the queue is not empty. So while the queue is not empty, what you will do, you will pop out something. You will say okay, give me the node which is at the front of the queue. So node f, this is equal to queue dot poll, right? So this removes the first node. Like we have seen in the diagram, we are always removing the node at the front of the queue, right? So this is going to remove it and return it, right? Now I can print the data of this node. So I can say s out f dot data, and now I can check if the left and the right child, if they are not null, I can push them into the queue. If f dot left is not null, I will say q dot push q dot offer f dot left, and if the right child is not null, or if the right child is not null, I can say q dot offer f dot right. So in this way, queue is getting filled using these if conditions, and it is getting empty from the front using this whole operation, right? That's all. That is the code, and now I can just run this code in the display method, or here I can say t dot level order print. Okay, root. So it's better to call it internally, because root, I don't want to access it outside. So okay, I'll just call it from the display method because we are testing the functionality. So I can say level order print. So here I can just call t dot display. So now my tree will be displayed in a level order fashion. Let's see what output do we get. So for the given tree, I'm getting 1, 2, 3, 4, 5, 6, which is correct. And if you look carefully here, for this tree, I'm getting 1, 2, 3, 4, 5, 6. Yeah, this is the tree actually. So I'm getting the correct output, which is this. So I hope you understand the level order traversal and how it is achieved using the queue data structure. The code is very simple, and you can also do a dry run of this code at your own, right? Thanks a lot. Let us start discussing binary search tree data structure. So right now we have learned about binary trees, which we said it is a tree in which every node can have at max 2 children. A binary search tree is a special kind of binary tree which is optimized for the search operation. Okay, so that is why the name called binary search tree. In short, we also call it as BST. So BST is a special kind of binary tree with the following properties. The first property is the value of all the nodes in the left subtree of a given node should be less than the value of given node. For example, if this is the root node and it has certain value, for example, this value is 8, then all the nodes which are in the left subtree, they must be less than 8. Okay, and all the nodes which are in the right, they must be greater than 8. So this is the BST property, right? Now how this makes searching easy, for example, you are searching for 5, you don't need to have to traverse the entire tree. You will have to say, okay, I will go into the left subtree, right? Now this property that we are talking about, that nodes in the left subtree would be smaller, nodes in the right subtree would be greater, it is not just applicable for the root node, but it is applicable for all the nodes of the tree. Okay, so we will see an example. How do we construct such a tree where every node follows the BST property? So this we call as the BST property, right? Or the BST properties. So this is what makes this tree very special and efficient as well, right? Now suppose we are given this data and we want to create a binary search tree from it, right? Now how we will create it, let us discuss. So first of all, we are getting 8, right? So 8 will be the root node because my tree is currently null. So 8 becomes the root node, right? Now next element that I'm getting is 3, right? Now 3, I know it is less than 8, so it will go in the left subtree of 8. So 3 will go here. Next I'm getting 10. So 10, I know it is greater than 8, so it will go into the right of 8. It will get connected here, right? Now I want to insert 1. So again, I do not know where it will go. So I will start from the root node. So 1 is less than 8, I will go left. 1 is less than 3, so I will again go left. So I will insert 1 here. Then I get 6. 6 is less than 8, I go here. Now 6, if you compare with respect to 3, it is greater, so it will go here. 6 gets inserted here. Then we have 14. So 14 is greater than 8, I go here. It is greater than 10, so I go here. So 14 will get inserted here. Then I have 4. 4 is less than 8, I go here. It is greater than 3, I go here. But it is now less than 6. So I have to travel the branches accordingly. So that means 4 will get inserted here. Then I have 13. So 13 is greater than 8, go here. 13 is greater than 10, go here. 13 is less than 14, so you will go here. And finally I have 7, right? So 7, if I start with respect to root node, less than 8, go here, greater than 3, go here, greater than 6, go here. 7 will get inserted here, right? Now this is how the binary search tree is constructed. Okay, so we have discussed how do we create a binary search tree. So we have to insert all the nodes one by one, right? Now how much time it will take to insert one node, right? So it will depend upon what is the height of the tree. Now suppose if this tree height is h and I want to insert a node, so in the worst case I have to travel one branch. For example, if I want to insert, let's say 20, right? Or let's say I want to insert 12, right? So what I have to do, I have to start with 8, go here. It is greater than 10, I have to go here. It is less than 14, I have to go here. And it is again less than 13, so I have to go here and insert. So this is how 12 will be inserted in the tree, right? Now let us talk about searching. Okay, how do I search for a given node? Now for example, I want to search for, let's say 7, right? Where is 7 present, or if it is present or not? So I just want to output yes or no, whether this is present or not. So I start with 8. If 7 is present, it must be on the left. So I go here. At 3, if 7 is present, it must be on the right. So I go here. At 6, if 7 is present, it must be on the right. So I go here. Now I hit a node which is actually 7, right? So that means if I'm again performing an operation like search, I will do it in order of h time, where height in the worst case can be n also. For example, if you say, okay, I want to insert these nodes into the binary search tree, so it will form a skewed tree like this 1, 2, 3, 4, right? So a height can become n also. So that is why I'm not saying order of n, or I'm not saying order of log n, right? So the height in the worst case will be can become order of n, right? And in the best case, if your tree is a fully completely balanced tree like this, okay, in the best case, if a tree is like this, the minimum height it will have would be log of n, right? So height will be greater than log n, greater than equal to log n, and it will be less than equal to n. So height lies in this range, right? So accordingly, the creation and the searching time, okay, not about creation but inserting one node, okay, so inserting a single node will take order of h time, where h is the height of the tree. Searching for a given node will take order of h time, where h is again the height of the tree. I hope you understood the fundamental concept behind binary search tree, and now let us dive into the implementation of it. So let us start by building a binary search tree class. Okay. So in this class, what this class should know that what is the root of this tree. So I can say, okay, private node root. So I have a root node which is a private member, because I don't want outside world to access this root directly, right? Now I want to initialize this root node by creating a tree, right? So I can say, okay, there is a binary search tree constructor, and in this case I can say this dot root, this is equal to some build tree method that I am going to create, right? Now let's see what is this build tree method going to be. So I can say, okay, public void or public node build tree. So build tree is going to read data from the user, and it's going to insert all the nodes into the tree one by one. Okay, so in the example that we took, we said, okay, we will take these nodes and we will insert them into the tree one by one. So if you take 8, you insert it into the tree, then you took 3, you inserted into the tree, then you took 10, you inserted into the tree, then you took 1, and so on, right? So what we have to do, we have to insert nodes into the tree one by one. So we will also build a insert method that will do the work for us, right? Now how do I read this data? So I will read it till I hit -1, right? So this is one way. Or you can ask how many nodes you want to insert, and then you can read n numbers. Both are fine, right? So I can do this as well, or I can say, okay, I will read n followed by n integers, right? So right now I'm doing it this way, that okay, I will read everything until I hit -1. So I can say, okay, fine, scanner equals new scanner, and now I'm going to read data, right? So I can say int data, this is equal to scanner dot next int. So while this data is not -1, what I will do, I'll insert nodes into the tree. So while data is not -1, I can say, okay, this dot root is given by the insert function, and what I need to insert, so I will say, okay, take root and take this data, insert it into the tree. Okay, so for example, if I want to insert 6, so I'll say, okay, fine, take this root node, take this number 6, and go and insert 6 into this tree. So maybe 6 will go here, right? Something like this I'm going to do. So I will give data as well, right? And finally I can say, okay, build tree is going to return root, right? That is fine. Or you can do it like this as well. Node root, which is initially null. You can say it like this as well. So I'm finally returning the root node, which will get updated here, and this root is the data member root that is here, right? Now let us write the insert method that is going to insert data into this tree. So this is just like a wrapper function. Okay, so the actual insertion will be done by the insert method. So I want to say, okay, node insert, I'm going to get root node. Now this root node is in the beginning it is this root node, but it's going to be a recursive function, so this root node is going to change, right? And the key that I want to insert, right? Okay, so I'm already getting the key. Now can you think how this insertion will work? Okay, so let us take an example of beginning. What is going to happen in the starting? So in the starting you are going to insert 8. So root is null, so here the root is null and the data that you're getting is 8. So if the root is null, can I say inserting 8 is very easy? Just create a new node and return it. So your root will get updated. So you can say, okay, root is equal to insert. You give the current root node. Maybe you can give this root node, that is fine. And you can give the data, right? So what is going to happen? You're going to say, fine, I'm inserting something into a null tree. So you can say if root is null, that means you can insert it directly. You can create that node and you can return it. So you can say return new node and the data is equal to key. So this will also act as a base case, and it will also help us in the beginning to create the actual root node of the tree, right? But if this is not true, for example, I've inserted 8 now, so root is pointing here, right? And suppose I want to insert 3. Now this 3 is given input to this tree, right? So I will compare, is 3 less than 8? So I will compare if root dot data, sorry, if key is less than root dot data, then what should I do? I should go and insert in the left subtree, right? So I can say, okay, root dot left. Now this will point to a new subtree in which 3 has been inserted. So root dot left, this is equal to insert method again, where in the root of left, and the key will remain key, right? Now this is a very important step you have to see, right? So what I'm saying is that go and insert 3 in the left subtree of 8. So if you hit this, what will happen? So your root will come here. Again, you will observe that root is null, so you will return new node of that key. So you will say, okay, fine, I'm going to create a new node 3 and I'm going to return it. So where you're going to return it? You're going to return it from here. That means it will get updated in the left of 8. So this is how 3 will get connected in the left of 8. Okay, let me finish the code. I will do a complete dry run. Okay, and the complementary case, okay, we can make it less than equal to. So if duplicate elements are present, all of them, they will go into the left subtree, else this is not the case. Else root dot right, this is equal to insert root dot right comma key. That means if it is greater, go and insert that node into the right subtree and update the root dot right. Okay, and once it is done, what I have to say? I have to say return root, right? Now this is important because every function is expecting that address of a tree or a subtree or a root node will be returned. So we are going to return the current root node. Now let us take an example of, let's say, 8 3 10 1 6, and let us try to insert some of these numbers into our tree. Okay, so I'll just take this example and I will dry run this function. So what is happening? Oh, okay, I think I missed out one thing here. I will have to read the data again also. So I have to say data equal to scanner.nextInt. So I'm inserting a number, okay, and then I'm reading the next number, right? So first of all, I will read 8, fine. So if for 8 root is null, the root will point to 8. So I will say, okay, return new node of key. So insert call is over. Next time I'm reading this number 3 using this line, data is equal to scanner.nextInt. Data is not -1, so I say, okay, root is equal to insert into this tree, right? So root is now 8 and I'm saying insert 3. So if you want to insert 3, what will happen? The base case is not true. You come here, if key is less than equal to root data, yes, root dot left, this is equal to insert root dot left comma key, right? So I will draw the call stack as well. So I have 8. So 8 makes a call on the left. So left is null. So you hit the base case. You say return new node of key, right? So it returns a new node 3. So this function returns a new node 3. Now where is this 3 getting updated? So 3 is getting updated in the root dot left. So it is getting connected in the left of 8. So this is how it is getting connected, right? So this is over. And now from this function call you return root. So you basically return the address of 8 back into the uh, build tree function. Okay, now you want to insert 10. Okay, you got 10. Again you compare 10 with respect to 8, right? So what happens? You call the insert function, take this tree, insert 8. Now root 8 is not null, 10 is not less than root. So you come into the else block. You say root dot write, this is equal to insert root dot write comma key. Now root dot write, this is null. That means you again hit the base case. So this base case returns a new node, that is 10. Now where is this node returned? It is returned to the previous function, which is this. And where it is getting updated? So 10 is getting updated in the right of 8. So you get 10 here, and this base case is over. So 8 is connected with 10, and you return root. So what is the root node? This 8 is the root node. So you return this address back into the main, right? Now comes the next node. You read 1 and you want to insert 1 into this particular tree. So now this is the tree, 8, 3 and 10, right? Now you want to insert 1 here. So 1 is less than 8, fine. So 8 says go and insert 1 in my left subtree. 8 makes a call here, right? 8 makes a call here. Now when you reach 3, so your root is 3, right? And you again compare, is 3 is 1 less than equal to 3? The answer is yes. So you again make a call, root dot left, this is equal to insert root dot left. So you make a call here. So you make a call in the left of 3. Now this value is null. So you return a new node, that is 1. This 1 is updated in the left of 3. So you return 1. 1 gets attached in the left of 3. And then you say return root. Effectively now you're returning the address of 3 back to 8. Now 8's left is again, earlier it was referring to 3, now again it is referring to 3, but now with 3 1 is also attached. Okay, so that is what I was saying, that 1 gets inserted in the left subtree of 8, right? So this is again updated. So earlier 8 was storing the address of 3, now again it is storing the address of 3. And again you say, okay, from this function I'm going to return root. So you are going to return the address of 8 back into the build tree method. Okay, let us do one more insertion. Let's say I want to insert 6. So 6 is less than 8. So this is now the tree, 8, 3, 1 and 10, right? Now 6 is less than 8, I go here. 6 is greater than 3, I go here. So again what happens? This is null, so you return a new node. So you create 6. So that address is attached in the right of 3, and from 3 you say return root. So 3 gives its address back to 8, and 8 gives its address back to me, right? So by keep on doing this, you will be able to insert all the nodes until you hit -1 into this tree, right? So I hope you have understood the insert method. The insert method is going to take order of h time to insert one node into the tree, right? Now let us try run this code and see if it works. Okay, I want to execute this code. Dry run we have already done. So I have a binary search tree test class. I've created a main method. So I have to create a BST object here. So I have to say binary search tree BST. This is equal to new binary search tree. This will automatically trigger the build tree method, and it will start reading input from the user. Okay, but if I want to display this tree, maybe I have to do some kind of traversal as well. So I go into the binary search tree class, and here we can write a method for doing the in order print of this tree, right? So void in order, I can say node root, And here I can say, okay, if root is null, do nothing. Otherwise, do a in order print on the left subtree, print the root data, and do a in order print on the root dot right. So let's call this as in order print, in order print. Okay, let me create a display method from where I will call the in order print method. So I can say, okay, in order print, and here I give root, or you can say this dot root. Both are okay. This dot root means we are talking about the data member root. Okay, so display method is done. So I am going to create the BST, and I can say BST dot display. Let us execute this code. The build is complete. It is waiting for us to give input. So let us give the input, and here we got some output. So this is the output of in order traversal of this tree, and this output looks sorted. Let us see what output we should ideally get. So let us quickly create a tree with these numbers. So I have 8, I have 3, I have 10, I have 1, I have 6, I have 14, I have 4. So 4 will go here. Then I have 13. So 13 will go here. Then I have 7. So 7 will go here. That's it, right? Now in order traversal, that means before printing root node, you will print left and then you will print right. So now we know all the nodes in the left subtree are smaller. All the nodes here are greater, right? And if you do it for every node, you will observe your output will be sorted. So at 3, if I say, okay, go left, that means I will print 1. Then you will print root, that is 3. Then you will print the right subtree. So for 6, you will print left, root, right. So you will print 4, 6, 7. And then you go back here. For 8, left subtree has been printed. So you print root and then you print right. So you come here. At 10, you say, okay, left, which is null, then root, which is 10, then the right subtree. So again here, left, root, right. So again you will print 13 and 14. Right? So this is the expected output of in order traversal. Let us verify if it is correct. So we are getting 1, 3, 4, 6, 7, 8, 10, 13, 14, which is absolutely correct. So that means our build tree and the insert methods, they are working perfectly fine, right? So I hope you have understood the insertion in a binary search tree. So now let us talk about the search operation in a binary search tree. So given this BST, I want to search for a particular node. For example, let's say I'm given that I'm searching for a key that is 2. How do I search for 2, right? So I will start from the root node. I will compare 8 with 2. So I will say, okay, 2 is less than 8. So I will go here. I will go left. 2 is also less than 3. So I will go here. And here I compare if 2 with 1. So what happens? So if 2 is present, it must be on the right of 1. So I go here. So I go in the right of 1. But as I reach here, I see that I am hitting a null value. That means 2 is not present, right? So one of our case would be that if I hit a node that is null, right? That means the given key is not present. So I can simply return false. That will be one kind of a base case, right? Now suppose I am not searching for 2, but I am searching for, let's say, 7, right? So 7 is present here. So let's see how we can do it. Now if I compare 7 with 8, I know it is less than 8. So I will go left. If I come to 3, 7 is greater than 3. So I will come towards right. And at 6, 7 is greater than 6. So I will again come towards right. So now I'm hitting a node where my root data matches with key. So what should I return? Of course, I should return true. So if root data matches with my key, I would be returning true from the method, right? Now let us talk about a recursive case. If we are searching recursively, so what exactly we are doing, right? So we are saying that fine, I'm going to compare root node with the given key. Let's say the key is 7. So I'm comparing 8 with 7, right? Now if the key is not matching, so what I'm saying that, okay, if the key is lesser, I will search in the left subtree. Whatever is the answer of left subtree, I will return that answer. Now suppose the left subtree says true, that key is found, I will return true. But if the left subtree says false, I will go and search. I will not go and search in the right subtree. Why? Because I am already checking whether I should go left or I should go right, right? Because if the key is less than or equal to, it will be present in the left subtree. If the key is greater than or equal to root node, it will be present in the right subtree. Let us take an example of 13, right? So now 13 is greater. So I will not make a call in the left subtree. I will make a call in the right subtree. So I say, okay, go and search in this tree. Now at 10, 13 is greater. What I do, I say, okay, go and search in the right subtree. At 14, 13 is less than 14. So what do? I say, go and search in the left subtree. Now as I reach this node, I say, okay, this matches my key. So what I will do, I will return true. This 14 will also return true. This 10 will also return true. And this 8 will also return true. So this is how true will be propagated back, right? So what I have to do, if root data is let's say root data is greater than equal to key, right? So that means key is less than equal to root data. That means I will return the answer of the search method by calling the left subtree. So I will say, okay, return whatever has been returned by the left subtree for that key. So root dot left comma key, right? Otherwise I'll say return whatever has been returned by the search method by calling it on the right tree. So root dot right comma key, right? So this will be my search method. Now let us quickly write this method in our code as well, and then we will see whether this works correctly or not. It should work, right? So this, I'm writing it recursively. You can also write it iteratively, right? So the only thing that you need to do is you need to travel at max from the root node to one of the leaf nodes. In the worst case, that means the complexity of this method will be order of h, where h can lie between n and log n, right? So in the best case scenario, when the tree is perfectly balanced, your height will be log n. In the worst case, if all the nodes are on one side, that is called as a skewed tree, your complexity for search operation will be order of n. Now it is much better than binary tree, because in binary tree you have to search for across all the nodes, but here we know that we have to move in one direction, either left or right, but not both. Okay, let us quickly code it up and see. So let us write a method called search. So it will have a boolean return type. So I can say boolean search. I'm going to get the root node, and I'm also going to get the key that I'm searching for. Okay, let's say this is some search function, right? So it's a recursive function, so I have to write a wrapper function as well. So I can say boolean search, where I'm just getting the key. So it will return whatever has been returned by the search function, and here I will pass the root node and the key. Now let us see how this can be done. So I discussed there will be two base case. So you can stop if your root is null, that means the key is not present. So I can say return false in that case. But if your root matches with the key, you can return true in that case. Okay, otherwise I have to compare. Okay, so I have to say if root dot data is greater than equal to key, or you can say key is less than equal to root data, then you have to call the search function on the left, and you have to return whatever that function is returning. So you return the output of the left subtree. So search in the left subtree, that is root dot left comma key, else you can return the output of the right subtree. So root dot right comma right. So this will be your search function. Recursive function is the search function. So this looks good. Now let us test our method. So here I can say, okay, sout t dot search. Let's say I'm going to search for 4. sorry, this is not the correct file. I have to do it in binary search tree. So bst dot search, I can say, let's just search for 4, and bst dot search for, let's say, 41, right? So I will s out the output, and same here. So this looks good to go, and let us run our code. Now let us give some elements, let's say 10, 20, 30, 41, 3, 5, 6, 8, 9, -1, right? So this creates a tree, and for the value 4, I'm getting an answer false, that 4 is not present. And for other values, I'm getting the tree is the 41 is present. The 41 is present here, right? And you can see in order display is looking sorted, and 4 is not present in this, and 41 is present. Okay, so this is how the search method is working. I hope you understood the search method really well. Next we will move on to deletion. Let us discuss deletion in a case of a binary search tree. So deletion means that, okay, I've given a particular node and I want to remove that node. Okay, for example, someone might say that, okay, let us delete 13, or let us delete 3, or let us delete 8, right? So if you observe closely, there are three kinds of nodes. Okay, so there are nodes which have no children, also called as leaf nodes. So there are nodes with 0 children. Deleting them is very easy. There are also nodes which have one child. Deleting them is slightly more difficult. And there are nodes which have two children. They are even more tricky to delete. Okay, for example, node like 8, if I want to delete this node, then how would my tree structure would look like? So we have to discuss all these scenarios now, right? So let us start with scenario 1, and let me create a copy of this tree as well, so that I can use it, right? Now suppose I want to delete a node like 4, or I want to delete 7, or I want to delete 13. So deleting it is very easy. So suppose, let's say I want to delete 7, right? So that is my case 1. So case number 1. So in that case, what I need to do? First, I need to search for 7. Where is this 7 located? Right? So I need to reach that node. Right? So I start from 8. I say, okay, 7 must be on the left. So I go to 3. So 3 says 7 must be on the right. So I go here. Now 6 says 7 must be on uh, right. So I go here. Right. Now if I reach this node, what should I do? I would say, okay, fine. This is the node that I want to delete. So I will somehow delete this node, and I will return a value null to the parent. So basically what I will do in every call, I will try to change the tree. I will say, okay, in the right of 6, I will attach a null value, and this node is now referenced by no one. So that means this will be automatically garbage collected. Okay, so garbage collector will come, and it will get garbage collected because no one is referring to this node. Okay, so garbage collection mechanism will clear out the memory occupied with by this node. Okay, so what I need to do is I need to reach this node, and if this matches with the data that I'm finding out, I have to return delete null. Okay, so when I return null value, that will get updated in the right of 6. Okay, so I will also update. So that means the return type of the function will be of the type node. It will not be a void function. So there will be a function, and I say, okay, fine, root dot write, this is equal to some delete node, and delete node returns a null value which gets attached in the right of 6. Okay, so this function is delete node, something like this I will be doing. So just to give you an idea how it's going to work, so basically we are going to update the right reference in the parent. That is case number 1. This is how it will be deleted. Now let us write the code and see case number 1, and then we will discuss case number 2 and case number 3. So I am in the file called binary search tree.java, which we have written. Now we are going to define a method called as node remove, and here we are going to accept the current root node, and the key that we want to delete, right? So of course there will be some base cases which we will see, okay, and there will be some recursive cases as well, right? So one thing that I told you, that first we have to search for the node. Okay, now three possibilities can happen. So if you are at 8 and that the node that you're deleting is also 8, then you can do work there. But if the data is lesser than 8, you have to go left. If the data is greater than 8, then you have to go right. So first let us do the searching part. So if the key that you want to remove is less than root dot data, in that case you do not need to do anything at the current root node. What you need to do is make a recursive call in the left subtree. For example, this is 8 and I want to delete something which is 5. A 5 is not present here. So what I will say, okay, I'll say, okay, go and remove 5 from the left subtree. The remove function will go and remove 5 from the left subtree. So you say root dot left and key. Go into this tree and remove it. Now it is possible 5 might be present here, or 5 might be present here, or 5 might be present here. We do not know, right? So whatever it is, after removing 5, whatever is the new root of the tree, that will be given back to me. So I will say, okay, 8 dot left, this is equal to remove. So I can say root dot left should be updated by the reference of the new left subtree that I'm going to get. Now it is possible that here the node was 6 and nothing changed. Still I will get the address of 6 back here, right? So that is something we have to do. So root dot left, this is equal to remove. So I make a call in the left subtree to remove it. So this is a recursive case, right? Else it is also possible that key is greater than root data. That means I have to do the same thing but in the right subtree. For example, I want to remove 10. I can say, okay, go and remove 10 from the right subtree, and whatever is the new tree, give the reference back to me. I can say root dot right, this is equal to remove root dot right comma key, right? Else, that means this is the node where I have to do the actual deletion. That means it is the case of equality, right? So this is the node to be deleted. Now I said there can be three cases. Case number 1, that I have a node with no children. In that case it is pretty easy. That for example, if you are talking about a node like this, a node like 7, right? So if you have already traversed till this node and you want to delete this node, it matches 7. So what I can say, I can simply say return null, right? I can simply say return null. So I can say if root dot data matches key, I can say return null. Now this null will be attached in the back in the parent, right? So if it was present in the left, so left value of the parent will become null. For example, 6 and 7, right? So 6 made a call on the right that, okay, delete the 7 node from this subtree. Now 7 is equal to 7, so I'm saying return null, right? This null is returned, and root dot right called the remove function which returned null. So this remove function returned null. So eventually what will happen, the right of 6 will start referring to null, and from 6 we will return the address of this subtree, which is nothing but this node itself, right? So finally what we have to return, we have to return root also, right? Like if we are not returning null, that means if we are returning from some other node, we have to return the same root that we were getting as input. So 6 will return its address. So 7 returns a null, okay, which gets attached here. 6 returns 6, 3 returns 3, 8 returns 8. Okay, this is how it's going to happen. So we have discussed the case with 0 children. Now let us discuss the case when we have one child, right? Now suppose I want to remove 10, right? Now look at this. I want to remove 10. So let me draw this diagram again, right? I want to remove 10, right? Now this is case number 2 where I have one child, right? Now if you look carefully, if I want to remove 10, what should I do, right? So that simply means that it is a node which has either a left child or it has a right child, right? If I want to remove 10, can I simply say that whatever is the left subtree or the right subtree of 10, this will get connected directly here and 10 will be removed. So if I simply say remove 10, and this child will be connected here. Is it correct? Is it a BST? The answer is yes. For 8, 14 is greater and 13 is less than 14. So it is correctly placed. Okay. So what I'm trying to say is, if you have 10 and if you want to remove 10, right? What? So you have to actually return the non-null child of 10 back to 8. What is the non-null child? So this is the right subtree, right? So if you want to remove this node, you have to return the reference of this right subtree back to 8. So 8 will point to 14 and the remaining subtree will get attached as it is. So nothing changes in the subtree. So nothing changes in the subtree, right? Okay. This is the point that I'm trying to make, right? So how do you reach 10? By the search mechanism that we have already written, right? I want to delete 10, so 10 is greater, so I will come here. Now at this node, 10 is equal to 10. What should I do? I will return the non-null child of 10 back to the parent. So this is what I have to do. Now let us see how we can write it in the form of code. All right. Okay. So I think I have made a small mistake. This is a node to delete. So of course the data will be equal because we are in the else case. But case 1 was no children. Okay. So I need to fix this case. So the condition would be both left and right of that node are null. Okay. So I'm fixing a small mistake here. Root dot left is null. And root dot right is also null. Null would be capital I. Small. So I can return null, right? So root dot left is null and root dot right is also null. That means if it is a leaf node. Okay. Now let's talk about case 2. That means exactly one of the child is not null. So else if root dot left is null, that means the left child is null and the right child is not null. In that case, can I say I will return root dot right back to the parent? Else if it is the other way around, if root dot right is null, that means the right subtree does not exist. So we are at a node where the right subtree is null, but the left subtree is existing and I want to delete this node. So what I need to do, I need to return the address of the left subtree back to the parent. So I can say return root dot left. Now what's going to happen? This will get attached here. But do you really think that this node will be deleted? Do you think this node will be deleted? The answer is yes. Why? Because who was storing the address of this node? The address was being stored here. If this is updated, if the right of this root node is updated, then no one is referring to this node. That means in a way, this object becomes eligible for garbage collection. So this will get deleted, right? So this is what we need to do. Now we have a third case, which is case 3. That means a node has 2 children. We need to delete a node with 2 children. So let us discuss how this case 3 will work. So let us discuss case number 3. This is the tree. And suppose I want to delete a node which has 2 children. So it can be any node which has 2 children. So let's say I want to delete 8, right? Now if I directly delete 8, this tree will be split into 2 parts, which I don't want. This tree should remain same, right? This tree should remain same. So what I can do is, I need a way so that I do not disturb the tree structure a lot, right? If I talk about in order traversal of this tree, I get 1, 3, 4, 6, 7, 8, 10, 13 and 14, right? So this is what I get, right? If I want to delete 8, the new root node should be either 7, okay, or it should be either 10. So one of them should become the replacement of this node, right? Now how I'm going to do it? So it can be the largest node in the left subtree. That is option number 1, right? Option 1 is make the largest in the left subtree as the root node, right? Option number 2 is make the smallest in the right subtree as the root node, in the right subtree as the root node. So you can use any of these options. Okay, so if I show you, if I make smallest in the largest in the left subtree as the root node, in that case 7 will become the root node. Okay, now how it is done, let us see. Now suppose you have reached the node which you want to delete and it has 2 children, right? So you will say, okay, I'm going to find out the largest node in the left subtree. So how do you find the largest node in the left subtree? You start from this node and you try to keep on going right. You always go right, and eventually when you stop here, because the right of this node is null, so you have to stop at this node, and you will have to say, okay, this is the largest node, and I will put this node here, right? Now putting means I will copy the data, so you will copy the data 7 here. So this data is copied, right? I'm not changing the node structure, I'm just copying the data. So 7 is copied here, right? Now if you copy 7 here, what you will observe? You will observe this 7 is duplicate, right? This is present 2 times. This is duplicate, right? Now what I can do is, can I make a recursive call to remove 7 from this subtree? From this particular subtree. Can it be done? The answer is yes. If I remove 7 from this tree, then my work will be done, right? Now if you look carefully, now 7 will be a node which has either, okay, it will have either no children, for example in this case, or if it is the largest node, it will not have any right child, right? So 7 can have a left child, can have a left subtree, right? 7 can have a left subtree, right? So that means if I'm recursively removing 7 from this tree, two things can happen. 7 does not have any child, so it will fall back to case number 1, that a node with no children, so it can be easily removed. I can return a null here, right? Or 7 has a left subtree. In that case, that subtree can be returned here, and it will be correct to attach it. Why? Because all these nodes, they are greater than 6, but they are less than 7. So they can be attached directly in the right of 6, right? So 7 still can be removed. So this, if this is the case, it will handled by case number 1. If this is the case, it will be handled by case number 2, that a node has one left child or right child, but it cannot have both. Okay, so you can see largest node can never have a right child. Okay, similarly the smallest node can never have a left child because it is a BST, right? If it is has a left child, then it is not the smallest, right? So we are going right until we don't find anything on the right. So 7 can be replaced. Okay, so that means in this case 7 is not having any left child. I want to remove this node. I will make a recursive call on this left subtree to remove 7. So 7 will be removed, and this is how the tree structure would look like, right? So I hope you are able to understand. New tree would look like this. It will be 7, 3, 1, 6, 4, and here I have 10, 14, and 13. This is how the new tree would look like. If you talk about the in order traversal, it will be 1, 3, 4, 6, 7, 10, 13, 14. Is it correct? Of course it is correct. Is 8 removed? Yes, 8 is removed from this traversal, right? Now let us look at into the code how this can be actually done, right? So I have case 3 where the node has 2 children. So this can be handled by the else block. So what we need to do? We need to uh, so first we need to do is we need to find the max node in the left subtree. Okay, so I can say, okay, I will take a temp variable, node temp, this is equal to root dot left. So I can say while temp dot right is not equal to null, so I will move this temp towards right. So temp equal to temp dot right. So if you are confused what we are doing, now suppose this is the tree 8, let's say I have 5, 6, 7, and I have some nodes here as well, right? I'm saying, okay, I want to find the largest in the left subtree. So I start a temp here. So temp dot right is not null, so temp goes here. Again, temp dot right is not null, temp goes here. Now temp dot right is null, so what do I do? I stop. So even if it is a left subtree, temp will stop at 7, right? Okay, so we found out the node. Now what I need to do, I need to replace the data here. So I can say, okay, fine, root dot data will be replaced by temp dot data, the data of the temp. So I copy this 7 here, right? Now what I need to do, I need to recursively delete the node 7 from the left subtree. So can I call the remove function? Yes, because it will either lead to case 2 or case 1, which I have handled, right? So I can say, okay, fine. Now my function is to remove the node with temp dot data from the left subtree. So I can say remove root dot left. The node is called temp dot data. I don't want to remove 8 now. I want to remove 7 now. So that is why the value is not key, but it is temp dot data. But after removing this, something will be updated, right? So I am standing here. I'm making a function call on this left subtree. So this left subtree will tell me the updated address of the left subtree or the updated reference. So I have to say that root dot left, this is equal to remove, right? So whatever is the tree after removing, please tell me, right? So root dot left, this is equal to remove, right? So once it is done, what should I do? I will simply return the address of the root. So this is something we will do, right? So I'll tell you quickly what is happening here, right? Okay, return root we have already done at the end, so no need to do it here. So we have 3 cases, right? When we are at the node which is matching the given key that we need to delete. Okay, we have 2 recursive cases which are basically helping us to reach a node. Okay, so there will be a base case also, right? So base case would be that if node is not present. So if node is not present, we might end up at a value that is null, right? So I will show you what will be the base case. Now suppose I want to delete let's say I want to delete 41, right? Now I start with, let's say, 7. I say, okay, 41 is greater, I go to 10. It is greater, I go to 14. Now it says it must be on the right, so I go here. So basically the right of 14 is null. So if I reach a value that is null, that means the node is not present. So it is just like the search method where we were returning false. Here we will not do anything. So if root becomes null at a certain point, right? So I can say, okay, I'm also going to return null, right? So this, I think, makes the code complete. Now let us test our functionality by going to binary search tree test file. Okay, so okay, I was all doing searching earlier. Now I can say, okay, I will remove something and then I will display the tree. Okay, one more thing we have to do is we cannot call the remove function directly because we have to supply the value of root. So we'll create a wrapper function. Let's say node remove key, let's say void remove key. This is the method, and here we will only accept the key, right? And from here we'll say, okay, let us call the remove function where we will give the actual root and the key here, right? So now from binary search tree test we can say, okay, bst dot remove key, and here I can give some key, let's say 41. Now if this is present, it will get removed, so I will give this value, and let's say I want to display this tree. So I have given this particular input. So this is the tree before printing, before removing. Then I removed 41, and this is the tree, right? So we can experiment with this tree as well that we had. For this tree, the input was 8, 3, 10, 1, 6, 14, 4, 13, and 7. Let us try to play with this tree as well. So I will quickly type the input. So this is the tree from the diagram, and now from this tree, let's say I want to go with case 1 where I want to remove, let's say, 7. So I will give input as, let's say, 7, or I can ask the user for the node to delete. Okay, that is also doable. I will just rerun this code. and I want to delete 7 from this tree. Let's rerun it. Okay, so let's say, sorry, this is the wrong input we have given. All right, so this is the input we have given, and now from this input I have removed 7. So you can see the 7 has been removed from this tree, right? So that means case 1 is working fine. Now let us rerun this once again, and let us discuss case 2 where I want to remove, let's say, 10. So the same input goes, but I have to remove 10, so I have to rerun this code once again. I will stop it and I will rerun it. Let's say I'm removing 10. Now from this code you can see 10 has been removed. That means it is working fine for case 2 as well. Case 3, let's say I want to remove 8. So I want to remove 8. I will rerun this code and let's see. Now after removing 8, you can see this is the in order traversal of the tree, which looks correct. Okay, so in this code I have 2 4s, which is okay, but you can see 8 is removed and 8 was the root node of the tree, right? That means it is working fine for all the 3 cases. That's about how you remove a node from a binary search tree. Okay, if you want a small dry run, we can do it once again. Let's say now you're removing it. So as I discussed, so what are you doing? You had 7 here, right? So you say, okay, I want to remove 8. So I will go in my right subtree, in the left subtree, and I will try to iteratively find the largest node. So it says okay, 3 says okay, temp is here, temp goes here, right is not null, temp goes here, right? Then I say root dot data. This is the current root where I want to delete. So I say root dot data, this is equal to temp dot data. So 7 is copied here. Then I make a recursive call on this. I say okay, root dot left, this is equal to remove. Okay, if I talk about in the code, I'm making this change here. If I show you, okay, this is the remove function. So I'm saying root dot left, this is equal to remove root dot left and temp dot data. So I'm not saying remove 8, I'm saying remove 7 from this tree, right? Because 7 is now duplicate. So I can say root dot left should point to a new tree in which 7 is removed. So now I say 7, I want to remove 7 from here. So 7 is greater than 3, I go here. 7 is greater than 6, I go here. So I reach finally 7. If I reach 7, I say return null. Now 6 right is pointing to null and I say return root. So 6 is being returned. So 3 refers to 6, this node is gone. And from 3 I say return root. So 7 now refers to this 3. So this is what is happening when I am doing a recursive call for deleting 7 from this tree. I hope all those who had a doubt, now it is clear. And this is how removal in BST works.
Time complexity. All right. So how do we talk about the time complexity of binary search? So what is really happening is, initially I have the search space of size n, right? Initially I have the search space of size n, and I guess the midpoint. I guess the midpoint, right, as my guess. Right? If my guess is too low, then I'm able to remove these elements. Right? I'm able to remove these elements. How many elements was I able to remove? So if this is 0, this is mid, and this is n, then after one guess, if my guess was too low, then how many elements was I able to remove? I was able to remove n plus 1 by 2 elements. Right? Yes or no? On the other hand, if my guess was too small, then I would be able to remove all these different elements. Right? Everything from mid all the way till n minus 1. Right? Even then, I was able to remove n plus 1 by 2 elements. Right? I was able to remove n plus 1 by 2 elements. So what really happens is, every time I make a guess, I'm reducing the search space by half. right? I'm halving the search space with every guess. Every guess. Right? So suppose we started with this guess n, right? We started the search space of n. After one guess, I will have a search space of n by 2. After one more guess, I will have a search space of n by 4. One more guess, I will have a search space of n by 8. Right? And when will I end? So finally, this search space will reduce down. This search space will reduce down to just one element. Right? This search space will reduce down to just one element. Is that clear? So the question is, how many guesses did it take? So it took me one guess over here, it took me one guess over here, one guess over here, one guess over here, and so on and so forth. So how many guesses did it take? Right? How many guesses did it take? So no, guys, it did not take me n plus n by 2 plus n by 4 all the way till 1. No, this is not how many guesses I got. Right? This is incorrect. So remember that when we are moving from this search space to this search space, I am making one guess. I am not making n guesses over here. Right? I made just one guess and I was able to reduce my search space from n to n by 2. Right? So basically, at the 0th guess, when I have not made any guess, my search space is of size n. After first guess, right? After first guess, my search space is of size n by 2 to the power 1. After second guess, my search space is of size n by 2 to the power 2. After the ith guess, my search space will be of the size n by 2 to the power I. Right? Now the question is, at what value of k? At what value of k will this thing become equal to 1? At what value of k will my search space reduce to one single element? Right? That is the question that we are asking ourselves. So this is the equation that we get, right? So at the kth guess, our search space will be this, and we want the search space to have just one element. So can we find the value of k from here? Can we find the value of k from here? So what can we say? This implies that n equals to 2 to the power k, which implies that I can take log on both sides. Right? I can take log base 2 on both sides, log base 2 of 2 to the power k, right? Which implies that k equals to log base 2 of n. Is that clear? Yes. So I am taking order of log n guesses. I am making order of log n guesses, right? And that is the complexity. That is the time complexity of binary search. Is that clear? Yes. Is that clear, guys? So basically, we started with an array of size n. Then after first guess, we were able to reduce it to half the size. Then after the second guess, we were able to reduce it to 1/4 the size, and so on and so forth. So how many guesses will we take to reduce it to size 1? Well, it will take us log base 2 of n guesses. Right? The depth of this tree, the depth of this is log base 2 of n. Is that clear? Right? Okay. What about the space complexity? What about the space complexity? So let us go to the code to analyze the space complexity. Let us go back to our code and let us see what variables we are using. Okay? So this is our code. Let us see what variables we are using. So we are declaring a variable over here, n. We are declaring a low, we are declaring a high, and we are declaring a mid. Right? All of these take constant space. They are just integers. So overall, our space is just constant. Right? We are not allocating any space that is dependent on the input. We are just allocating a constant space. Right? Notice that this vector, we are not allocating this. This is given to us already. Given to us. Since we are not changing this array at all, so we don't have to allocate the space for the array. All right? The array is given to us. So the space complexity of binary search is going to be simply order of 1. All right? Constant space. Is that clear, guys? Perfect, perfect, perfect. Now let me ask you a question. Let me ask you a fun question over here. So this is called binary search. Right? This is called binary search. Binary search. Why is it called binary search? Because we are splitting into two parts. Two parts with every guess. Right? And we saw that when we do binary search, our complexity turns out to be log base 2 of n. Right? Our complexity turns out to be log base 2 of n. What if instead of binary search, what if I try to come up with something like ternary search? What if I tried to come up with something like ternary search? So first of all, how would ternary search even work? Right? How would ternary search even work? If I have this particular array, then now I have to guess two values. I have to get mid 1 and I have to get mid 2. Right? This is my low. This is my high. In ternary search, what I can do is I can make two guesses. Right? I can make two guesses. I can say mid 1 equals to low plus high minus low by 3. Right? And I can say mid 2 equals to low plus 2 times high minus low by 3. Yes or no? Can I do that? And then I can compare. Right? Then I can compare. So I can compare AR of mid 1 with my key. Right? I can compare AR of mid 2 with my key. Right? And what will I get? What will I get? Either my key will lie in this area, or my key will lie in this area, or my key will lie in this area. Yes, that is all the possibilities, right? My key cannot lie in both these areas at the same time. Right? My key cannot lie in both these areas at the same time. Does that make sense? So after one guess, we were able to reduce our search space by 1 to 1/3. Right? From n, we could go to n by 3. Right? We could eliminate a larger chunk of our search space. Does that make sense? This is called ternary search. This is called ternary search. And in general, you can extend this idea. You can define something called a k-array search. And in k-array search, what you will do is you will calculate mid 1, mid 2, all the way till mid k minus 1. Right? And then we will compare with all of them. That will allow us to, in one guess, it will allow us to go from n all the way till n by k. Right? Does that make sense? Yes, ternary means 3 divisions. Binary means 2 divisions. K-array means k divisions. All right? Is that clear? Example of ternary search? Well, the example is very simple, right? We given an array. What I'm going to do is I'm going to make 2 guesses. Right? Instead of making one guess at any point, I'm going to make 2 guesses. And based on these 2 guesses, I'm going to decide whether I should be looking over here, or I should be looking over here, or I should be looking over here. Right? Going back to our original question, when we were supposed to guess between 0 and 1000. Right? Instead of you giving me a guess like 500, you could have given me 2 guesses at the same time. You could have given me 333 and 666. Right? And then I could have told you that, okay, it is less than 333, or it is between this, or it is above this. Does that make sense? Yes? Does that make sense? Right? So the time complexity of ternary search, it seems that the time complexity of ternary search will be order of log base 3 of n. Right? Because we are dividing by 3 every time. Similarly, the time complexity of k-array search would be order of log base k of n. Yes? Now, which is greater? Which do you think is greater? Is log base 2 of n more, or is log base 3 of n more, or is log base k of n more? Right? For some large value of k, which value is more? Which value is smaller? Right? So which value is larger? Which value is smaller? Well, if we divide by 2, then it takes us certain number of steps to reach 1. If we divide by 3, then it will take us lesser steps to reach 1. Right? If we divide by 3, then it will take us lesser steps to reach 1. So log base 2 is greater than log base 3n, which is greater than log base kn. Right? So it seems like k-array search should be the fastest. Should be the fastest, right? So why do people still use binary search? Why do people still use binary search? Why don't we always have k-ary search? K-ary search seems to be very fast, right? And it seems that I can make it as fast as I want, right? I can just increase the value of k to make it as fast as I want. Yes or no? Yes? Well, let us see what is the fastest value I can have. So maybe when k equals to n, I will get log base n of n, right? Which is simply 1. So I will be able to find the answer in just one guess. That is amazing, right? I will be able to find the answer in just one guess. That's very, very weird, right? I was able to find the answer. I was able to search the element in the array in just one guess if k equals to n. Is that correct? Is that correct? Yes, but there's a catch over here. Right? Now what really happened was we had this array and we made every element as a guess. Right? We made every single element as a guess. And then we checked if our guess is between over here or 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 over here, right? In one guess itself, we made we chose n different values and different midpoints, right? N minus one different midpoints. So are we really doing an efficient search over here? No, this has reduced to the linear search. Right? This has reduced to linear search. So it turns out that when k equals to n, we were expecting it to take just one guess. It did take just one guess, but inside that single guess, we were doing a linear search. Right? So this is the worst thing that we can do. Does that make sense? K equals to n is the worst thing that we can do. So what really gives? We see that our intuition does not equal our math over here. Right? Math says that this should be faster, but intuition says that this should be slower. So what really gives over here? Right? What really gives over here? Well, there's a catch. Right? There's a catch in the fact that this is big O complexity. Right? There's a hidden constant factor. Let us look at the exact complexity of searching. Right? Let us look at the exact complexity of k-ary search. If I'm doing binary search, then I have one guess, right? I have one midpoint. Yes? I have one midpoint. Do you agree? And what check am I making? I'm comparing A of mid with k. Right? How many comparisons is this? This is one comparison. Right? So my actual complexity is 1 times log base 2 of n. Right? This is in the case of binary search. On the other hand, when I have ternary search, I will guess 2 midpoints. Right? I will be guessing 2 midpoints. And then what comparisons do I have to make? I have to compare A of mid 1 with k. I have to compare A of mid 2 with k. Do you agree? Yes, I have to compare A of mid 1 with k, and I have to compare A of mid 2 with k. So how many comparisons is that? This is in fact 2 comparisons. Right? Now you see the hidden cost. As we increase the value of k, the number of comparisons for each guess increase. Does that make sense? Yes, guys. So for ternary search, our complexity is 2 times log base 3 of n. Right? This is for ternary search. And in general, for k-ary search, our complexity will be log base k of n. But for every guess, we will have to make k minus 1 comparisons. Right? We'll have to make k minus 1 comparisons. Now let us ask this question again. What do you think is larger? Right? What do you think is larger? Is log base 2 of n times 1 larger? Or is 2 times log base 3 of n larger? Or is k minus 1 times log base k of n larger? Right? Which one of these is larger? Well, now we know that actually this is the reverse, the other way around. This is the slowest. This is the largest value, so this is the slowest. And in fact, binary search is the fastest. Is that clear? So we can totally do k research. We can totally do a ternary search. We can totally do a k research. But practically, binary search will work much, much faster. Is that clear, guys? Is that clear? Binary search will work much, much faster. Right? Cool. Now, there's this question. Now you might be thinking that, okay, you told us about ternary search, you told us about k research, and then you said that, okay, those don't really matter, right? Why did you even tell us in the first place? Right? Why did you tell this to us in the first place? The reason is that in certain situations, k research can become faster. Right? K research can become faster. Let us look at how. Right? Let us look at how. Suppose that we are dealing with some sort of a disk, right? Hard disk. Right? Suppose that we are dealing with some sort of a hard disk. Do you know that hard disk is split into blocks and sectors and tracks? Yes. So basically, we are talking about a spinning hard disk over here. Right? We're not talking about that the new SSDs over here. We're talking about that spinning hard disk over here, the magnetic hard disk. So what really happens is, in a magnetic hard disk, you have several platters. Right? You have several platters, and for each platter, you have a read head. Right? You have a read head that is at a particular platter, that is tracking a particular track. Right? That is tracking a particular track on this platter. Right? Now, what you have to do is this one track, information across this one track is let's say called a track. Right? And let us say this is one block. So usually this can be something like 32 kilobytes. This could be 32 kilobytes. All right. Now what happens is, if you have to read any value within this, then that is very fast. Right? Then that is very fast because your disk is spinning. Right? Your magnetic disk is spinning at 1000 RPM. Right? So within 0.001 second, you can read this entire 32 kilobyte. You can read this entire 32 kilobyte block. Right? But if you have to change blocks, if you have to move from this sector, if you have to move from this track to perhaps this outer track, right? If you have to do that, then what you have to do is you have to move this head. You have to move this read head. So you have to unplug this read head. You have to run the motor to move it back. Then you have to plug it back, right? And that takes some time. So that moving the read head can take a lot of time. It can take, say, let us say 0.1 seconds of time. Right? So that is very, very slow. Is that clear? So it turns out that what really happens is, it could be the case that due to this thing, it could be the case that making comparisons is fast. All right, you read 32 kilobytes of data in the memory, and then once the data is in your RAM, you are making comparisons in the RAM, right? And RAM is very, very fast, very, very fast. On the other hand, making a guess is slow. Making a guess is slow, right? Why? Because for every guess, for making a new guess, you have to change the block. You have to change the hard disk block, right? And you have to move that. You have to move that read head manually, right? Because this is happening at the hard disk level. This is not happening at the RAM level. Okay. So what really happens in this case is, making a guess. I want to reduce the guesses. I want to reduce the number of guesses I make. I don't really care about the number of comparisons I make, because the comparisons are happening in the RAM very, very fast, right? So in this sort of scenario, I would prefer to use some sort of a k research, right? I would prefer to use some sort of a k research, because in a k research, this is the number of comparisons, right? And this is the number of guesses. This is the number of guesses. The larger the value of k is, the lesser my guesses will be. Right? The larger the value of k is, the lesser my guesses will be. So basically, to maximize my efficiency, I choose a k which is equal to the block size. I choose a k which is equal to the block size. Right? And this thing, right? This thing is used all the time in databases. Whenever you are using a database, the database internally is storing the data in some in a thing called a B plus tree, right? In something called a B plus tree, and a B plus tree is simply a binary tree that has been extended from. So binary tree works in a binary search manner, right? On a binary tree, you can have a binary search tree and you can binary search on it. On a B plus tree, you can do a K research. You can do a K research on a B plus tree. All right. How did you come up with this formula? So this formula is what we just saw, right? This formula is what we saw for binary. For binary search, we have one comparison and log base 2n guesses. For ternary search, we have two comparisons and log base 3n guesses. For K research, we have K minus 1 comparisons and log base Kn guesses. All right. Is that clear? This is multiplication. Is that clear, guys? All right. So I think we are going to leave it at this, right? We are already above the time. So today we basically discussed binary search. Binary search. We saw how to implement it, right? We saw how to implement it, and we saw that this idea can be extended into a K research, into a ternary search or a generic K research. K research is generally slower, right? Generally, we would like to do binary search, but there are cases. There are cases, like for example, databases, in which K research is very, very valuable. Okay, cool. Now, I would want each of you to, once this lecture is over, to find the link in the video description, or there's a link to the assignment, right? Today's assignment. So please go over there and try to solve those problems. So those problems will be on basic binary search. There are some things that we were not able to discuss, like binary search on a rotated array, right? Finding the peak element. We can discuss it in the next class. All right. All right, guys. Cool. Will we cover interview bit problems from your website? Yes, Reshma. So all these problems. So that is why we give you the assignments, right? We are discussing the problems that are part of those assignments. Okay. I mean, of course, when we are actually doing a scalar class, when someone joins our academy, we usually have 3-hour classes, right? And we have classes every single day for 3 hours. So that gives us a lot of time to work with the student, right? So they are able to solve many more problems. We won't be able to do that on YouTube, right? So I understand that you won't be able to get the exact same experience as Scalar, but that's to be expected, right? Because this is on YouTube. All right then. So please make sure that you solve the assignment. Please make sure that you are taking notes while you're studying the lecture. And see you in next class. In the next class, I will continue. We will continue with binary search, and we will be looking at more advanced problems on binary search. Okay. Perfect. If you want to join Scalar, well, we don't really announce the dates during lectures. So whenever, if you're trying to join Scalar, just go to scalar.com, right? And any announcement about a new batch, will be made over there, right? So please monitor the scalar.com website, and any announcement about any new upcoming batches will be made over there, right? So let us end the lecture then. All right. Bye-bye, guys. Have a nice day. We are back with another lecture. Today, we are going to continue binary search. We are going to look at some questions that have been asked in companies, in some of the top companies, right, regarding binary search. Now, without further ado, let us start the class. So let me just share my screen. All right. I hope that everyone can see the screen and whatever I'm writing over here. Cool. So let us start with a question directly. So yesterday we had looked at what binary search was and how to implement binary search. Let us dive into one question today. Okay. So suppose that you have been given an array, right? And this array has n integers. All right. Now it has also been told to you that in this array, all elements but one come twice. Come twice. All right. Also, it has been said that the array is sorted. Array is sorted. So let us first take an example of such an array. Let's look at such an example. Let's say that we have 0, 0, we have 4, 4, minus, we have, let's say, 5. All right, we have 5 over here, suppose. Right? Then we have, let's say, something like 7, 7, and we have 8, 8. Right? So in this array, we see that every element has been repeated twice. There are 2 zeros, there are 2 4s, there are 2 7, there are 2 8s, except for one element. Right? Except for one element, every element is repeated twice. Also, this array is sorted. Right? So it is sorted in ascending order. I hope my voice is clear. All right. Cool. Now the question says you have to find this singlet element. Right? You have to find this element which occurs only one time. So if this was the array that was given to you as input, then you are supposed to return 5. Is the question clear? Yes. So we have been given an array. It is sorted. Every element in the array occurs twice, except for one element. And we have to find that one element that occurs only once. All right. So let us see some approaches. Let us see some approaches. So Piyush has a very nice idea over here. Piyush says, let's try XOR. Right now, we all know the property of XOR. We have seen that in the bit manipulation class. That XOR acts like a lock and key. Lock and key. Right? Basically, if I XOR the entire array, that is supposed to give me that element that occurs only once. Right? That element. I'm supposed to get the correct answer because all these things will cancel. Right? 0 XOR 0 will cancel. 4 XOR 4 will cancel. 7 XOR 7 will cancel. 8 XOR 8 will cancel. And I will be left with 5. So yes, that's a valid approach. That is totally a valid approach. What is the time complexity of this? How much time will this take? How much time will this take? This will take order of n time, right? Because we have to go over each element and check, right? We have to XOR each element, all right? Cool enough. Can we do better? In this, using this XOR thing, are we first of all making use of this property? We know that the array is sorted, right? We know that the array is sorted. So either if we use XOR or if we use a map to keep a count, then we are not really using this sorted property, right? They are going over each element. So let us try to make use of this sorted property and see if we can reduce the time complexity. So this is a valid brute force approach. But let us come up with an optimized solution that exploits the property that the array is sorted. Yes, let us see if we have some other approaches. All right. So yes, binary search would be the answer here. But what exactly are you going to do with the binary search? How exactly are you going to search it? All right. So Anurag over here says that let us check the middle element. All right. Let us suppose we have some middle element. And what Anurag is saying is let us compare it with the previous or next element. Right. And then return. Well, let us suppose that this array was a little longer. Right. Let us say that we had 10 over here as well. So when you find the middle element, let me just add the indices. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So what will be the middle element? This will be the middle element. Right. Cool. Now, if this is the middle element, then we compare it with the left and right element. And what exactly do we do? What exactly do we do? So we look at both neighbors. All right. This is 5 and this is 7. So how does that help us? How does that help us? It doesn't really help us, right? Okay. So what can we do then? Yes. So Dipanshu has a nice idea over here. Let me just show Dipanshu's comment. So Dipanshu says that let us observe one thing. That whenever a new element comes, it always comes at an even position. Right? Whenever a new element comes, it always comes at an even position. Yes? Is that correct? until and unless that middle element comes. After that, every new element comes at an odd position. Do you all agree? Yes, the first occurrence of any element is on an even position on the left side of this mid and is on an odd position on the right side of this mid. Do you guys observe that? So we are going to use this property. We are going to use this observation to find out what the single occurrence element is. Right? So suppose that we do something like this. We pick. So we have a high and we have a low. Right? So this is 5 and this is 8. We have a low and we have a high. Right? Let us calculate some mid. Right? What we will do is this mid will be, let us say, A of mid. Right? This A of mid, it might be the first occurrence of this value or it might be the second occurrence of this value. Right? We don't really know. This 7 that we landed on, this could be the first occurrence of 7 or this could be the last occurrence of 7. Right? We don't really know. So what we can do is we can find the first occurrence of 7. Suppose that we landed on this bit. Suppose that we had landed on this bit. Then we can compare it with the previous element and always find the first occurrence. First occurrence of A of mid. Can we do that? Yes. Given a mid number, can we find A of mid and then can we find the first occurrence of A of mid? It will either be that element itself or it will be just the previous element. Right? Cool. Now once we have that, we can check if the index of first occurrence of A of mid, right? If this is even, then what does that mean? That the singlet element lies to the right of me. Right? Whenever I find the first occurrence at an even position, that means that a singlet element lies to the right of me. So I will move right in this case. Right? On the other hand, if this is not the case, if it is odd, then I will move left. Yes. And I will also have to stop at some point. Right? So I can check. If A of mid is the first occurrence, and there's only one occurrence, right? So A of mid plus 1 is not equal to A of mid, then I know that I have found my singlet element because it occurs only once. Does that make sense? Yes. So what will be the very quick pseudocode for this? So we will start with low equals to 0. We will start with high equals to length of, so AR dot length minus 1, right? Then we will loop while low is less than equal to high, right? What will we do? So we will calculate the mid first. So we will say mid equals to low plus high minus low by 2. Yes, we just calculated the mid. Remove the extra string comment, surely. Yes, cool. All right, so we calculate the mid, then we can check. So we will first check. So we know that we have to find the first occurrence of A of mid. Right? How do we find the first occurrence of A of mid? Well, we can check over here. We can check if A of mid minus 1 equals to A of mid. Right? If this is the case, then A of mid is the second occurrence and not the first occurrence. Do you agree? Yes, if A of mid minus 1 is equal to A of mid, then A of mid must be the second occurrence because the previous element is also equal to. In this case, what is the first occurrence? The first occurrence is mid minus 1. Right? In this case, the first occurrence is mid minus 1. Otherwise, the first occurrence is mid itself. Right? All right. So what I can do is over here is I can do mid minus minus. Mid minus minus. And then over here, my mid contains the index of the first occurrence. Now I can check. If mid is even or odd. So if mid is even, mod 2 equals to 0, then I have to move towards my right. Yes, I have to move towards my right. How do I move towards the right? I say low equals to mid plus 1. Right? Otherwise, else I move towards the left. I say low equals to, high equals to mid minus 1. I simply say high equals to mid minus 1, right? Perfect. But that does not really tell me when to stop, right? That does not really tell me when to stop. So I have to make some other checks as well. Also, there is one more problem over here, that what if this mid turned out to be 0? What if this mid turned out to be 0? Then this a of mid minus 1 will give me an index error, right? I will be trying to index at a negative value. That is not good, right? So I have to take care of these things. So first of all, what I can do very quickly over here is I can first confirm this, right? I can first fix this thing. I can say if mid is greater than 0, right? And a of mid minus 1 is equal to a of mid, right? Then do mid minus minus. Then do mid minus minus. So after this point over here at this line, mid will be the first occurrence of a of mid. Right? Mid will be the first occurrence of a of mid. Now if mid is even, we do low plus, we increment the low, else we increment the high. But once again, when do we stop? Once again, when do we stop? So we can check over here. If a of mid plus 1, right? If a of mid plus 1 is actually equal to a of mid, is not equal to a of mid, my bad. So we have the first occurrence of this element, right? We have the first occurrence of this element. And if the next element is not the same, then we have found the correct location, right? Then we have found the correct location. So what I can do over here is, let me just erase this and write it properly. And also we will have to make sure that we check the boundary condition, right? So we will check if mid is less than n minus 1 and a of mid plus 1 is not equal to a of mid, then what do we have? We can just return. We can just return the mid because this is the correct answer. Is that clear? Yes, is the approach clear? So the approach is very simple. The approach is just saying that once you have these elements, all the elements come in pairs, right? All the elements come in pairs. So 0, 1 will come in one pair, then 2, 3, this will be the second pair, then 4, 5, this will be the second pair, until and unless this singlet element comes. Right? This singlet element comes. After that, we will once again have the numbers in pairs. We will once again have the numbers in pairs. So 7, 8 will be there, then 9, 10 will be there, then 11, 12 will be there, 11, 12 will be there, right? Now notice that before this singlet element, every new element occurred at an even index. Right? Every new element occurred at an even index. But after this, every new element occurs at an odd index. Right? So that is just what we are exploiting. All right. Cool. So what will be the time complexity of this approach? What will be the time complexity of this approach? So Abhay says, what if a of mid minus 1 equals to a of mid, then what are we doing with this? Right? So basically what I'm saying is, suppose we landed at this element. Right? Suppose we landed at this element was 7. Right? This and its previous element was 7. So if this is mid, then we are checking if a of mid minus 1, right? Mid minus 1, if that is also the same as 7, if that is also the same as the same element, then move mid to the left. Right? Then do mid minus minus. Right? That will make sure that we are always looking at the first occurrence of an element. Right? Cool. So the complexity of this is just order of log n. Right? Why? Because this is a binary search, and at every time we are splitting the array into half. We are reducing the search space by half. Right? Is that clear? Cool. So this was a fairly easy question. Let us move on to a slightly more difficult question. Okay. But before that, let me just give you a brief thing. So when you are finding a number in an array, right? You usually return some index. Right? You usually return some index. Now, what occurrence is this? Which occurrence is this? Which occurrence is this? Basically, what I'm saying is, suppose that I have a sorted array 0, 1, 2, 2, 2, 2, 2, 3, 4, 5, 6. Right? Suppose that I have this sorted array. Right? So this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, suppose I want to find the value 2. Right? I want to find the value 2 in this array. Right? So when I'm searching for the value 2, the value 2 occurs at more than one indices. Right? It occurs at all these different indices. So what index should my binary search really return? That is the question. Right? So yesterday we saw that okay, we were returning an arbitrary index, right? As long as we found the index, it didn't really matter what occurrence we were looking for. Right? So I mean that is perfectly fine. But usually what you will do is you will try to return either the lower bound. You will try to return either the lower bound, right, which is basically the first occurrence, right, or you will return the upper bound, right, which is the last occurrence. Does that make sense? Yes. What if the array is not present? So lower bound is the first occurrence, right? Or if the element is not present, it is the location. It is the location at which I can insert the element. I should insert the element. Insert the element to keep the array sorted. Yes. Similarly, the upper bound is the last occurrence. Right? Is that clear? Yes or no? All right. Cool. So basically, the question now is that if you have been given this, if you have been given an array like this, and I ask you that given a value 2, you have to return both the first occurrence and the last occurrence of this element, then how will you do that? Right? How will you do that? What if lower bound equals to upper bound? Well, that simply means that the element occurs only once. Right, Reshma? That simply means that the element occurs only once. So suppose that the question is that given this array and this value 2, you have to find both the first occurrence and the last occurrence of this array. So basically, if I give you 2, you have to return 2 and you have to return 6. So if the input is this array into, you have to return 2, 6. Right? So how will we do that? Yes, so this is very simple, right? This is very simple. We just have to make sure that we tweak a little bit on those -1s and +1s. Right? We just have to make sure that we tweak a little bit on those -1s and +1s. Right? So usually what we do is we write the loop like this. So while low is less than equal to high, right? And then what do? We say if array of mid, so we have mid calculation over here, we have something over here. We say if array of mid is less than key, right? If array of mid is less than key, then what do? We do lower bound. We do low equals to mid +1. We do low equals to mid +1, right? Otherwise, else if a of mid is greater than key, then we do high equals to mid -1. Mid -1, right? Otherwise, if it is exactly equal, in the last class we saw that we can just return the mid, right? We can just return the mid because we have found the location. But now we can't just return the mid. Right? Now, if we are looking for the first occurrence, suppose, if we are looking for the first occurrence, can we return the mid arbitrarily? No, because what could happen is when we calculated the mid, suppose we landed at this particular location. Right? We found the two, but we cannot return it, but because this is not the first occurrence. Right? This is not the first occurrence. So how do I ensure that this is the first occurrence? I will have to check over here that first of all, else if mid should either be 0, right? If the mid is equal to 0, then it is my first occurrence, or a of mid -1 should not be equal to a of mid. Should not be equal to a of mid, right? Because if the previous element is equal to the same element, then this mid is not the first occurrence. Does that make sense? Yes or no? All right, that is fair enough. But then what does really happen then? If I write this code, there is a condition remaining, right? There is some condition remaining over here. Yes, there's some else condition remaining over here, right? So what do I really do in that else condition? Well, I have to absorb that else condition. It will have to absorb that else condition somehow. So basically what I need to do is I need to make this thing I need to make this thing less than or equal to key. Oh, sorry, I have to make this thing greater than or equal to key. Right? Basically, if I have found the element, but it is not the first occurrence, then I will still decrease my height. Right? Suppose I found the element over here, but it is not the first occurrence. The first occurrence occurs over here. Then what should I do? I should move left. I should decrease my height. Is that clear? But once again, the moment I do this, something else happens. Right? Another issue arises. What is that issue? That issue is that if I have this condition in my else if, I will never come into the else. Right? I will never come into the else. So what I will have to do is I will have to move this particular condition on the top. Yes, do you guys agree? Do you guys see the problem? Because if I have less than here and if I have greater than equal to here, then I will never go into that else condition, right? These conditions are exhaustive. Yes? So I will have to move this up. So what will my actual code look like now? What will the correct code look like now? For finding the first occurrence, what I have to do is I have to check first of all. If mid is 0, right? If mid is 0, sorry, if a of mid equals to key, right? If I have found the value and either mid is 0 or a of mid minus 1 is not equal to a of mid, right? Only then, if I found the element and it is the first occurrence, only then can I return the mid, right? Only then can I return the mid. Otherwise, so let me just put it over here. Right? Otherwise, if a of mid is less than the key, then I have to move up, right? So I can say low equals to mid plus 1, right? Otherwise, else, I can simply say high equals to mid minus 1, right? And this is what my correct code looks like now. This is what my correct while loop looks like now. And this is for the first occurrence, right? This is for the first occurrence. So this code is incorrect, this code is incorrect, right? And this is the final correct code for the first occurrence. Can you similarly find the last occurrence? Can you similarly find the last occurrence? Yes or no? Yes, you just have to do it the other way around. Right? You just have to do it the other way around. Basically, you have to make sure that a of mid equals to key and mid is equal to either mid is equal to n minus 1 or a of mid plus 1 is not equal to a of mid. Right? That way we find the last occurrence. And when we are finding the last occurrence, this will be less than equal to, and this will not be, this will be less than equal to, right? This will come in less than equal to over here. So that is very simple. It is very simple to find the first and last occurrence of an element in an array. All right. Now suppose that I have an array which is sorted and has size n, and I tell you that given a value x, you have to count the number of occurrences of x in this array. Then what will we do? If we have to count the number of occurrences in this array, then what will we do? Yes? Jay says instead of two binary searches, can we take a while loop both sides and find first and last occurrence? Yes, totally, Jay. We can totally do that. So let us we are going to explore that via this question. Right? We are going to explore that via this question. Suppose that we have this array. Right? Suppose that we have this array. This element is x, 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 and all the way till this location, it's x. Right? Then this is something else. This is y, y. This is a. So if I am supposed to find the count of x's, this is a sorted array. If I'm supposed to find the count of x's, then I have two options. Either I can find the first occurrence, then write a while loop, then write a for loop, right? Till the last location of x. Yes or no? I can find the first occurrence and then I can increment the count one by one. I can go one by one and till I reach the last occurrence of S, and I can do a count plus plus. Right? I can do a count plus plus. If I do it this way, then what will be the time complexity? What will be the time complexity of this way? Well, to find the first occurrence, it will take me order of log n time. But after that, to count each of these values, I will have to count one by one again and again. Right? I will have to count one by one again and again. So it will take me order of n time for the counting. In the worst case, right? What if the entire array was full of the same values? Does that make sense? So in this case, this approach will be linear. This approach will be linear. On the other hand, can I do something better? Can I do something better? Let me just clear the banner. Just give me a second. Yes, can we do something better? Right? So what we can do is we can simply find the last occurrence. We can simply run a binary search to find the last occurrence. Right? This is one binary search. And we can also use another binary search, one more binary search, right, to find the first occurrence. Right? And then we can simply return last occurrence minus the first occurrence. Yes? Is that correct? Plus 1. Exactly. Right? Last occurrence minus first occurrence plus 1. Alright? And that will basically give us the count of that element. Is that clear? Yes? Alright, perfect. Cool. So I hope this is clear, because this is very important. First of all, because whenever you do binary search, you have to understand that you're either going to be finding the last occurrence or the first occurrence. You're not going to be returning any arbitrary occurrence. Also, because in all of the further questions, whenever you are doing binary search, this is going to be very important for us. It is going to be very important for us. So let us look at another question. So suppose that we have been given two sorted arrays. Right? This is a very, very famous question. This question has been asked in all sorts of companies, right? Be it Google, be it Amazon, be it Facebook, be it DirectTime. All the companies have at some point asked these questions, this particular question, and this question is very, very, very frequent, right? And even if you try to search on YouTube, you will find hundreds of videos about this question. So this question is very important. The question is that you have been given two sorted arrays of length n and m respectively, right? So you have been given two sorted arrays. One is of length n, one might be of length m. Right? We don't really know which is larger, which is smaller, and both are sorted. Right? Both are sorted. The question is, we have to find the median of both the arrays combined. Right? We have to find the overall median. Yes. Right. So first of all, let us look at what median is. Right? First of all, let us quickly look at what the median is. So suppose that I give you this particular thing. Suppose that I give you this array 1, 2, 3, 5, 6, 8, 10. Right. Suppose that this is my array, and let me put the indices as well. Right. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Right. So what is the median defined as? What really is the median? So median basically is another term for the middle element. Right? This is a loose definition. This is not the exact definition, but median, you can think of median as the middle element, right, of a particular collection. Now, what do we mean by middle element? If you're talking about a middle element, we should have some sort of order. We should have some sort of ordering, right? Yes. So that is why we are talking about a sorted array. So we are saying if we sort a particular array and then we look at the middle element, so in this case, do I have a middle element? How many elements do I have? I have 9 elements in total, right? I have 9 elements in total from 0 all the way till 8. So what will be my middle element? This will be my middle element. Yes, this will be my middle element. Okay. So basically, this is what a median is. Now, some of you might ask, all right, well, what if the number of elements is even? Right? What if the number of elements is even? So let us say that I add up 20 over here. Right? Now I have 10 elements. Now I have 10 elements, right? This is no longer 9, this is 10 elements now. Now there's no middle element, right? The middle element does not exist now. There are two middle elements. Both this and this are middle elements. Yes. Then what is the median? Well, in that case, median is the average of both of these. So in this case, this is both 5 and 5. So the median is just 5. On the other hand, let us try to change the values. So let us say this is 9, this is 9, and let us say this was 8. Right? If this was 8, then what will the median be? It will be 5 plus 8 by 2, right? Which is 13 by 2, which is 6.5. All right? Is that clear? Cool. So this is what the median is. Now the question says that you have two arrays. You have two arrays. Let us suppose 0, 0, 1, 3, 5, 8. Right? And you have another array. Let us suppose 4, 5, 6, 7, 8, 9, 20, 30. Right? Let us suppose that we have these two arrays. So let me put the indices very quickly. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7. Right? Now the question is not asking you to find the median of each of these arrays. That is not what is being asked. What is being asked is the median of the overall array, right? Of the overall collection. So basically, if I were to take all these elements, consider all these elements and sort them, right? Consider all these elements and sort them, then what will be the median? So what will be the median in this case? What will be the median in this case? If I write both the arrays in sorted form, I have 0, 0, 1, 3, 4, 5, 5, 6, 7, 8, 8, 9, 20, 30. Right? Yes or no? And this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? That's an even number of elements. So the elements, what? The elements 6 and 7. So the median will over here be, the median will be 5.5. Is that clear? Yes or no? Is the question clear? We have been given two arrays and we have to find the overall median of the two arrays. Is the given array sorted? Yes. Both the arrays are individually sorted in ascending order. Right? Both the arrays are individually sorted in ascending order. Right? But I mean, relatively they are not sorted. So it is totally possible that this element is greater than this element. Right? That's totally fine. Okay. There's no relation between the two arrays. It is just that they are individually sorted. Yes. So yes, Shivani has a nice approach over here. Shivani says that let us very quickly merge the two arrays. So where did our comment go? Yes. So Shivani says over here that what we can do is we can merge the two arrays. So when you were doing the merge sort class, you read this merge algorithm, right? Merge algorithm. What did this merge algorithm do? Given two sorted arrays, it created a sorted array. Yes. And how much time did it take? How much time did this merge algorithm take? So if I have total of n plus m elements, if I have n plus m elements, then usually if I just do sorting, right? If I just do sorting in a naive way, then how much time will sorting take me? It will take me n plus m log of n plus m, right? This is how much time sorting will take me. However, if I use the merge algorithm, given that both the arrays are sorted, then I can do it in order of n plus m time. Yes, I can merge the arrays in order of n plus m time. Once I have merged both the arrays, then I can very quickly find the median. Yes, I can very quickly find the median. Right? Find the median. How much time will it take me? If I have merged both these arrays, how much time will it take me to find the median? So suppose that I have merged both the arrays. After that, how much time is it going to take me to find the median? So is it going to take us order of log n time? No, right? So finding a median is just order of 1. You just have to look at a of mid. Right? You just have to look at a of mid. If the number of elements is even, you just have to look at a of mid and a of mid plus 1. Right? So finding the median takes just order of 1 time, provided that I already have a sorted array. Overall, if I do this merge thing, my overall complexity will be order of n plus m to merge the two arrays plus 1 to find the median. Right? To find the median, which is just order of n plus m. Is that clear? Order of n plus n. Well, that is fine. That is good. That is certainly better than the naive approach. Right? So this was the naive approach. So this is certainly better. But we can still do better. So this is not the best approach that we can use. So can we still optimize? Can we come up with an optimized approach now? What other approaches we have? So Ratnesh has a very, very nice question over here. Ratnesh says, can't we just use the median of medians? Median of medians, right? What does Ratnesh mean over here? Let us suppose that we consider these two arrays, right? Let us consider these two arrays separately. What is the median of the first element of the first array? So this is the first array. What is the median of the first array only? So this array has 6 elements. So the median will be what? So 0, 1, 2, 3, 4, 5, right? It has 6 elements. So the median will be at what index? No. So what Rakesh is telling us is that let us try to find the median of medians. Right? Let us try to find the median of medians. So first of all, let us consider this particular array, A1. Right? This particular array has how many elements? It has 6 elements from this location to this location. So what will be the median of this particular array? It will be the sum of these two. It will be the average of these two, right? It will be 1 plus 3 by 2, which will just be 2. Right? Similarly, let us calculate the median of this array. Let us calculate the median of this array. Well, how many elements does this array have? This has 8 elements, right? And what is the median of this element or this array? That will be this 3 plus 4, right? This element at 3 and element at 4. So that is 7 plus 8 by 2, which is 7.5, right? Now, Ratnesh is saying, once we have these two medians, can't the final answer simply be the average? Can't the final answer simply be the average of these two? 2 plus 7.5 by 2? Well, no, that is not going to be always true. Right? That is not going to always be true. Is that clear, Ratnesh? Over here, we see that this does not really work. This is 9.5 by 2, which is 4.75. Right? And that is not the answer. The correct answer is 5.5 over here. So it doesn't really work. All right. So let me just remove Ratnesh's comment. So median of medians will not work over here. So we have to do something else. Yes. So what approach can we use? What approach can we use? So now we have to do some sort of a binary search. Right? We can use some sort of a binary search to optimize the solution. Right? So what we are going to basically do is we are going to binary search. There are multiple ways of doing this. Right? We are going to binary search on the index only of. We are going to binary search over the smaller array. Right? So first of all, suppose that this is A1. Suppose that this is A2. Right? So can I assume without loss of generality that A1 is smaller than A2? Can I assume that the length of A1 is smaller than length of A2? Yes. If that is not the case, then I can just swap those arrays. Right? I can call this A1 and this A2 if that is not the case. Right? So let us assume that A1 is the smaller array. So what we are going to do is we are going to binary search in this smaller array. All right. So we will have some low, we will have some high, and we will calculate a mid. All right. Now, once we have this mid, the question is, when will A1 of mid be the correct median, be the answer? What has to be true? What has to be true for A1 of mid to be the correct median? What has to be true? If A of mid is the correct median, then how many elements in A1, are less than mid, A of mid? How many elements in A1 are less than A1 of mid? When all these elements are less than A1 of mid? Yes or no? Do you agree? And how many elements are greater than this? Well, all these elements are greater than it. Yes. If A1 of mid is actually the median, right? Then what must be true? What must be true? then half of the elements, right, across both the arrays, half of the elements must be less than it and half of the elements must be greater than it. Yes, half of the elements must be less than it and half of the elements must be greater than it. Cool. So let us check. Let us quickly check. So if A1 of mid is actually the median, then how many elements in A2 should be, or if this is the case, if is actually the median, then how many elements in A2 should be less than A1 of mid? Right, that is the question. Right, so we know that in A1 there are mid minus 1 elements. Oh, there are mid elements, mid number of elements. So the count of elements in A1 that are less than mid is mid. Right? So the total number of elements that have to be less than A of mid. The total number of elements that has to be less than A of mid should be n plus m by 2. Yes or no? Should be n plus m or plus 1 by 2 actually. Do you guys agree? If I have this total sorted array, and this is actually the median, then half the elements will be less than it and half the elements must be greater than it. So if this many elements are less than it overall, right? And out of these, this many elements were already present in A1. This many elements were already present in A1. Then what is the number of elements that are present in A2 which are smaller than this A of mid? So this many elements were already present in A1. So this must be the number of elements. This must be the number of elements in A2. Number of elements in A2 that are less than mid. A of mid. Yes? Does that make sense? How can you say that length of A1 is equal to mid? No. We are not saying that the length of A1 equals to mid. We are not saying that. We are saying that assume that mid is the correct median. Assume that mid is the correct median. For that to be true, if there are these many elements that are less than it in A1, then how many elements should be less than it in A2? And this is the answer. This is the answer. These many elements should be less than mid in A2. So what we can actually do is, we can start with some low over here. We can start with some high over here, and we can calculate a mid. Now what we can do is, we can put a marker at n plus m plus 1 by 2 minus mid. Right? We can look at this particular index. Right? We will have 4 elements now. We will have 4 elements. We will have one over here, one over here, one element over here, one element over here. Right? So let us call these elements A, B, C, D. Let us call these elements A, B, C, D. A, B, C, D. Right? Now, when is this A of mid? When am I at the correct position? I am at the correct position when A is less than D and B and C is less than B. Right? If this is the case, then this marker, these two markers, they point to my median. Do they not? Yes. Do they not point to the median? Why do they point to the median? Because the number of elements over here and the number of elements over here is equal. Do you guys agree? The number of blue elements is equal to the number of green elements. Yes, and how are they equal? Because I have chosen to be. Right? Because I have used this formula to make sure that I land at the correct spot over here. Does that make sense? Cool. So, guys, if this is not clear to you at the moment, we will make sure to basically explain this with an example. Okay. So we will look at a concrete example. But let me first explain the idea. Right? So basically, what we have to do is we have to binary search for a mid such that the property of the median, this property of the median becomes valid. Right. Now look at a concrete example. Let us look at a concrete example to further establish this. Right? Suppose that we have this array 0, 1, 1, 3, 5, 7. All right, and we have another array. Suppose 4, 5, 6, 8, 8, 12, 20, 30. All right, and let us mark the indices 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7. All right. Now, which one is A1 and which one is A2? Which one is the smaller array? This is the smaller array and this is the larger array. Yes. This is the smaller array and this is the larger array. So let us have 2 pointers. Let us have the low pointer and let us have the high pointer. Yes, let us have the low pointer. Let us have the high pointer. Also, what is the value of n? The value of n over here is 6. And what is the value of m? The value of m is 8. Yes, there are 6 elements in the A1 array and there are 8 elements in the A2 array. Yes or no? Cool. So now we have this low and high. What will be the mid? What will be the mid? Mid will be 5 by 2, which will be 2. Yes, mid will be 5 by 2, which will be 2. So this is the midpoint. This is the midpoint. Alright. And A1 of mid equals to what? It is 1. Right? Now the question is, how many elements in A1 are less than or equal to A1 of mid? How many elements in A1 are less than or equal to A1 of mid? Well, these many elements, right? This element and this element. Yes, there are 2 elements that are less than or equal to A1 of mid. What is the count of that? Well, the count is simply mid. Right? Mid is the count. Do you agree? Right. Now, if this one was actually the median, then how many elements should in this array should be less than 1? Right? In this array, how many elements should be less than 1? Well, total there are 14 elements. Right? Total there are 14 elements. So if there is my median, then half of the elements must be less than it, half of the elements must be greater than it. Right? So basically what I'm saying is 7 elements should be less than or equal to it, 7 elements should be greater than or equal to it. Right? That is the property of my median. Right? Yes or no? Cool. So basically, if this is the case, and 2 of these 7 elements come from A1, right? 2 of the lesser elements come from A1, then how many lesser elements should come from A2? How many of the lesser elements should come from A2? Well, 2 are from A1, so 5 must be from A2. Right? 5 must be from A2. So all these elements should be less than 1. It should be less than this 1. If 1 was the median, then all these elements should be less than 1. Are they less than 1? Are they really less than 1? Yes or no? They are not less than 1, right? So 1 cannot be the median. Does that make sense? Because all these elements, they are not less than 1. So 1 cannot be the median. So my median is too small. In that case, I have to increase my load. Right? I will try to find the median on the right hand side. Is that clear? Is that clear, guys? Yes. So basically what we are saying is that let us say that we are going to have a low and we are going to have a high, and we are going to calculate the mid as low plus high by 2. Right? Now, how many elements are less than mid, A of mid in the first array? Well, that is just mid. So how many elements should be less than it in the second array? How many elements should be less than it in the second array? That should be what? That should be n plus m plus 1 by 2 minus mid. Yes, that should be n plus m plus 1 by 2 minus mid. Right? So what we can now do is, so this is the partition. This is basically the partition of A2. Right? Now we can simply check. Now we have 4 elements. We have A1 of mid. We have A1 of mid plus 1. Right? And we have A2 of partition. And we have A2 of partition plus 1. Right? Is that clear? And we can check if this element is less than this element and this element is less than this element, then our partition is valid and we have the correct midpoint. Right? Then our partition is valid and we have the correct midpoint. All right. Why n plus m? Why this plus 1 thing? Well, this is just to make sure that the number of elements that are on the left are greater than or equal to the number of elements on the right. Right? That is just to make sure that the number of elements on the left are either equal to the number of elements on the right, or they are one more than the number of elements on the right. Okay. So if the number of elements is even, then there will be a mismatch, right? You can't have both the same number of elements on both left and right. So we will have one extra element on the left. Is that clear, guys? Just give me a second. let us look at some code for this. Right? Let us look at some code for this. So what will really happen is, let us suppose that we have two arrays. So we have find median, and we have two arrays. We have A1 and we have A2. Right? Let us call this A and B. Let us call this the array A and the array B. All right, for simplicity. Now what we are going to do is, we are going to make sure that array A is smaller. We are going to make sure that array A is smaller. How can we make sure that array A is smaller? How can we make sure that array A is smaller? Well, we can declare it over here, right? So we can say, if the length of A dot length is greater than B dot length, right? If it is in fact larger, then simply swap the values of A and B. Right? So this will ensure that that this particular array is smaller. Right? And notice that this swap is just swapping the pointers. This is just swapping the pointer. This is not actually moving the arrays. This is just swapping the pointers. All right. So now that we have ensured that A is the smaller element, so now what we can do is, we can have a low and we can have a high. Right. So we can say that, all right, low, we can initialize low equals to 0, and we can initialize high equals to what? So what array are we searching over? We are searching over the smaller array. We are searching over the smaller array. So we will say high equals to A dot length. Right? A dot length, right? And basically, let me also do one thing. Let me also save two values over here, n and m. So let me say, for simplicity, let me say that n equals to A dot length and m equals to B dot length. B dot length. Right? So we have saved the length or the length in nm. So now my low will be 0 and my high will simply be n. All right. Now I can loop. While my low is less than or equal to the high. Right. Now what is the first thing that I should do? The first thing that I should do is I should calculate the mid. Right? I should calculate the mid. And what is the mid? The mid is simply low plus high minus low by 2. Right? Cool. Now this mid is a marker in the first array. This mid is a marker in the first array. What will be my corresponding marker in the second array? As we just saw, that corresponding marker, that is called this partition. Right? This is called this partition. This is going to be n plus m plus 1 by 2 minus mid. Right? Is this clear to everyone? Is this clear to everyone? That this will be the partition? Cool. Now what we are going to do is, we are simply going to compare values. Right? We are simply going to compare values. We are going to say that if, okay, we are going to say if A of mid, right? If A of mid is less than or equal to B of partition plus 1. Right? If A of mid is less than or equal to B of partition plus 1, and A of mid plus 1, or basically I can write it the other way. I can write B of partition is less than A of mid plus 1. Right? If this is the case, then what do we have? What do we have? We have two arrays. We have two arrays such that this element is smaller than this element, right? And this element is smaller than this element, right? So A is less than B and C is less than D, right? And we know that the number of elements over here is equal to the number of elements over here, right? If this is the case, then I have found my median. Right? So I have found my median over here. So I have found the correct midpoint, right? And I will actually return the median over here. So we will have two cases over there as well. We will look at that. But if that is not the case, then some other case will arise. Right? Then some other case will arise. What case can arise? So either it can be that A is actually greater than B. Right? It can be that A is greater than B, or it could be that C is greater than D. Yes or no? If A is in fact greater than B, let us suppose that I have something like 5 over here and 7 over here, right? And I have something like or let's say 12 over here, and sorry, not 12. Let us say 1 over here and 3 over here, right? So if this element is greater than this 3, then what does that mean? If this element happens to be greater than this 3, then what does that mean? It means that my midpoint is too high. This midpoint is too high, right? I have to move left. Is that clear? Similarly, if that's the opposite thing, right? If I have 5 and 7 over here, right? If I have, let's say, 12 and 15 over here, right? So if this element is greater than this element, right, then my mid should be on the right. Right? This value 7 over here, this is too low. So I should move to the right. Right? So that is what we are going to do over here. We are going to say else if A of mid is greater than B of partition plus 1, then I have to increase my mid. Right? So I have to decrease my mid. Right? So I will say high equals to mid minus 1. Right? Otherwise, I will say low equals to mid plus 1. Alright, so this is the main while loop. Now, there are some more conditions that arise. Those conditions are basically, let us take one more example. Let us suppose that we have this particular array and we have this particular array. Right? Alright. Now, we have two conditions. Either the combined length n plus m, either this is even, or n plus m, this is odd. Right? Either this is even or this is odd. If the length is odd, then what will be my median? If the length is odd, then what will be my median? This is A, B, C, D, right? We know the number of elements over here. So the number of blue elements is either equal to number of green elements, or it is equal to green elements plus 1. Right? It is either equal to it or one more time. Right? So if I found the correct midpoint over here, then what can I say about the median? The median has to be one of these two things. Right? The median has to be one of these two things. Yes or no? Yes or no, guys? And which one of these is the median going to be? Is it going to be A or C? Well, it is going to be the maximum of A comma C. Yes, the median over here is going to be the maximum of A comma C. On the other hand, if the number of elements are even, then what do I have? Well, in that case, what do I have? I have the max of, I want to find the maximum value on the left, right? I want to find the maximum value on the left. So max of A comma C, and I want to find the minimum value on the right. Right? So a min of B comma D, and I want to take the average of those because the median will be average of two different values over here. Right? I want to take the average of those. Is that clear? Cool. So basically, what do I have to write over here? I have to check if n plus m mod 2, right? If n plus m mod 2 equals to 0, if it is even, then I have to return basically A of max. So basically I have to return max of A of mid comma B of partition, right? The max of these two plus the minimum of A of mid plus 1 comma B of partition minus 1, right? And I have to take the average of these two. So I will add these two up and I will divide by 2. Right? That's a very long line, but I hope that it makes sense. Right? That is the case when my number of elements is even. On the other hand, if the number of elements is odd, then this is very simple. Right? I simply return. So I can simply return over here the max of A of mid and B of partition. All right, we can simply return the max of A of mid or B of partition. So this will basically be the code for finding the median of two arrays. Now there's one bug over here. Can someone catch that bug? This code is not entirely correct. there is one very crucial bug over here. And that bug is basically, let us suppose that I was searching in this array and I was searching in this array. Right? Suppose that while searching this array, either my midpoint became n minus 1, or if my midpoint became 0. Right? Then what do I compare? I don't have anything to compare. Right? If my midpoint is this thing, n minus 1, then I can't compare a of mid plus 1 with anything, right? I can't really compare a of mid plus 1 with anything. Yes or no? So for that, to handle that, we can very simply, we can virtually append infinity and minus infinity to the left and right of both the arrays. All right? Yes, exactly. So Jay, even in that case, if the first array is only of size 1, so we will very quickly exhaust the mid. Right? We will very quickly exhaust the mid. So to handle that situation, to handle that boundary case, we need to add infinity and minus infinity on the right and left side of both the arrays. All right? You don't have to actually append it. You can treat it virtually. Right? You can treat it virtually. Is that clear? Yes, आज कुछ ज़्यादा हो गया. Well, I mean, I would recommend that you actually try and code this up. When you try and code this up, this will, so I understand that you won't be able to, you will have to get practice on this. You will have to actually try and code this up to properly understand this. Right? But I hope that the intuition was clear. The code might not be clear to you, but I hope that the intuition was clear. Right? Cool. So now what will be the time complexity of this overall algorithm? What will be the time complexity of this overall algorithm? Yes. So we are doing a binary search, right? We are doing a binary search over what? We are doing a binary search over the smaller array. Right? We are doing a binary search over the smaller array. So what will be the time complexity? It will be order of min. So it will be order of log of min of n comma n. All right. It will be order of log of min of n comma n. Is that clear? Yes, Himadari, there are a lot of edge cases over here. So we always have to take care of the edge cases. I mean, the solution is very elegant, but the code only becomes difficult because of all the edge cases that you have to handle. All right. Tushar says, how are the corner cases rectified? The corner cases can be rectified by just adding a minus infinity to the left of both the arrays and a plus infinity to the right of both the arrays. All right. Basically, you can say that you have 4 values over here, right? You have 4 values over here. You have A, B, and you have C, D. You have these 4 values over here. Well, what if this midpoint was equal to n minus 1? In that case, if that is the case, then there is no A of mid plus 1, right? There is no A of mid plus 1. So what value should you consider instead of B? There is no B. B does not exist, right? So what value should you consider instead of B? You should consider infinity. Similarly, this value over here, if this is partition and this is partition plus 1, right? If there is no D element over here, then you should consider infinity in its place. Similarly, on the left hand side, if mid is 0, then on the left hand side you should consider minus infinity, and same for partition. Is that clear? So once you actually try to code this, things will start making sense. I don't want to give you the exact code right now, because then it will defeat the purpose of us trying to solve these questions. Right? You actually have to code this yourself, struggle a little with the edge cases, and once you figure this out, things will become clear. All right. Cool. So let us move on then to the next question. Right? So the question goes something like this. That we have an unsorted array. Right? Of size n. All right? And this array only has positive integers. Right? We have an unsorted array of size n, and this array only has positive integers. Now we have been given a value. X, right? And we have to find the largest value of k. The largest value of k, such that no sub array of length k has sum greater than or equal to x, or let us say just sum greater than x. Right? So that's a mouthful. Basically, what we are saying is, suppose that we have some array with some elements. Right? We have some array with some elements, and we have been given a number x equals to 10. Right? Let me also give this array. So this is 1, 5, 6, 2, 0, 1, 3, 5. All right. Let us say this is my array, and I have been given some x equals to, let us make this a little smaller, perhaps x equals to 6. Right? Now we have to find the largest window size. Right? K is the window size. We have to find the largest window size such that in that window there is no window that sums up to greater than 6. Right? There is no window that sums up to greater than 6. So in this case, what will be the answer? In this case, what will be the answer? Is the question clear? So if I make a window of size 1, this or this or this or this or this or this, then is the sum ever going to be greater than 6? Is the sum ever going to be greater than 6 if I have a window of size 1? No, right? So window of size 1 is valid. Right? Window of size 1 is valid. Size 1 is valid. Right? On the other hand, if I have windows of size 2, let us say this window, right? What is the sum of this window? The sum of this window is 6. Right? So 6 is okay. What is the sum of the next window? 5 plus 6. The sum of this is 11. Well, 11 is greater than 6. Right? 11 is greater than 6. So this window is not okay. And because this window is not okay, the window of size 2 is not valid. Right? Windows of size 2 are not valid. Is that clear? Okay. So we know that a window of size 2 will give me a sum greater than 6. So should I try a window of size 3 or above? Should I try a window of size 3, size 4, size 5? Yes or no? I should not try them, right? There is no point in trying them. Does everyone agree? Yes, because we have to find the largest window such that the sum of any subarray of that size must be less than or equal to this summation value over here. Right? Let us take another example, perhaps. So let us take one more array. So suppose this array is 1, 0, 3, 6, 4, 2, 7, 0. Right? And let us say that x equals to 13. Right? Let us say that x equals to 13. Okay. Now, what is the largest window? What is the largest value of k such that no window of size k has sum greater than 13? Right? So does k equals to 1 work? If I have windows of size 1, then is the sum going to be greater than 13? No, right? So windows of size 1, they all have sum less than 13. Right? So windows of size 1 are valid. Right? Every window of size 1 is valid. So size 1 is valid. This is valid. All right. What about windows of size 2? Well, this has a sum of 1. This has a sum of 3. This has a sum of 9. This has a sum of 10. This is 6. This is 9. This is 7. Right? All the sums were less than or equal to 13. So windows of size 2 are also valid. All right. Let us try increasing the window size further. K equals to 3. All right. Now, what do my windows look like now? My windows are, so this is my first window. Right? What is the sum of this? It is 4. Then this is the second window with sum 9. This is the third window. Right? This has sum 13. This is the fourth window. This has sum 12. This is the fifth window. What is the sum of this fifth window? This is still 13. This is the last window. This has sum 9. Right? So still we see that window of size 3 is also valid. Is that clear? Window of size 3 is also valid. All right, let us try to increase it further. So let us try k equals to 4. All right, now what is the size of what is the sum of this? That is 10. What is the sum of this? That is 15. Right, the sum of this particular window is 15, and 15 is already greater than 13. 15 is already greater than 13. So windows of size 4 are not valid. Is that clear? And because windows of size 4 are not valid, windows of size 5, windows of size 6 will also not be valid. Right? All these will not be valid. Is that clear? Yes, is that clear? So if this is my array, if this is the input array, and this is the value of x that has been given to you, then what value of k should you return? What value of k should we return? We should return k equals to 3. Right? We should return k equals to 3 because we have to return the largest size of window, so that no window of that size has sum greater than x. Is the question now clear? Yes, is the question now clear? All right. So how can we approach this particular question? So guys, whenever you come across a new question, don't try to come up with the optimized approach right away. Right? Come up with the most brute force approach. Right? First, try to solve the question. Once you have solved the question, then you can try to optimize it. Right? Because some solution that works but is slow, some solution is always better than a fast solution that you never find. Right? So having some solution at least is better. Right? So let's think of a brute force approach first. Yes. So what can we do? All right. So let us look at two questions. Suppose I have a guess. Right? Suppose I have a guess for k. Right? Suppose I say that k equals to, let's say, 5. Right? Suppose I have this array and I have been given a value of x, let's say 20, and I am guessing that k equals to 5. Then how can I verify? How can I check it? How can I check it? I have to consider every possible window of size 5. So how can I do that? I can either do two nested loops. So I can either say for I equals to 0 all the way till n minus 5 minus 1, right? For j equals to 0 till 5 minus 1, right? And then I can say sum plus equals to a of j, a of I plus j, right? And initially sum equals to 0, right? So doing this, what will this do? This will give me, so only, sorry, over here. I will have to say sum equals to 0 over here. So basically, after this inner loop, in each iteration of this inner loop, I will have the sum of one window. Right? I will have the sum of one window again and again. So I will have to check if sum is greater than x, then return that window size is invalid, right? K is invalid. Right? After this entire thing is complete, I can say that k is valid. Right? So given a window size k, this is how I can check it. Yes or no? That seems like a very, very difficult approach to do, right? So can we simplify this a little bit? How can we do that? So are you guys aware of prefix sum? Suppose that this is my array. And I want to find the sum from some start location to some end location. Right? If I want to do many queries of such form that find the sum of all these different elements, then how can I do that efficiently? I can calculate the prefix sum of the array. Right? Let us say that this is the array A, then the prefix sum of array A will be P of A. Yes. Now, if I were to tell you to calculate A of I plus A of I plus 1 or plus A of I plus 2 plus all the way till A of j, then how can you express this in the form of prefix sum? Well, this is simply equal to what? P of j minus P of I minus 1. Yes or no? Is that clear? Yes or no, guys? Alternatively, you can also rewrite this as P of j minus P of I plus A of I. Right? You can also rewrite this as this. They are the same thing. All right. So once I have this prefix sum, if I tell you that find me the size of window of size 5 starting from this location I. Right? If I ask you to find the sum of this window, then how can you do that? How can you do that? You can very simply do what? You can simply do prefix sum of I plus k minus prefix sum of I minus 1. Yes or no? This will give you the sum of this window. Right? And to go over the sum, to go over all possible windows, you can just write a loop for I equals to 0 all the way till n. Right? N minus k basically. Yes? So that is the first thing that we can do to make our sliding window calculation a little simpler. Right? We can store the prefix sum. But the thing still comes that, all right, given a value of k, I can check if it is correct or not. But how do I find the value of k? Currently, the approach that I have is start from k equals to 1 and try increasing it. Right? Try increasing it one by one. Right? If I do that, then what will be my time complexity? I will have a loop for k. This will run for order of n time. Right? Then I will have a loop for checking k. This will also run order of n time. So my total time complexity will be order of n squared. Yes. Of course, I also have to consider the complexity of the prefix sum. But calculating the prefix sum is just order of n pre-computation. Right? Pre-computation. So this is actually order of n squared plus n, which is just order of n squared. Right? This is my naive. This is my brute force algorithm. All right. Can we improve this? So Teju says that we can use binary search, right? But what should we binary search over? Teju, what should we really binary search over? Yes, so Prakash says that we can binary search for the value of k. So we are going to binary search for the value of k itself, right? So what is the minimum possible value of k? What is the minimum possible value of k? What is that? What is the minimum possible value of k, guys? It is 0, right? It is 0. Basically, if some a of I itself is greater than x, then I can't have a window even of size 1. Right? In that case, the value of k will be 0. On the other hand, what is the maximum possible value of k? That is n. Right? If I take if the sum of the entire array is still less than x, then that is the maximum possible value of k. So what I have to do is I have to binary search in this search space. So I can say low equals to 0, high equals to n, while low is less than equal to high, right? I will say mid equals to low plus high by 2, right? All right. Now, once I have the mid, what should I do? I should check window of size mid. All right. I should check window of size mid, and I will have another function over here. Check window, right? That takes a value of k and returns true or false. Right? This check window is going to do exactly this. So it is going to loop. It is going to say for I equals to 0 all the way till n minus k, right? If the prefix sum of I plus k minus prefix sum of I minus 1, right? If this is greater than x, if any of this sums is greater than x, then return false. Right? Otherwise, return true. Right? If all these windows are valid, then return true. Right? This is the check window functionality. Is that clear, guys? Cool. So we have a function for check window now. So what can we see over here? So if I check window of mid and this comes out to be true, if check window of mid comes out to be true, then what can I say? If a window of size k works, then can I return this? if a window of size k works, then can I return that window size as the final answer? Yes or no? No, I cannot. Because yes, this works, but this might not be the largest value that works. I have to find the largest value that works. Right? So if this is the case, then I have to increase my low. So I will say low equals to mid plus 1. Right? Mid plus 1. On the other hand, if this does not work, then I have to decrease my value of k. Right? So else, I will say high equals to mid minus 1. Right? High equals to mid minus 1. Well, when do we stop? When do we stop? So we can either stop when this loop exits, or we can explicitly check. We can explicitly check that k works, but k plus 1 does not work. Right? If that is the case, then we can simply return. Is that clear? Even if we don't do that, that is fine, because this loop will automatically take care of it. Is that clear? So we will return when we find a position of k which works, but the immediate higher position, right? K works, but k plus 1 does not work. That will be our correct answer. Is that clear, guys? So after this loop, after this while loop is over, I can simply return what? What can I return? So this will exit when low will become greater than high. Right? Low will become greater than high. How will it become greater than high? When I would just do low equals to mid plus 1. Okay, so I can just return low over here. Right? I can just return low over here, and that will be my size of the window. All right, cool. So what will be the overall time complexity of this algorithm? What will be the overall time complexity of this algorithm? So let us take this step by step. How much time does check window take? How much time does one function call to check window take? This is simply a for loop. Right? This takes order of n time per call. Right? This takes order of n time per call. Well, what about this thing? This is log n search. Right? This is log n search. But inside this log n search, we are doing this order of n call every time. Right? Inside this log n search, we are doing this order of n call every time. So basically, the time complexity will be order of n times log of n. Yes, order of n times log of n. Well, we also have to consider the prefix something. So this is for the prefix sum. This is for the binary search. Oh, sorry. This is for the binary search, this log n thing. This is for the binary search. And this is for check window. Right? So the overall time complexity is just order of n log n. Is that clear? All right. So let us end the class at this point. Bye-bye. Have a good day. Hello, everyone. So we are back again with another class. All right. So today's topic is once again binary search. So we have been studying binary search in the past 2 lectures. Right. So if you have not watched those past 2 lectures, please go and watch them. So let us continue with some more advanced problems on binary search today. All right. Let me just share my screen. I hope that everyone can see the screen. All right. So let us start with a question that you might have seen earlier. Right. It is a pretty famous question. And you might have seen this in the arrays, 2D arrays class that we already had. Right. But this question is relevant to binary search. So let us quickly see it here once again. Question goes something like this. You have been given a matrix. I mean, this is not that matrix movie thing. This is a matrix. It's a 2D array, right? Now, this matrix can have a certain size. Let us say that the size is n cross m, right? Now, this one property in this matrix that each row and each column is sorted, right? So let us quickly take an example of what such one such matrix would look like. So suppose we have 10 over here, 20, 30, 40, 50, right? All right. What other numbers can we choose? So let us suppose that we have 15, 25 perhaps, 35, 45, 55. Something else, maybe 27, right? 29, 37, let us say 48, and let us say 60, right? So let us just add quickly one more row. So suppose this is 32, and suppose this is 40, suppose this is 51, suppose this is 60, and suppose this is also 60, right? So we see that in this matrix, every row individually is sorted, right? Every row individually is sorted, and so is every column. So is every column, right? Cool. All right. Now, what is the size of this particular matrix? Well, over here we have 4 rows, so n equals to 4, and m equals to, we have 5 columns, so m equals to 5. So this is a 4 cross 5 matrix, right? Now we have been given an integer. We have also been given an integer k. Right? So k stands for key. We have been given a key, and we have to search this key. We have to search this key within the matrix, and we have to return. We have to basically tell whether the key exists or not. Key exists or not. Fair enough? Yes? All right. So Rahul has a question over here. Rahul, I guess, is talking about the assignments that were given in the last class. Rahul says that 5 questions in 24 hours is kind of aggressive. Right? So Rahul, you do not have to attempt those questions in 24 hours. Right? So unlike when you are enrolled in SCALER Academy, you will have a lot of guidance. You will have mentors. You will have TAs that will be helping you while you're working through the assignments. Right? We will have remedial classes a lot. When we are on YouTube, we just want to give you as many assignments as we can so that you can practice on your own time. Right? So it could be the case that yesterday, after taking the class, you were able to solve 2 of the problems. Now, maybe 5 days later or 10 days later, you want to come back and try it again. Right? So we just want to make sure that you have some new problems that you can still attempt. All right? So do not worry about the time constraint. This assignment is not timed. Right? So feel free to take this assignment whenever you want, how many times you want. So it doesn't really matter. Okay. Just the assignment is just to make sure that you can practice a lot. Perfect. So yes, Shazia is saying that this question has been done in the previous class. So we are going to very quickly move through this question. All right. But this is kind of important for binary search as well. So as you guys already know that this is binary search question. So let us just quickly recap this. All right. Perfect. So this is the question. You have been given a matrix of size n cross n. Each row and each column is individually sorted. Given a key, we have to find whether this key exists in this matrix or not. Yes. Perfect. So what approach do we have? Well, one of the brute force approaches. So whenever we have a new problem, we try to come up with a brute force approach. Brute force approach, right? In a brute force approach, we will not be using any extra information that we are given, right? So what will be the brute force approach? We simply try to linearly, so linear search. If we search through the entire matrix in a linear manner, then how much time is it going to take? What will be the time complexity? Well, how many elements are there? There are total n cross m elements. We are doing a linear search, so it will be the complexity, the amount of time it will take us for linear search will be order of n cross m. All right, but we can optimize, right? We know that each row and each column is individually sorted. Interesting. Well, let us just worry about the rows for now. Let us just worry about the rows for now. So we know that because each row is sorted, we can binary search. Inside each row. Is that correct? So if we binary search, let us call this binary search 1. If we binary search inside each row, then how much time is it going to take us for every row? Well, there are m elements. There are m elements in a row, right? There are n rows and there are m columns. So every row has m different elements. So if we want to binary search among m elements, it will take us log of m time. Right? This is for one row. Now we have to do this for all the rows. How many rows are there? N different rows. So it will take us order of n times log m time. Yes, do you guys agree? On the other hand, if we basically, so this is on the rows. If we binary search number 2 on the columns, right? then it will be very simple. So it will be m times log of n, because now we are searching within each row, right? We are searching within each column. And how many elements are there in a column? Well, equal to the number of rows. So we can search through a column in log n time, and we have m columns to search through, right? So if we search through just the rows, we will get this complexity. If we search through just the columns, we will get this complexity. The question is, can we do better, right? Now, this might not be obvious from the question itself. We have already tried binary searches, right? We have already tried binary searches, but binary search is not always about this binary property. So just because you are saying binary, that does not mean you always have to split the array into half, right? That is originally what binary search means. But binary search has a more important concept, more important underlying concept. And the concept, as we discussed in the previous classes, is what? The concept is that given a search space, when you make a guess, you are able to eliminate a large part of that search space, right? So every guess allows you to eliminate a large chunk of the search space. Perfect. All right. So that's fair enough. So how can we basically do that? How can we basically do that for this particular question? Well, we can observe. Let us suppose that we are looking at this particular element. Let us just pick any random element, and let us say that we are looking at this particular element, right? Then, if we determine that given our key, right? Let's say that we compare this key with 45. Suppose that the key is less than 45. Right? Suppose that we are looking for an element like 29. 29 is less than 45. Right? Then what can we know from here? This key was less than 45. So can this key be over here? Can this key be in this area? No, right? This key cannot be in this area. Why? Why can it not be in this area? In fact, this particular area, because this key is less than 45, and everything in this area, everything over here in this area is already greater than 45, right? So the key cannot be over here. Similarly, so I can reduce my search space, right? I can reduce my search space by a large chunk. This might be a large chunk. Now there's one more property that we get. If we move in a particular order, right? Suppose that we are starting from the top right, then we can also eliminate some more rows or some more columns. Right? So we will see that we will be able to eliminate this top row as well. Right? So over here, there's nothing binary over here. Right? We are not really splitting the search space into half. However, what we are able to do is we are still able to eliminate a large chunk of the search space with every guess. Yes, so Dev has a nice name over here. Dev is saying that we can call this staircase search, right? And yes, Tushar also points out one thing. So Tushar says that this has already been discussed in a previous class. So yes, it has been discussed in the array class. However, it is important enough to bring up again in the binary search class, right? Just to stress the point that binary search is not just always about binary search, right? You can still do sort of a binary search on even though you're not splitting the data into half, right? So very quickly, how can we do the search now? Suppose that we start from the top right. So once again, let us assume that the key we are looking for is 29. We are looking for the value 29, and 29 happens to be over here, right? So we better reach this point. But for now, we don't know where the key is. So let us start from the top right. And we will compare 29 with 50. 29 happens to be less than 50. Since 29 is less than 50, what can I eliminate? What part of my matrix can I eliminate? So where can 29 definitely not lie because of this comparison that I have just made? I know that in this particular column is sorted, right? So over here, in all this column, every element is greater than 50, is greater than equal to 50. And we already know that 29 is less than 50. So my key cannot be in this column, right? My key cannot be in this column. So I can eliminate this column. Do you agree? Yes. All right. Once I have eliminated the column, now I have a different matrix. right? I have a different matrix. The matrix exists only up till this column, right? So what is the top right part now? What is the top right part of the matrix? It is this particular cell. All right, let us compare once again. So we know that 29 is again less than 40. So once again, by the same argument, since this column is sorted, then 29 cannot be in any of these elements because we know that 29 is less than 40. So let us very quickly eliminate this column as well. Perfect. Let us move on to the next top right element. So this is 30. 29 is still less than 30. By the same argument, we will be able to eliminate this particular column. Does that make sense? Yes. Let us continue. So now the top right element is 20. Right? 29 versus 20. What is it? So 29 is greater than 20. Well, now a different argument appears. Let us look at the different argument. So we know that 29 is greater than 20. Right? So if we look at this particular column, if you look at this particular row, we know that everything to the left of 20, everything to the left of 20 over here, in that same row, right, that has to be less than 20. Everything to the left of 20 has to be less than 20 because the row is sorted. So 29 cannot be over here. So what we can now do is we can eliminate this particular row. We can eliminate this particular row. And notice that these columns have already been eliminated. Right? We move on to the next top right element. So 25 is the next top right element. We compare once again. 29 happens to be greater than 25. So by the same argument, we can eliminate this row. Then we move to the next top right element, which is 29. And now we can return yes, we have found 29 and 29 exists in our matrix. Is that clear? Yes. So we are not doing binary search. We are kind of doing a staircase search, right? We are zigzagging around. So in this particular case, we moved along this path. There's nothing binary about this, but this is still an example of binary search. Is that clear? Cool. Now, very quickly, what will be the time complexity? Time complexity of this approach. So we have already seen that linear search takes this much time. Binary search will take either n log n time or m log n time. What about this particular approach? Well, for this approach, we have to go from the top right corner, in the worst case, to the bottom left corner. Right? From the top right corner to the bottom left corner. And the path does not matter. The path does not really matter because in both the cases, we will be covering n different rows and m different columns. Right? So our total path length is equal to n plus m, irrespective of what paths we take. Right? Either we go this way, or we directly go over here, or we maybe take this weird way. Right? All these cases have the same path length of n cross m, m plus n. The time complexity will be order of n plus m. Is that clear? So this was a repeated question, but this was still very simple and very relevant to binary search. Let us move on now. So we very quickly saw this question. Let us move on to the next question. So Animesh over here says, can we rewrite this? So Animesh says that, okay, perhaps we can also rewrite this as order of max of n comma m. And that is true. That is true. So as we saw in the very first class on time complexity analysis, we saw that we can rewrite this part as max of n comma m, right? Because asymptotically, these complexities will turn out to be the same. They are related by a constant factor of each other. All right. Perfect. Moving on, let us see a more challenging question. So this question is very famously called aggressive curves. Aggressive curves. I think this question was originally from the platform Spodge, right? And this question is very, very common. I mean, this question happens to be one of the favorites for all the companies. So this question has been asked numerous times at Google. This question is still asked very frequently at places like DirectTag and Amazon. And this is a very, very nice question. Right? The special thing about this question, as you will see, is that it has a very nice solution using dynamic programming as well. But it can also be solved using binary search. Right? So a lot of the times when a student goes to an interview, they are expecting a difficult interview question. Right? A lot of the students are afraid of dynamic programming, even though dynamic programming is pretty easy. Right? So whenever they see this question, the natural approach, the natural idea that comes to their mind is, okay, I can try dynamic programming on this particular question. I mean, of course, dynamic programming solves this question, but binary search solves this in a faster manner. Okay, so let us quickly see the question. The question goes something like this: that you have n different stalls. You have n different stalls, right? And the stalls, so let us say n is greater than 2. You have n different stalls. So you have more than 2 stalls. And you have C cows, right? Once again, C is going to be greater than 2. There's one constraint over here that C is less than or equal to n. All right? We have n different stalls and we have C different cows. Now, you have been given the location of these stalls. The location of these stalls has been given to you. So let us say that we have 4 stalls, right? N equals to 4. And the location of these stalls are 1, 2, 5, and 8. All right? Or let us say make this n equals to 5. Let us just add one more. And 1 to 5, 7, and 8. What that means is that the first stall, the 0th stall, is at location 1. The first stall is at location 2. The second stall is at location 5. Third stall at location 7. And fourth stall at location 8. Right? So you can try to imagine this, that this is one stall, this is the other stall, this is the third stall, this is the fourth stall, and this is the fifth stall. And if this is at 0 meters, then perhaps this stall is at 2 meters, then this stall is at 5 meters. Right? This stall happens to be at 7 meters, and this stall happens to be at 8 meters. So they are unevenly spaced. Right? These stalls are unevenly spaced. Now we also have C cows. Right? Suppose for this example, we have 3 cows. Right? C equals to 3. So now our task is to place these cows. Our task is to place these cows into the stalls. And one cow can only go in one stall. So I'll just draw the cow as a circle. Right? Cows are not sphericals. So I mean, if you were a physicist, then you would say that okay, cow is you would consider a spherical cow in vacuum. Right? But we are not physicists over here. So let us just consider this cow in this particular stall. Right? So I can put this cow installed in many different ways. If I have 3 cows and I have 5 stalls, if I have 5 stalls and I have 3 cows, then very quickly, can someone tell me what is the total number of ways I can put them? What is the total number of ways I can take 3 cows and put them in 5 stalls? Well, that will simply be 5 choose 3. Right? I have to choose 3 stalls out of 5 stalls to put the cows in. And oops. So let us go back. Sorry about that. Right? And if the cows are distinguishable, then I will also have a 3 factorial factor coming. Right? That depends on whether the cows are distinguishable or not. Right? Perfect. So suppose I put the first cow over here in this stall. I put the second cow over here in this stall, and I put the third cow over here in this stall. Right? Now the cows are aggressive; they want to fight with each other. Right? So we want to maximize the distance between the cows. Right? Now, but there are multiple differences, right? So there's one distance between this cow and this cow. And there is one distance between this cow and this cow. So which distance are we trying to minimize? We are trying to maximize the minimum distance. The minimum distance between any 2 cows. Right? So let us suppose that this distance is 6 and this, so let us not suppose that this is 6. Let us just calculate. So this is at 2 meters and this is at 7 meters. So this distance will be 5 meters. Right? Similarly, this is at 7 meters, this is at 8 meters. So this distance is 1 meter. Right? Now the minimum distance among these two is 1 meter out of 5, and 1 is minimum. So we are saying that this is the minimum distance between 2 cows in this particular arrangement. We want to maximize this distance. We want to place the cows as far apart as possible. All right? And this distance, mind you, this distance is not in terms of the stall number. This distance is in terms of the location of the stall. Right? So we have 2 things over here. We have the 0th, 1st, 2nd, 3rd, 4th stall. We have the stall number. That is not what we're talking about. We're talking about the distance in terms of the location of the stall. Is the question clear? Yes. So very quickly, what do you think should the answer for this particular case be? Suppose that this is the arrangement. Suppose that this is the arrangement. I have stalls at 0 meters, 2 meters, 5 meters, 7 meters, and 8 meters. And I have 3 cows. Then where should I put these cows? Where should I ideally put these cows to maximize the distance? Yes, the first cow should go in this particular stall. The first cow should go in this particular stall. All right. Then I can put the second cow in this stall, and I can put the third cow in this stall. Is that clear? Yes. So this will be the ideal case. And what will be the final distance? The distance will be, so the distance between these 2 cows happens to be 5 meters. The distance between these 2 cows happens to be 3 meters. Right? And the minimum of those distances is 3 meters. So we are making sure that the cows are 3 meters apart from each other. Any pair of cows is 3 meters apart from each other. All right? Perfect. So now the question is that given you have been given N, you have been given C, and you have been given the location of these N stalls. Right? And you have to tell me what minimum distance can you achieve? Can you achieve by placing the cows as far apart as possible in the different stalls? I hope the question is clear. So basically, if this is the input, you have to give me the output 3 meters. Right? You have to give me the output 3. All right. Now, how will we do this? How can we do this? So once again, let us start with a very, very brute force approach. The brute force approach would be to try all possible arrangements of the cows. Right? Try all possible arrangements. So as we just saw, so are the cows distinguishable in this particular case? Does it really matter what the first cow, second cow, and third cow is? No, it does not, right? All that matters is what stalls they are in. So over here, how many possibilities do we have? We have 5C3 possibilities, right? Or basically, we have N choose C possibilities, where N is the number of stalls and C is the number of cows. So if we do this brute force, we will check each of the possibilities, and then for each possibility, we will find the minimum distance. Right? We will find the minimum distance. So what will be the overall time complexity of this brute force approach? It will be order of N choose C times. So once we have chosen an arrangement, we still have to calculate. So let us say that we have several stalls and we have chosen to put 1 cow here, 1 cow here, and 1 cow here. That is not done, right? We still have to measure these distances and find the minimum distance between any pair of cows. So that will take us an additional of order of N time, because we have to go through every pair of cows. Right? The total time complexity will be N choose C times N. Well, how big is N choose C? Can someone tell me how big N choose C is in terms of ON complexity? So what polynomial, N to the power what will it approximately be? This is the same as N to the power C, right? N choose C is the same order as N to the power C. Yes, no? Yes, no? Well, not really. Not really, because binomials flip. From the midpoint, the binomials flip. Right? So we are assuming, so this is if C is less than N by 2. Right? C is less than N by 2. So we can rewrite this as, so let us not write this complex expression. Let us just keep this as N choose C times N. And this is in the worst case. In the worst case, this is equal to order of N to the power C times N. Right? Now, if C is very big, if the number of cows is very big, this complexity is perhaps not that big. Right? If there are 10 cows, then you will have to spend N to the power 10 times. That is very, very bad. Right? So let us try to optimize this approach further. Let us try to optimize this. Okay. So those of you who are familiar with dynamic programming, what would you try to do over here? What would you try to do over here? So anyone who is familiar with dynamic programming would say this, that all right, I have several stalls and I have some cows. Right? I have several stalls and I have some cows. That is simple, right? For every stall, I have to make a yes/no decision. I have to make a yes/no decision whether to put this cow in there or whether to not put this cow in there. Right? So people would try to apply DP over here and say that, okay, for the first stall, I can choose whether I'm going to put the cow in or I'm not going to put the cow in. Again, for the second stall, I'm going to choose whether to put the cow in or to not put the cow in. Right? And so on and so forth. I will build my choices. And by DP, I can finally find the answer. Well, that is perfectly valid. Right? That is perfectly valid. And if you do that, your complexity will turn out to be order of n squared, which is not bad, right? Which is definitely better than order of n to the power c times n, right? But we can do better. But we can do better. So the moral of this story is that even if you have come up with a solution, it is still worth checking if the solution can be optimized or not. All right. Now let us dive into the most optimized approach, which will be using binary search. Binary search. Perfect. So if we are supposed to use binary search, we have to have a search space. We have to have a search space. We basically have to decide what we are searching for. What are we really searching for over here? Can we search for the location of stalls? Can we search for the location of stalls? That doesn't really make sense, right? Because we have to consider multiple stalls and there are multiple cows. So how it doesn't really make sense to search for the location of a particular stall. What we can search for is the answer itself. We can search for the answer itself, right? So what is the answer over here? The answer is the minimum distance. The answer is the minimum distance. And we are trying to maximize this particular answer. Minimum distance between any two cows. Between two cows. All right. So now that we have figured out what we have to search over, let us quickly discuss the bounds. Let us quickly discuss how large this search space is. So what is the minimum value for this minimum distance? What is the least possible distance that we can achieve? What is the least possible distance when we can achieve? Well, if every stall, if we are forced to put one cow in every stall, and every stall is 1 meter apart, right? So they're just next to each other. They're just next to each other. Then the minimum distance will be just 1. Do you agree? Can the minimum distance be 0? Can the minimum distance be 0? Not really, right? Not really. What is the maximum possible distance that we can achieve? What is the maximum possible distance that we can achieve? Well, this is my first stall, right? This is my 0th stall is at location 0. All right. And let us say my nth stall, my n minus 1th stall, right? Let us say it is at location, let us say L. All right. And I have to place C cows. I have to place C different cows within this distance. So in the worst case, I mean, even in the best case, doesn't matter how the stalls are arranged. Can I achieve, what is the best distance that I can achieve? If all the stalls are equidistant from each other, then I can simply place the cows one in each of them, right? And then basically my distance will be L by C, right? This is the maximum possible distance I can achieve. Can I achieve more than that? Can I possibly get more than that? No, because once I have placed the cows at equidistant locations, if I try to move any cow to the left or right, then the distance between the previous cow or the next cow, this decreases. Right? And we are supposed to consider the minimum distance between any pair of cows. Right? Minimum distance between any pair of cows. So the maximum possible distance that we can achieve possibly is L by C. Right? And what is L over here? L is simply the maximum of the array. Right? So let us consider that these distances are given to us in the array. Right? So this location of the stalls, this has been given to us in array of size n. Right? So this is simply max of A, right? Max of AL for all n. So we now have the bound. We now know that we are supposed to look for a value in this search space. This search space goes from 1 all the way till max of A of I. All right. Now, what else is required for a binary search? So now that I have a low and a high, I will calculate a mid, and this mid is going to be my guess. Okay? This mid is going to be my guess. Now I have to check. Now I have to check several things. I have to check, is the guess perfect? Is the guess valid? And is this the correct answer? That's one thing I have to check. Or I have to check, is the guess too low? Or I have to check, is the guess too high? Because only if I know all these three things, only if I know the answer to these three things, only then can I adjust my search space. Do we agree? Yes, exactly. We need a proposition. Right? If I don't have these three values, I will not be able to figure out in which direction should I move in the search space. All right. So let us quickly look at how we will do that. So suppose that I tell you, suppose that you have been given this array A of n, size n, and this is the location of stalls. Location of stalls. And I am telling you that, okay, you can achieve a distance. You can achieve a distance of, let us say, 5 meters. Right? We have to verify whether this is true or not. So how will we verify that? How can we verify that? Well, this is very simple. Right? This is very simple. What we can do is, so let us suppose that these are the stalls. Right? And let us suppose that this is at location 0, this is at location 5, this is at location 7, location 11, location 16, location 23. Let us suppose this is how the stalls look. So what we can do is we can place the first cow in here. Right? We can always place the first cow in the first stall. Then we can move on to the next stall and we can check what is the current distance. What is the current distance? Is that distance greater than or equal to 5? Yes, it is, right? So we can safely place the next cow over here because we are trying to achieve a distance of at least 5. We're trying to achieve a distance of at least 5. All right, then we can move on. So when we want to put the third cow, we will come to the next stall and check. Is the distance from the previous cow greater than or equal to 5? So is 7 minus 5 greater than or equal to 5? No, it is not. Right? So we cannot, if we have placed the cow in this stall and we are trying to achieve a distance of 5 meters, then we cannot put the next cow in this stall. All right. What about the next stall? Well, the distance from 5 till 11 is 6. So we can safely place the next cow over here. Does that make sense? Moving on. So we can definitely place the next cow over here. And we can also place the next cow over here. Right? So we can place the cows in this particular manner. Now, if we are able to place all the cows, successfully, right? So remember that we have C cows, right? If we are able to place all the C cows successfully, then what can we say about this particular guess? What can we say about this particular guess? Is this the correct guess? Not necessarily, right? This is a valid guess. This is a valid guess, but we are supposed to maximize this guess, right? So this is a valid guess, but this might not be the maximum value. So we have to continue searching. We have to continue searching with larger values. Right? We have to continue searching with larger values. Suppose that we were not, so if we were able to place it, then we have a valid distance, but the distance can be higher. All right. What is the other possibility? The other possibility is we were not able to place all the cows. Right? For example, suppose over here, let us suppose that my guess distance was, so let me just erase this. So let us say that my guess was that, okay, I can achieve a distance of 10 meters, right? And let us suppose that I had 3 cows to put. So I will try to put the first cow in this first stall. Then I cannot put the second cow in the second stall or in the third stall. I will have to put the second cow over here. Right? I will have to, in this case it will work. So let us just say that we had 4 cows. Let us say that we had 4 cows. So I will put the second cow in this stall. Then I can't put the third cow here. I can put the third cow here. So I will put the third cow over here. Now where do I put this fourth cow? I cannot possibly put the fourth cow because I have exhausted all my stalls. Right? So in this case, we see that we had a guess of 10 meters distance and we tried to place the 4 cows, but we were not able to place all the 4 cows. We were only able to place 3 cows. So that means that my guess is incorrect. Right? That means that my guess is incorrect. Is there anything else that I know? I know that my guess is too high. Right? If 10 meters did not work, then 12 meters or 20 meters or 50 meters will also not work. Right? My guess is too high. I have to reduce my guess. Does that make sense, guys? Yes? So what we are essentially doing is, we are saying that let us initialize the low as 1, the high as L by C. So this is maximum of A of I, right? So maximum of A of A is just the last location, the location of the last one, A of A dot length or N minus 1, right? A of N minus 1 by the number of cows, C. Then while our low is less than equal to high, right? What we will do is we will calculate a mid. So our guess is the mid, which is simply low plus high minus low by 2. Do you agree? Now we have to verify the guess, right? So if works, right, if this array for this number of cows, for this value, for this guess, if this works, so we will write this function works. But if this works, then what can we say? If this particular thing works, then what can we say? We can say that, hey, this guess is valid, but it might be too low. Right? This guess is valid, but we could do better. Right? So we have to increase our guess. Right? How will we increase our guess? We will say low equals to mid plus 1. Right? But this guess worked. Right? This guess worked, so we must also save it. This was the largest guess that worked. So let me also save a variable over here, largest working guess. Right? Let me save a variable over here, largest working guess. And this was initialized with, let's say, 0 or minus infinity, whatever you want. And I can say over here that largest working guess equals to maximum of my guess, my mid. So it is maximum of mid, the current guess, comma the largest working guess. All right, I can make sure that whenever I have a valid guess, I save the largest of those valid guesses. Is that clear? On the other hand, if this does not work, then I have to adjust my high. High equals to mid minus 1. Right? And at the end of this loop, when this loop is through, I can simply return whatever maximum guess I have found so far. So largest working guess. Does that make sense, guys? Does this binary search make sense? Yes? We still have to write this function, right? We still have to write this works function. Well, this function is very simple, as we saw. How will this function work? So we have to write works. This will take an array. This will take the number of cows. And it will take a guess. So what will we do? We will start from the location first. Right? We will say that the previous stall equals to 0. Right? We will place the first cow at location 0. Now, how many cows do we have to place now? So for I goes from 1 till C minus 1. Right? We have already placed the 0th cow. Now we have C minus 1 cows remaining to place. Right? So we will go over each cow, and then what will we do? Right? We will try to place the cow in the next stall. So we will also, let me also save a stall number over here. Right? So stall number is 1. Right? I have already used up the stall number 0. So the current stall number is 1. Okay. So now what can I do is, I can try to put the cow in over there. So I can say while the location of the current stall, right? While A of stall minus A of previous stall. Right? If this distance, while this distance is less than my guess, I cannot really put this cow in the current stall. Right? So I must move on to the next stall plus plus. Do you guys agree? While this is true, I will do stall plus plus. Right? And finally, I will say that, all right, once I have this, I will say previous stall equals to stall. Right? So I will put the cow in there. So this is my loop. Now, of course, this loop might not always work. Right? Basically, when will it fail? When will it fail? When my stall number has become equal to the size of the array. When I have reached the last stall, but my cows have still not been finished. Right? My cows have still not been finished. So I can put a condition over here. I can very quickly check over here. So instead of directly doing this stall plus plus, let me do a stall plus plus. And now I can check if stall equals to n. If I have already reached the last stall, then I can return false. Return false. Because this guess did not work. I still have some cows to place, but I have exhausted my stalls. Right? So I will return false that, hey, this guess does not work. If I can complete this for loop, that means that I was able to place all the C different cows. I was able to successfully place all the C different cows at a minimum distance of guess. So over here, I can return true. Return true. Does that make sense? Does this function, this works function make sense? Yes? Do you guys agree? Perfect. So what will be the time complexity of this? What will be the time complexity of this entire code? Well, let us take it step by step. Right? How much time does the works function take? Given a particular guess, how much time does it take to verify that guess? Well, we have to linearly search through the array of stalls. Right? We have to linearly check the array of stalls. So this works takes order of n time, right? Where n is the number of stalls. Do you agree? Do you guys agree? So, okay, some people will over here say that, okay, you have a while loop. You have a while loop over here, and you have a loop that goes C times over here. So isn't the complexity going to be C times n? Shouldn't the complexity be C times n? Well, no, right? The complexity of this entire for loop is not C times n, because as we see, this variable stall is strictly increasing. Right? This variable stall is never reset. So it can only increase. And the maximum possible value of stall can be up to n. Right? So it is the complexity of this entire nested loop. It is not C times n. It is simply order of n. Is that clear? Yes, perfect. What about this? What about this binary search? So I think I deleted something from here. Right? What about this binary search? So this binary search takes us how much time? It takes us log of the size of search space. What is the size of search space over here? Is the size of search space n? No. The size of search space is this value over here. Right? This is the size of search space. A of n minus 1 by C. Right? This is the size of search space. So this will be the number of times we will have to do the binary search. And each binary search will take us order of n time. So we can say that the complexity of this is order of log of max of AI, max of AI, so the maximum stall location divided by the number of cows, right? The log of that times n. Is that clear? Yes? Yes or no? Well, C over here. Is that clear, guys? So C is not a constant, so we can't really ignore it. So this will be the final value. This will be the final value. And is this better than n square? So do you guys think that this is better than n square? Well, that will depend. That will depend on how large this A of I is. Right? How large this A of I is. Is that clear? So it might be the case that A of I is 1 trillion. If A of I is a very, very large number, then it might make sense. It might make sense to do this n square solution. But that is going to be extremely, extremely rare. Right? So if n is large, then definitely this log value will be much, much smaller. Right? So in general, this approach will work faster. Is it clear? So we saw the brute force approach for this. Right? That was order of n to the power c plus 1. Right? Then we saw the DP approach for this. We did not discuss this in detail. We will discuss this maybe later. So this was order of n square. And then we discussed the binary search approach. And this turned out to be order of log of max of A by C times n. Is that clear? Yes? Any doubts on this particular question? I hope that you will be able to code it. So this is part of the assignments. So please try and code it. You will actually learn a lot when you implement these solutions. Right? And one more thing, please try to make sure that you make the code modular. Right? So just like we have discussed in the class, please define a separate function, right, that will check the guess. You can also write this. You can also write this code over here as well. Right? You can also write this code over here as well. But please do not do that, right? Because then your logic will not be clear. You will be mixing the logic of your binary search with the logic of your checking a guess. Let us keep those two logics separate. Binary search is separate. Checking if a particular guess works or not, that is separate. So please let us do the separation of concerns thing and then keep them in different functions. All right. So let us move on to another question. So this is again fairly challenging question, and this is also a very interesting question. Okay. So the question goes something like this: that you have been given an n, you have been given a number n, and this n is a 64-bit number, 64-bit integer, and let us say it is also positive. All right, let us say it is also positive. Let us also say that n is greater than 2. All right, let us also say that n is greater than 2. So basically, what values can n take? So n can take a value from, let us say, suppose 3 all the way to 10 to the power 18, perhaps. Right? N can take all these different values. Cool. So now what we are saying is, let us suppose that n written in some base k, n written in some base k. So k can be either 2, in which case we are writing n as a binary number, right? Or k can be ternary, or k can be 3, or k can be 8, in which case we are writing n as an octal number, right? But if we write k in, if we have n in some base k, and if this equals to 1 1 1 1 1 dot dot dot, right? If this is just a string of ones, right? Then we will say that, okay, this k is a good base. Good base. All right, is that clear? For example, let us say that n equals to 7. All right, n equals to 7. Then what different bases will work? What all different bases can work? So first of all, this k equals to 1 will always work, right? Yes or no? I can always write something in base 1. Right? A number n in base 1 is just 1 1 1 1 1 n times. Do you guys agree? Yes. Let us not do that. Let us not do that. Let us ignore this k equals to 1 thing. All right. Let us ignore this k equals to 1 thing. So we are also considering that k is greater than 1. That k is greater than 1. Okay. Now let us try some other base. So 7 written in base 2. What does this look like? What does 7 in base 2 look like? 7 in base 2 is, so this is base 10, my bad. This is base 10. In base 2, if I write it, then it will be 1 1 1. Right? So 2 is a good base. 2 is a good base for 7. All right. Are there any other good bases? Are there any other good bases? Yes, no? Well, what happens if we write 7 in base? What happens if we write 7 in base 3? What do we get? So we get 1, then 4 remains, right? Then we will get, so just give me a second. So the last, so 7 is basically equal to 3 to the power 0 plus 3 to the power 1 plus 3 to the power 2. So this is going to be 3 to the power 3. Yes, so this is going to be 2 times 3 to the power 1 plus 1 times 3 to the power 0. Yes, so this is 7. This is 7. So what will 7 look like in base 3? What will 7 look like in base 3? 7 will look like 2 1 in base 3. Right? 7 is 2 1 in base 3. So is this a string of ones? Is this a string of ones? No, this is not a string of ones. So 3 is not a good base. 3 is not a good base. All right, let us continue. Let us continue. So we can check the base 4, we can check the base 5. That is also not going to work. there is some other base that is going to work. Right? 7 in base 7 is also equal to, in base 6, this is going to be equal to 1, 1. Right? In base 6, this is also going to be equal to 1, 1. Do you guys agree? Yes. In fact, if I have any n in base 10, then this is equal to 1, 1 in base n minus 1. Yes or no? 1, 1 in base n minus 1, that is simply n. Why is that? Because see, 1, 1 in base n minus 1, this is equal to n minus 1 to the power 0 times 1 plus n minus 1 to the power 1 times 1. Right? And that is equal to what? N minus 1 plus 1, which is just n. Right? So any number n that I have, I can always write in one less base and get a string of ones. So 7 equals to 1, 1 in base 6. Right? 13 equals to 1, 1 in base 12, and so on. Do you guys agree? So n minus 1 is always a good base. Right? N minus 1 is always a valid base. So this is also a good base. Right? Cool. Now the question once again is that you have been given a value of n, right, such that n is greater than equal to 3 and n is less than or equal to 10 to the power 18, suppose. So it is a 64-bit integer, positive integer. We have to find the smallest base, smallest good base. All right, so we found several different good bases, right? For 7, we found that 2 works. So we found that 2 works, 3 does not work, 4 does not work, 5 does not work, 6 works. Right? That is what we found for 7. So what will be the smallest good base for 7? What will be the smallest good base for 7? It will be 2. Right? It will be 2. So smallest good base. So for example, if n equals to 7, then the answer will be 2. And why 2? Why not 1? Because 1 works for everything. Right? If we allow 1, then for every number the answer will just be 1. Because base 1 works for everything. Is that clear? So we are saying that the smallest good base, let us call this k, is greater than or equal to 2. So this is the question. I hope the question is clear. Given an integer n, return the smallest good base. For example, if your value is 7, then you are supposed to return the value 2. All right. So what can our approach be over here? What can our approach be over here? Let us start with the most brute force approach. Brute force approach. What will the brute force approach look like? In the brute force approach, we can simply check all the possible options. Right? We can simply check all the possible options. So we can go from base k equals to 2 all the way till n minus 1. Right? We can check all these different values. Now, once we have a base, we have to convert n into that base, right? Base k, and check if this is a string of ones. If this is a string of ones, well, how much time does it take to convert a number into base k? How much time does it take to convert a number into base k? Can someone quickly tell me that? It will take me log of n time base k. It will take me log n time with a base k. This is how much time it will take me to convert a number. Why? Because I have to repeatedly divide that number by k. Right? I will say that, okay, the last digit equals to n mod k. Then I will divide the number. Right? I will say n by equals to k. N by equals to k. This is not or this is a simple division. Right? Then I will say d1 equals to once again n mod k. And then I will again say n equals to n by k. Right? And this will be in a loop. This will basically be in a loop. That is how I convert the base. So it will take me log of n time base k. All right. So what is the total time complexity over here? I have these many bases to check. And it takes this much time to check each base. So it will be order of n times log n. Right. So my brute force approach takes me order of n times log n time. Is that clear? Yes. Now this is not very good, right? This is not very good. If my n is, let us say, 10 to the power 18, then it will take me 10 to the power 18 steps. That is definitely not possible. I cannot do 10 to the power 18 steps on any computer. Yes. So we should better come up with a faster solution. We should try to come up with a faster solution. Okay. So what can we do over here? What is the first thing that comes to your mind? What is the first thing that comes to your mind? The first thing, since we have been doing binary search, might be that, okay, let me make a guess. Let me guess base B. Let me guess B and check if the guess is valid or not. Yes, that is what comes to your mind. That let us take a base B, let us consider a random base B, and let us check if it is valid or not. Well, this is not going to work for this case. This is not going to work for this case. Why? Suppose that my number was 7. I checked the base 2. I checked the base 2 and it worked. What does that tell me? Does that really tell me anything? That tells me that 2 works. That tells me that 2 works, but that is not enough, right? I also have to understand. Is my guess too low or is my guess too high? Yes. Just because 2 works, that does not mean that my guess is too low or that my guess is too high. Do you agree? It might be the case that 7 of 6 still works, right? So for this, for the base 7, 7 of 2 works, 7 of 3 does not work, 7 of 4 does not work, 7 of 5 does not work, 7 of 6 works. This works. So suppose you make a guess. There is a valid value to the right of it as well as to the left of it, and you do not know in which direction you have to go. So if it turns out to be false, if you figure out that, okay, the guess did not work. So are you supposed to increase the base or are you supposed to decrease the base? Are you supposed to increase the low or are you supposed to decrease the high? Does that make sense? We have no way of knowing in which direction should we move our guess. So we cannot do the binary search over base. Does that make sense? Because once again, if we go back to the first class, if this is our search space, then we need to come up with a proposition such that all the answers here are yeses and all the answers here are no's, so that we can binary search for this midpoint. For this particular thing, the answer over here is yes, the answer over here is yes, the answer over here is yes, but all the other numbers can be no. Right? We don't really know. It can be randomly. It can be in a random manner. So binary search is not going to work for this proposition. Is that clear? Yes, it seems very, very seductive to try to apply binary search over here. I have a base. I can verify if it is a valid base or not. So let me just binary search over the base. That is not going to work, unfortunately. So what else can we do? What else can we do? So we have to look at the question from a different perspective over here. We have to look at the question from a different perspective over here. So let us suppose that we are talking in base B. Right? Suppose we are talking about in base K. Suppose base K. Right? Then if basically my number n in base K is a string of ones, I already know what the string of ones is, right? I can construct this string of ones, right? I know that this is in base K. I know that this is a string of ones. The only thing I don't know is how many ones there are over here. Yes, how many ones there are over here. Let us call this value I. Does that make sense? So n written in base 2 will have 3 ones. Right? N written in base 6 will have 2 ones. Right? So instead of trying to binary search over the value of k, let me try to binary search over the value of I. Okay, let me try to binary search over the value of I. But let me first establish a relation between these two. So if n in base k is a string of ones in base k, so n is equal to a string of ones in base k, right? And let us say that there are I ones over here. Then what can I say? Is there any relationship between n and k? Is there any relationship between n and k? Yes, there is, right? What is the relationship? I know that 1 times k to the power 0 plus 1 times k to the power 1 plus 1 times k to the power 2 plus all the way till 1 times k to the power I, right? This thing equals to n. Right? If I have this number in base k, then this is the expansion of it, and I know that this must be equal to n. Right? What can I say? N equals to summation of k to the power I, or k to the power, let's say x, for x equals to 0 till I. Right? So this is what is this? This is a geometric progression. This is a GP. So can I write the sum of it? The sum of it is simply k to the power I plus 1 minus 1 by what? By k minus 1, right? So the sum of a GP, summation of r to the power I for I equals to 0 till k, this is equal to what? 0 till n, this is equal to r to the power n plus 1 minus r to the power 0 by r minus 1, right? Yes. So just notice that there is this denominator over here, right? You can't simply say that the denominator is 1, right, Shazia? So Shazia, there's a small mistake in your formula. You have to make sure that this denominator is also dependent on k. Right? So we can say that n equals to k to the power I plus 1 minus 1 by k minus 1. This is the relation that we have established between n, k, and I. Now I know that I cannot really binary search over k, but that's okay. Let me binary search over I. Right? Let me binary search over the value of I. All right. Now let us suppose that I have I ones over here. Right? Let us say that I have I ones over here. Right? And this is equal to n. Right? This is equal to n. Then what if I'm trying to minimize? So remember that I have to find the smallest good base. Right? I'm trying to minimize the value of k. So what am I trying to do with the value of I? If see n is my constant, right? N is my constant. I'm trying to minimize the value of k. So what am I doing with I? I'm trying to maximize the value of I. Right? I'm trying to maximize the value of I. Do you agree? Yes or no? Right? Yes or no, guys? So that is one thing we know. Perfect. We know that we are trying to maximize the value of I. All right. Let us also consider what is the search space of I. Search space of I. What is the search space of I? So I can be, so this can be, so let us suppose that I write n in base 2, right? This is the smallest base that I can possibly have. So that will give me the largest possible string of ones. How many ones will I get when I write n in base 2? I know that n is a 64-bit integer. Right? So the maximum search space, the maximum value of I can be 64. Right? So I can have all the way from 2 all the way to 64 ones in my string. All right. Now, once again, the problem over here arises. If I know that this sequence of I works, does that tell me anything about this sequence of I or about this sequence of I? Does that tell me anything about this sequence of I or this sequence of I? It does not. Right? I know that I have to maximize the number of ones. But if this works or if this does not work, it doesn't tell me whether I should increase it or decrease it. So I cannot really binary search. Over the value of I either. That's sad. But how many i's can there be? We just established that the maximum possible value of I can be 64. On the other hand, when we were talking about k, we established that the maximum possible value of k can be up to n minus 1. So what would we rather search over? Should we search over k or should we search over I? This can be up till n minus 1. This can only be up till 64. Right? So this is much better, right? Do you guys agree? Searching over I is much better. So I can simply check for every possible I. For I goes from 2 till 64. Let me check for all the possible. Strings of 1. Right? Let me check all the possible strings of 1. Now what I will check? Now I will see whether n can be written in the form of 1 1 1 1 1 I ones to the base k. Whether I will try to see whether any such base k exists that will give me this. Does that make sense? I can go over every I. Yes, but how do I find this k now? I know the relationship between these two, right? I know the relationship between all these numbers. I know that n equals to k to the power I plus 1, right? N equals to k to the power I plus 1 minus 1 by k minus 1. I know this relationship. So now, if I have the value of I, and if I have the value of n, can I find the value of k? Can I find the value of k? Yes. How will I find the value of k? That is difficult, right? I will have to manipulate the formula. Right? If I want to find the value of k, I will have to manipulate the formula. I will have to extract k out of it. So can someone solve this equation for me very quickly? Can someone solve this equation for me very quickly? Well, you can't really. You can't really do that. Right? Because this I might be a very, very large number. Right? And you don't, so for higher degree polynomials, you don't always have a way of solving an equation. So you can always solve a quadratic. If you have a quadratic equation, you can always solve it. If you have a cubic equation, you can always solve it. Right? But for higher equations, I'm not sure for the fourth power, but I know that from fifth power and above, right, it is not always solvable. It is not always possible to solve a higher degree polynomial. All right. So this equation might not be solvable. So what can we do? Do we have to give up? No. Here is where we can binary search. We can binary search for the value of k. Right? We can try to plug in the value of k and try to binary search for an answer that works. Is that clear? So what we will do now is we now have to find a k that works. What is the maximum possible value of k? The maximum possible value of k, so the minimum possible value of k is 2. The high maximum possible value is n minus 1. And now I can binary search over this value of k. I just have to find one k that works. I can binary search for k which satisfies this equation, which satisfies the equation n equals to k to the power I plus 1 minus 1 by k minus 1. Is that clear? So just like in the first class, we tried to binary search. So we did not do it in the class, but it was part of your assignment. Right? So in the assignment, you had to do a binary search for the square root of a particular number. Right? For the square root of a particular number. Yes, so n minus 1. Right? This is n minus 1. Right? So we can binary search over the value of k. Is that clear? So how much time will this binary search take? How much time will the binary search for k take? This is my search space. Right? This is my search space. My search space has size of n. And I'm doing a binary search, so it will take me log n time. Log n time to binary search for a value of k. But I have to do this 64 times. I have to do this for all values of I. So this will be times 64. So the overall time complexity of my approach will just be 64 times log base 2 of n, which will just be log n. That is amazing. Right? We went from an n log n solution. We went from an n log n. What happened over here? N log n brute force, and we reduced it down to a constant times log n. Is that clear? Yes. So even though the question does not directly involve binary search, there is still an involvement of binary search. And the moral of this particular question is that be very, very careful. Be very, very careful. For binary search, you just don't have to make and verify a guess. You also have to understand, given the guess, if that guess worked, then is the guess too high or too low? Right? If the guess worked or if it did not work, this is not enough. You also have to establish, is the guess too high or too low? Because if you cannot do that, then you will not be able to binary search for your answer. Is that clear? Perfect. Ankush has asked a very good question. Ankush is saying, how can we know whether binary search will be applicable for this particular question? Now, that is a very, very tricky question. So basically, the most common answer you will find to this is practice. Right? The most common answer that you will find to it is that, okay, if you just practice, then practice will make you perfect. You will get to know which way, which approach you have to apply. But that is not the entire truth. There is a separate way as well. So there's a systematic way. There is a systematic way of approaching problems. Right? Now, unfortunately, I cannot teach this systematic way in a YouTube class. Right? It cannot be taught in a 1-hour class. So the entire scalar curriculum, the entire scalar curriculum of DSM algorithms is based on tries to teach you this systematic way. Right? So that whenever you get a new problem, you can just apply the systematic algorithm and try to come up with a solution for that. Okay, that is what we teach in the scalar classes.
Hash table is one of the most important and widely used data structures in programming. But very few people know how does a hash table internally work. Hi, my name is Prateek, and in this tutorial we'll understand the internals of a hash table and concepts like rehashing, load vector, and many more. And why the operations like insertion, deletion, search are considered as order 1 operations on average. Also, subscribe the channel if you haven't done already. Let's begin with the tutorial. Let us try to understand what is a hash table and how it works. Okay, so you might be already using hash table a lot of times, and it is known by different names in different languages. For example, in Java it is called as Hashmap. In Python it is called as dictionary. In C++ it is called as unordered map, right? So there are different names, but the internals of the data structure, they are same in different languages. Okay, so hash map in Java, dictionary in Python, and unordered map in C++, and in, of course, in other languages as well, you have this data structure that is available, right? So the reason why we are going to study this data structure is it is very, very powerful, right? And it is used a lot, right? It is used a lot, right? So when I'm saying it is used a lot, so not just business logic. So when you're dealing with your problem solving, when you're building real software, you would often require a hash map to store data in the form of key value pairs. Okay, so it stores information in the form of key and the value pairs. But not just that, we can also store key value pairs in the form of a list, right? Why it is powerful? Because it allows us to do operations like insertion. I want to insert a key value pair. I want to look up for a particular key, right? And maybe I want to delete a particular key, right? A key value pair. So I can just give, okay, this is the key, delete the corresponding value and the key. So delete the key value pair given the key. So lookup means the search, right? I want to search for a particular key, if it is present or not, and if it is present, what is the associated value with that particular key, right? So these are the three important operations associated with the hash table, right? And the good thing about these operations is why this is so popular or why this is so powerful, because these operations are performed on an average in order 1 time. So order 1 on average, that means most of the times these operations will be performed in constant time. Okay, so we will discuss the scenario when they are not performed in constant time, but you can say, okay, most of the practical scenarios, these operations would be performed in order 1 time by the hash table, right? So now let us discuss where this can be used. Okay, so I discussed that it stores information in the form of key value pairs. Okay, suppose you are building a application for a restaurant, and user of wants to order particular item, right? So user says, okay, I want to check if dosa is available and what is the price of the dosa. The restaurant owner might instantly reply that, okay, the cost of the dosa is 100, right? So given this key, you are telling the value in order 1 time. Okay, maybe I want to order some coke, maybe this is priced at 50. Maybe I want to order some noodles, right? This is costing maybe 70, right? So what can happen with this menu? What are the operations we might be doing on a restaurant menu, right? So if we are building an online menu, we might be adding a key value pair. Okay, a new item has been added, maybe a pizza has been added. So you will supply, okay, pizza has been added and it is associated with some object, or in this case that object is nothing but an integer object only, right? So the cost of pizza is 250, right? So I can say I want to insert a new key value pair, that is doable. Second is I can look up. Now I can ask what is the price of the coke. So the hash map will tell me in order 1 time, yes, the price of the coke is 50 rupees. Then I can delete. I can say, okay, coke is not in the stock, delete coke. So it will be deleted from the table. So these are the three operations that our hash table is going to support, right? Now, of course, we saw that this can be used in business logic. When you're building an application, a hash map can be a useful data structure to use, right? Because it provides fast lookups, fast inserts, and fast delete operations as well, right? But one major application is also in the language runtime, right? So whenever you are working with a language like Java or C++, you know, you create certain variables, you say, create certain classes. So you say, okay, I'm going to create a variable int x, and I'm going to say this is 10, right? Then you say, okay, int y, this is 20, right? So what happens is how these variables are stored. So these variables are actually stored in the memory, right? So x is a bucket that is storing 10, y is a bucket that is storing 20, right? But when you want to make a change, you want to say, okay, x is equal to x plus 2, right? So your compiler needs to know where is this x located so that it can go to that location and change that bucket. Now, suppose this bucket is at some address ABC, right? Let's say ABC20, right? This is some address written in a hexadecimal format, right? So the compiler maintains a symbol table for all the variables and the classes that you're going to, all the objects that you're going to create. So there is a symbol table, right, maintained by the compiler, right? So this symbol table will tell that, okay, x is a bucket which is present at this location ABC20, right? Now when you do this operation, x is equal to x plus 2. So I'll just scroll up a little bit. When you're doing this operation, x is equal to x plus 2. So the compiler will look at the symbol table, where is x located, it will go to that location and it will make the change, right? Similarly, y is located at some location, maybe 11462, right? And maybe, right? So 11462. This is some other location for y. So y will, it will again look up at the symbol table, where is y located, it will go to this location and it will make the change in the y, right? Similarly, if you create some objects, let's say dog d, this is equal to new dog. So this dog object is created at some location in the heap, right? So similarly, your d will be mapped with some address, right? Now, what is your symbol table? A symbol table is also of a form of a hash table, right? It is also a form of a hash table, right? That your compiler is maintaining, and it is called as symbol table, right? Similarly, when you have classes and objects, right? So you say, okay, I want to create a new class called dog. The dog has certain properties, right? Let's say it has a certain name, it has a certain breed, it has a certain method, right? So what is happening? So you're able to map dog with various attributes and various methods, right? So all these features, right, they are powered by the language runtime, and language runtime might be is actually using hash table internally, so that you can do lookups very fast. Okay, if this functionality is slow, your language will become slow. So that is another application of hash table. It is used in the internals of the language. So I hope you got a good introduction about hash table. Now we will jump into the internals of the hash table. So let us talk about hash table internals, right? So what is exactly a hash table from inside? Basically, it is nothing but it's a container. Okay, it's like, in the simple form, it can be an array as well. Okay, of some size, right? So basically, whatever data we are given, we have to map this data with a certain index in this array, right? So suppose I'm getting dosa, right? So the first step of a hash table is that we have to hash the key value, right? We have to produce an integer location for a given key. Now, given key, in this case, I'm taking it of the string type, but it can be any object, right? It can be student, it can be book. So for that particular type of object, you need to tell the hash function how that integer value will be computed, right? So right now I'm assuming that there is a hash function which is going to accept some key, let's say dosa, and it is going to produce an integer location, right? So maybe that integer location is 0 1 2 3 4 5 6 and so on, right? Maybe dosa will get stored here, and the value will also get stored here, right? I got noodles, so noodles will also go into this, and maybe I get a location 6, so maybe noodles get stored here and 150 gets stored here, right, in the same location, right? So what is this hash function doing? Hash function is taking input a key, and it is producing a integer location in the array, right? Now you might have some questions, right? How big this array should be, right? Now if I have 6 keys, and if I have six let's say 6 size of the array, right, and I have 12 keys, then of course I cannot store 12 keys in this array, right? So it's going to cause problems. So we will look at how to handle this very soon, right? This is not the completely correct implementation. We are going to discuss it step by step, right? So the idea of hash function is that it is going to produce a unique integer location for every key, but it is also possible that for two different keys they get mapped with the same location. For example, if I get something like Coke, and this since this is a mathematical function, it might compute a similar location as well, right? So it might say, okay, Coke should also go here, right? So this is called as a collision. We will discuss how do we handle collision, right? So maybe 200 something, but the idea is how big this array should be, right? So one thing we need to notice that if it is producing an integer, then integer can take any value, right? So integer can be in the range maybe 0 to 10, it could be in the range 0 to 100, right? It could be even in the range of 0 to int max, right? So that means, like, if I talk about every possible integer that can be generated, this range can be int max as well, right? But do I really need to create this big array? Okay, int max is approximately 10 power 9 elements, right? If I talk about how much space this array will take in the physical memory, this will come out around 16 GB, right? So will you need 16 GB of an array, right? Or can you create this big array? The answer is definitely not. We cannot create this big array because this amount of continuous memory might not be available. And secondly, suppose you have created this big array and you have only 1000 keys in your key value pairs in your dataset, right? Then you are allocating space for 10 power 9 elements and you just need space for 10 power 3 elements. That means you are doing lot of space wastage, which is not a good option, right? Then how big this array should be? It should be roughly of the order of number of keys that you want to insert, right? So if you have an idea, okay, I want to insert somewhere around 1000 keys, then it is good enough. This array should have around 1000 buckets inside it, right? Or if you want to insert maybe around 500 keys, it should be of the order this much, right? So what I'm going to say that table size should be of the order number of key value pairs that you're going to expect, right? Now it might happen that you expected 500 keys, but in practice, since the data was dynamic, 700 keys came, right? So we'll also look at techniques to grow this table dynamically during the insertion process, right? So that is something we are going to study, right? What happens if there is a collision? How do we grow the table? How do we initialize the table? So all these concepts we are going to see next. So let's begin. Starting with the hash function, we will talk about insertion, searching, and deletion in the hash table. So we are discussing hash function, right? So as I discussed, hash function can accept a key. Okay, input is a key. It can be of it can be any type of object. For our case, I'm just assuming it to be a string, and I want an integer value in some range. Okay, in some range that is from 0 to n minus 1, where n is the size of the table, right? So n is the size of the table that I am implementing, right? So for example, just to keep things simple, I'm going to assume that I have a small table where the size of the table is just 7. So 0, 1, 2, 3, 4, 5, and 6. So indexing is from 0 to n minus 1. So I have this array, right? Or I call it as table as well. So this is having a table size of 7, right? Now I have a hash function which knows how do I convert a given string into a numeric value. So suppose I'm getting a key like dosa comma 100, right? The goal is to generate a integer, map it with an integer, right? And that value should not be random. It should be same always. So whenever you ask dosa, you have to tell me at what location this dosa is present, right? So goal is to convert this dosa into a number in the range 0 to 6, right? How do I do it? So one simple way could be that I iterate over the ASCII values of dosa, add them, and since this addition will produce a number much larger than 7, okay? For example, your capital A, right? I think it has a ASCII value of 65, B is 66, C is 67, so D will be 68, right? So similarly here you will have certain values, 68 plus something plus 65. This is going to produce a large integer, right? Maybe of the order 200 to 300, right? But I want to map it in the range 0 to 6, right? So what I will do, how do I reduce a bigger range, which is some larger range, into a smaller range, right? So I can say, okay, fine, this can be easily achieved by using a mod operator, right? So I can say mod with n. So I can take a mod with n. So let us assume that this mod gives us an answer that is 4. So that will be called as a hash index. Okay, so basically the index in the table produced by hashing, the hash index is, let's say, 4. So that means dosa will go at this particular index and this value will be stored at this place, right? Now the question is, what should I do? Maybe I am getting another key, right, in which the result is also 4, right? The result is also 4. So can this happen? The answer is yes. So I can say, okay, I have maybe Coke and maybe 150, right? I do not know. I add the letters of Coke, right? And I take a mod with n, right? Now, mod with n can produce the same result for many numbers, right? So maybe this also leads to 4. What, what happened here, right? What happened here? So Coke is also fighting for the same position. That means I also want to store Coke here, right? Now this thing is called as a collision, right? We have space for only one key value pair, but we want to store maybe 2 or more key value pairs at that particular location, right? So this is something called as a collision, right? So what happens, right? So what is a collision? So collision is a scenario in which basically two or more key value pairs, they get with the same bucket, mapped with the same bucket. So this, what does this mean, right? Can we avoid collisions? The answer is no. Can we reduce collisions? The answer is yes, right? So we will talk about both the things, right? So in order to reduce collisions, right, what we need is we need a good hash function. So we will work on both the fronts, right? So collisions should be, they cannot be avoided, right? So how, irrespective of how good a hash function is, collisions cannot be avoided, but they need to be handled, right? So cannot avoid collisions, right? Okay, but I can reduce the chances of collisions, but chances of collisions can be reduced by using a good hash function, right? But chances of collisions can be reduced using a good hash function, right? Using a good hash function. Now, how do we design a good hash function? We will discuss by taking an example of string, right? And secondly, since you cannot avoid collisions, so even if the collision is happening, you need a way to handle that collision, right? So they still need to be handled. So we need something called as a collision handling scheme, right? Collision handling scheme. This is something we will discuss very shortly, right? Now there are two important things here. One is what is a good hash function. Second is we need a good collision handling scheme. So first, good hash function will reduce the chances of collisions, but they still can happen. So if the collision is still happening, we need to handle it using collision handling scheme. So let us discuss how do we design a good hash function and how do we design a collision handling scheme next. So let us discuss the properties of a good hash function, right? So I am going to discuss the properties of a good hash function, right? So basically a good hash function should have two properties. First, it should ensure a more of a uniform distribution. Okay, it should ensure more uniform distribution, right? And secondly, it should be fast to compute, right? So that means we do not spend a lot of time in computing the hash index itself, right? For example, in our case, what we were taking, I will take examples of two hash functions. Okay, so let's say example number 1, in which I'm simply adding the ASCII values and taking a mod with the table size. So I'm saying fine, I will add dosa d plus O plus S plus A, and I will take a mod with the table size, right? Now, is this function fast to compute? Yes, because I just need to iterate on the letters of the key, right? So when I'm talking about I'm going to insert many key value pairs. So what is n? N is the number of key value pairs. Okay, so key 1 value 1, key 2 value 2, right? Key 3 value 3. So I want to insert many key value pairs. So my hash index does not depend upon the value n, but it depends upon how big my key is. So in general, the key would be small length. So we can assume that, okay, if it is a name of a person and the phone number as the value, the key would be maybe maximum 50 characters or 100 characters. So yes, in this case, this is a fast hash function, right? But is this hash function is going to minimize the chances of collisions? Maybe not, right? Why? Because if I talk about English language, right? In English, lot of words, they are anagrams. That means lot of words have same set of letters in them. For example, let's say the word is tab, right? So it is made up of T, A and B, and if you add, you will get certain sum, right? But if I talk about the word bat, right, it is also made up of same letters. So in this case, we are sure that these two are going to collide because our hash function is doing a very simple sum, right? So in maybe, of course, there could be other words also. Maybe the word is mango, right? Now it is possible that even if you do a mod with table size, you might end up at the same index, right? So we do not know. So in this case, it is of course difficult to tell whether the collision will happen or not, but it may still happen, right? But here we are sure that a collision will happen, right? So many words in English, they will have such a scenario, right? What we can do is, instead of doing a simple addition, right, we can do a weighted addition, right? So this is like a simple addition of ASCII values we are doing, right? So a better way would be that you do not do a simple addition in your hash function, but you do a weighted addition, right? So example 2 of building a hash function would be that you do some weighted addition, right? So that means you are going to multiply each letter's ASCII value with some weight, right? So for example, I choose a weight, maybe generally it is a prime number, right? So maybe I choose a weight as, let's say, 31, right, or 29, right? So what I can say that fine, I will multiply dosa with powers of 2. So let's say the weight is 29. So 29 power 0, that is 1, into D, plus 29 power 1 into O, plus 21 square into S, plus 21 square into A. And then I take a mod with table size, right? What I'm trying to claim is, now if you do it for bat and tab, it is less likely that you will have a collision, right? So I'm saying you multiply 29 power 0, which is 1. This is 29 and this is 29 square, right? And then you, like, it's a weighted addition. Again, 1 plus 29 into A plus 29 square into B, and of course mod with the table size, right? Now earlier we were sure that these two values will surely collide. Now we can say, okay, the chances of the collisions are less, okay? So there is a less chance of collision, right? So these are the factors that you can keep in mind, that okay, if I'm building a hash function, can I modify it some way so that it reduces the chances of collision and it is fast to compute, right? So here also it is fast to compute, right? Maybe if you have a string in which the length is too big, maybe you can restrict that, okay, I will consider only the first 10 letters of the string for this weighted addition. That can also be done, right? So that will even make the function a bit more faster, right? So if you are thinking that the keys are too long, you can restrict to maybe the first 10 letters or maybe something like that, right? So now we have a good hash function, which is the second one. The second one is obviously better. We are doing weighted addition, so it is going to reduce the chances of collision, right? But a collision can still happen, right? So how do we handle if still a collision happens? So here comes a collision handling scheme, right? So let us discuss about collision handling scheme now. So you have seen how do we design a hash function. Now we need to discuss how do we design a collision handling scheme, right? So collisions can still happen, we need to handle them, right? So let us talk about how do we design a collision handling scheme, right? Collision handling scheme, right? So there are actually multiple schemes, but I will particularly discuss one scheme, right? So in this case, what we can do, we can do something called as separate chaining. So we are going to discuss only one scheme. Uh, there are other probing techniques as well, right? So I will discuss separate chaining, right? So this is one of the most popularly and widely used schemes in implementing a hash table, right? Now I'll just copy the diagram that we have seen earlier. This is the diagram, right? So let me just copy it. Okay, so here we go. The idea is that if a collision happens, what should we do, right? That is what needs to be addressed, right? That we are going to address using a technique called as separate chaining. So suppose if we got dosa and it get mapped with index 4. So what we will do, we'll not store it directly inside this bucket, but instead every time we get a particular bucket mapped with dosa, we will start a chain from there, right? So what is a chain? A chain is like a linked list, so it's exactly a list, right? That means each bucket is actually going to hold the address of the first node of the list, right? So for example, I'm going to store dosa comma 100 here, right? Now suppose I got coke comma 150. So coke goes into the hash function, and maybe this time I get 2. So I will start a chain from 2, and coke will go here, coke comma 150, it will be stored here, right? Now suppose I got something like noodles, okay, and noodles is going to have a value, let's say 120. Now noodles, if it goes to the hash function, let us assume the hash function computes the index 4, right? Now at index 4 we already have dosa, so what we will do, we'll also try to store noodles at this index. How? So we can say, okay, we can add noodles to this linked list. Now suppose this is some address, let's say this is 150, this is 270, right? So this is storing 270, this is storing 150. So each array bucket is actually storing the head of the linked list, right? Now how we can insert noodles in this chain in order one time? It's pretty easy. So you can say, okay, I will create a bucket called noodles. Let's say this bucket is this node is created, so I'll create this node n with the given key value pair, right? So it's a new node with the given key value pair, right? Now in this new node, what should I do? Like how do I add this node in this linked list, right? So I can say, okay, this is some array, right? So, or this is some table. So I can say array of and let us also compute the index. So I can say index where I want to store this is given by the hash function of the given key, right? So I get to know the index also. So at this index I need to store noodles. So one thing I can do is either I can insert at head or I can do insert at tail. Since I'm not maintaining the tail of the linked list explicitly, but you can maintain if you want, I can also do a direct insertion at the head, right? So that means we can say, okay, this node 4 will refer to noodles and noodles will connect here. So right now this is connected here. So what I can do, I can ask noodles to connect with dosa, right? So I can say n dot next. So in every node I'm also going to have next field, right? So that I can actually form a chain just like a linked list. So every node is going to have a next field. So I can say, okay, you should connect here, right? So I can say n dot next should be equal to array of index. So array of index is storing 150. So that 150 will be copied here, right? And now I can update array of index to point to this node. So I can say array of index should point to n. So basically I'm changing this connection like this. So n is whatever it is. So this will be now referring to this node. Now if you look carefully, we have actually formed a chain, right? So this is, let's say this is some address, let's say 480. So this is now storing 480, right? So you can see we are actually forming a chain, right? We are actually forming a chain. So this is exactly how the insertion is going to work, and this is the code to insert, right? Do you think will it work in order one time? Absolutely yes. this insertion will be always order 1, right? Because we are inserting something at the head of the linked list, irrespective of the chain length, the insertion will be always order 1, right? So I hope you have understood insertion, but is it done? The answer is no. We are not yet complete, right? We have to still discuss one more concept, but that concept I will discuss after discussing searching. Okay, so this is still not complete. So this is insertion part 1, right? Okay, so there is something more to the insertion that is going to come up, right? Let us discuss searching, how we can actually search in such a scenario, right? So we are discussing searching now, right? So now what is the purpose of searching? The purpose of the searching is that given a key, I want to look up for the value of that particular key, right? If I ask, okay, I want to know what is the price of dosa, how I will find it? So first of all, dosa is a key. This is given as input. So dosa will go to the hash function. The hash function will generate an index where this dosa can be present. In this case, hash function gives me an index 4. That means now at index 4, I actually have a chain, right? If I write it little more clearly, so this chain looks like this. I have noodles, and which is like 120, and I have dosa, which is part of the chain, and this price is 100, right? And of course the next is null. Now I have to iterate on this chain to check if this chain can contain dosa or not. So if I iterate on this chain, I will find dosa at this particular position, and once I find dosa, I can return the value that is 100, right? That is how searching is going to be performed. So we first find the bucket where the hash function is telling me, okay, in this bucket you have to check, and in this chain dosa can be present, dosa may not be present, right? Now you might ask, okay, if we have to iterate the chain, then what is the time complexity of this operation? So my answer is it will be order of chain length, right? Now how do we figure out chain length? Okay, can this chain length become very large? The answer is yes, it can become very large, right? So the key to successful search operation is that we have to ensure that this chain length is very small. Okay, so we have to ensure that chain length is very small, right? Maybe 2 to 3 nodes, or maybe 3 to 4 nodes, right? And this is achieved using a concept called as rehashing and load factor. So we will discuss this concept. Ensure that the chain length is very small. So if the chain length is very small, we can say, okay, on an average this operation will be order 1. Maybe I say, okay, the chain will have only 3 nodes, 2 nodes, right? But now let us discuss how this chain length will be decided, right? How this chain length will be actually decided, right? Now suppose I have a hash table where I have 7 nodes only, right? And I keep on inserting data, right? So if I say, okay, my table size is 7 and I insert 70 key value pairs inside it, right? What will be the average chain length? If I talk about the average chain length in this case, so I can say, okay, I have done 70 insertions across 7 buckets, so it will be 70 upon 7, that is 10. So 10 is a big number. I do not want to keep this much chain length, right? So this quantity that I've just written here, it is actually called as load factor. So load factor is a technical term for the average chain length. Okay, so how do we compute load factor? So we say, okay, total number of key value pairs that have been inserted into the hash table. So total key value pairs I have inserted upon my table size, or in other words you can say current size, the number of key value pairs that have been inserted upon table size. That could be another way of writing it, right? So I write, this one looks little more better to me. So in the current scenario, if you have 70 key value pairs inserted in 7 buckets, this is 10. It is actually huge, it's bad, right? So what do we need to ensure? We need to ensure that our load factor does not exceed a certain threshold, right? So in some languages it is 1, in some languages it is 0.7. So whatever is the case, we need to ensure that it does not exceed the threshold value of, let's say, 0.75, right? Now what does it mean? So if I have, let's say, 10 buckets and I insert 7 key value pairs. So what will be the load factor? It will be 0.7. That means on an average, every chain has less than one node, right? So that also means that my table size will be slightly bigger than the number of keys I want to put. So if I want to put, let's say 100 keys, then my table size could be of the order 150, right? Something of that sort, right? So that is something we need to ensure, right? Now, how do we ensure that our table grows dynamically as the data in the table is increasing, right? So one thing you can do is, if you have an idea that, okay, I'm going to insert somewhere around 70 keys, you can initialize your table size um, around 100. Okay, so generally it is a prime number, right? So if it could be like 103, something of that sort, right? Or 107, right? So you need to ensure that if it is a prime number, it ensures slightly better distribution, right, of the keys, right? So what I'm going to do, I'm going to do insertions, and I'm going to show you how the load factor is going to change and what happens if the load factor exceeds the certain threshold. So going back, I'm going to discuss the insertion logic once again, and now apart from doing the insertion in the chain, we will also discuss the concept of rehashing and how do we increase the table size dynamically. Let us talk about rehashing according to the load factor. Let us talk about rehashing, right? So rehashing is a mechanism that is going to help us expand the table size and bring down the load factor. Let us try to understand insertion and the rehashing procedure with the example. Okay, for example, now suppose I have a table which is of size 7, 0, 1, 2, 3, 4, 5, 6, right? Now I'm going to insert certain key value pairs inside it, and I will calculate the load factor during the insertion process. For example, I insert A, right? So the locations are decided by the hash index. So now the load factor will be 1 upon 7, which is 0.14, right? Which is well below the threshold. Okay, so our threshold is, let's say, 0.75. So it is below the threshold. I will not do anything. That means on an average, every bucket has 0.114 elements inside it, right? If I say, okay, I will insert B, maybe it goes here. Now my load factor is 2 by 7, which is about 0.28, right? Then I insert C, maybe a collision happens and C goes here, but then on an average, each bucket has now 0.42 elements, so it is 3 by 7. That is my load factor, right? And maybe I insert D, so it's going to be 4 by 7, right? So it's going to be around 0.56, right? So it's around 0.57 on the calculator. And similarly, if I insert, let's say, E, maybe E goes here, right? So it is 5 by 7, it's going to be around 0.71. It is still below the threshold. Then if I insert the sixth element, maybe F, it goes here and it collides, right? So it's going to be 6 by 7, which is around 0.85. Now at this point, what do I see? I see that the load factor, right, has reached 0.85. That means it is close to 1. That means on an average, every bucket has around one element each, right? It is the time to grow the table, right? So what is a table? This is my table. I want to grow this table. I want to make it bigger, right? So what I will do, I will create a new table or a new array, right, which is approximately double of the given size, right? So maybe this table size was 7. So I generally look for a table size which is a prime number, right? So this new table size could be, let's say, 7 into 2 is 14. What is the nearest prime number close to 14? It could be 13 also, it could be 17 also. Let's say this is 70, right? So I'm taking the next biggest prime number, right? Now what I will do, this table is empty, right? This table is empty, and my goal is to remove all the entries from this hash table and put it into this hash table. Now you might ask, why can't we use this hash table, right? The reason being, your table size has changed and your hash index that we saw, right? So we saw it was a weighted sum. Okay, it was a weighted sum of the letters of the string taken mod with the table size. Now table size has changed, so my hashing will also change. That means if I now insert A, earlier it was going at position 1, Now it might go at some other position. So A might go here, C might go here, B might go here, and D might go here. And since the number of buckets, they have also increased, that means my distribution uh, will also change, and it is possible that the number of collisions that are happening, they might reduce, right? So what I have to do, I have to do rehashing. So this is what rehashing is. So we have created a table of size double the capacity, right? And we iterated over every chain in the original table. Every node we added again into the hash table. So once we are done, what we will do, we will delete this from the memory. This will be cleared off, and now my hash table is going to refer to this table, right? Now in this table, if I compute the load factor, okay, if I compute the load factor now, this will be much lower than 0.85. Why? Because it was now 6 by 7. Now this will be 6 by 17. So if I calculate this value, 6 upon 17, this value comes out to be 0.35. 0.35, right? So I can keep on adding more entries into this table, right? Again, if again it exceeds the threshold, what I will do, I will execute rehashing once again, right? Now what I'm trying to say is that this rehashing is a special mechanism that will be triggered from the insert method when my load factor exceeds the certain threshold, right? So it will be some condition like if my load factor exceeds the certain threshold, I will have to call the rehash method from the insert function, right? So this is something I will show you in the code as well, right? But I hope you're understanding the reason of rehashing, right? What is the importance of rehashing? So if we have done rehashing, right, can I say the average chain length will be always less than 1? That means on an average, no bucket has more than one node, right? So it might happen that some buckets may have 0 nodes, some buckets may have 2 or 3 nodes, but I'm going to say this average chain length will be a very small number, and it can be treated as constant. So that is why we say that our search is order 1 on average, right? Order 1 on average, right? That is what my search operation will be, right? Now another point, what is the complexity of rehashing, right? So of course we have to iterate on the entire table and put all the keys into the new table. So it is going to take order of n time, right? Then how my insertion can be order of 1? So if you look carefully, this rehashing is not happening again and again. So it is happening once in a while. So you inserted this element, we took order 1 time. This element, it took order 1 time, order 1 time, order 1 time, order 1 time, and at this point we saw that load factor is increasing and it is going to trigger the rehash function. So it is going to hit order of n time, right? So can I say that for 6 elements I spent it constant time, but for one element I spent order n time, right? So if I talk about on average how much time I spent on each element, so again if I take an average, it's like a worst case, right? Inserting 6 is like a worst case. Worst case, yes, it can go order of n, but on an average we are spending order of 1 time in doing an insertion, right? You might ask, how can I bring down the time of rehashing? So if you know that, okay, I am going to insert about 500 keys, so you make sure in the beginning that your table size is big enough so that rehashing is never triggered, okay? Or it is triggered very, very rare, right? So the correct way to do it is initialize a large enough table. Okay, it should not be too big that you're using too much of memory. So you have to make a balance between effective memory utilization. So you should know from the historic data, okay, how big table should be sufficient. So if you're storing phone contacts, you know, in general people might have 500 to 1000 contacts. So you can initialize a table of the size around 1000, right? So it is just large enough so that rehashing is never triggered, right? Or it is triggered maybe just once, right? It is never triggered, right? So this is something we can do, right, to make sure that almost every insertion is order 1, right? So I hope you understood the concept of rehashing, and I'll show you in the code as well. Let us discuss the implementation of hash table. So I'm using C++, but you can also use Java or any other language. to map the same functionality in your own language, right? So first of all, I discussed that hash table is a table, and in this table is going to contain the address of it is going to contain the head of the linked list. So linked list is made up of nodes, so a node will store key, a value, and the next field, right? So that is what I've defined in the node structure. So I'm using templated classes, so it's like generics in Java and templates in C++. These templates allow me to hold data of any t type in my node, right? For keeping things little simple, I'm assuming that my key is always a string, but it can be of other data types as well. For that also you need to use templated classes, and you need to provide a way to convert that data type into a hash index value, right? So for now I'm dealing with strings only, but I'm saying the value can be of any type. It could be int, it could be string, it could be float, because we are not computing any hash on the value. We are just going to store that value as it is. And third thing is the next property, that is of the node, right? Whenever I initialize the node, I set the value of key, I set the value which is the value, and by default I set the next as null, right? And this is my constructor. And if I want to delete a node, so this deletion will happen if I am deleting a certain value, or I'm doing rehashing and I want to delete some data, right? This is actually a destructor which says that if next is not null, delete next. So basically it is a recursive way of deleting the node, right? So that means if I make a call at this point, it says, okay, if I'm going to delete this node, and if the next is not null, first delete it. If the next is not null, first delete it. So it's a way in which I can delete the entire chain at once, right? So this is something which you can also, like, uh, it can be implemented in other way also, right? So you might not necessarily do the same thing, but in my case I'm doing it. I will tell you why, right? So that is about the node constructor. And now let us come to the hash table class, right? So what I have done, I am actually keeping a dynamic array called table. So table is referring to an array, right? So you might ask why star star, because see, each bucket in this array is going to hold an address of the node, so it is of the type node star, right? And what is table? Table is a pointer to an array of pointers, right? Because each bucket is going to point to the head of the linked list, so each bucket is of the type node star, hence the type of the table is node star star, right? It is going to be a dynamic array referring to an array of pointers. Okay, so I have a table which is not initialized at the moment. I have current size, I have table size. So current size will be 0 in the beginning. So I will show you the constructor for this. Yeah, this is the constructor. So whenever a new hash table is created, right? So current size is set to 0, table size is set to default size. I'm taking a parameter with the default value of 7. So if user gives me, let's say I want a table size of 107, it will be 107. But if nothing is given, by default I'm taking it very small and it is 7, right? Then I initialize my table array. So table is an array that points to an array of node star, and this is of size table size. So these many buckets I have initialized, and by default in every bucket I'm putting a value null, right? So this is null, this is null, this is null, right? So instead of having garbage, it is better to initialize everything with null. That is how that hash table has been initialized. I hope you don't have any doubts till now. Now comes the interesting method, that is insert, right? Now if I want to insert something, right? So my table is ready. So table is here. My hash function is also ready. Okay, I'll show you the hash function. Let's say I want to insert dosa comma 100. What do? I will show you the hash function. Let us understand the insert. So my key, that is dosa, it goes through the hash function and I get an index. So maybe the index is 4, right? So at this index, what do? I will create a new node. So I say, okay, there is a new node called n, which is dosa comma 100. In this line, I do this work and I say n dot next, this is equal to table of index. So table, and this is index. So n dot next will point to whatever this is pointing to. So it is currently pointing to null. So the next starts pointing to null, right? Then I say table of index is equal to n. So this index is going to hold the value n. So n is, let's say, 248. That is the address of this node. So it is going to store 248, right? So this is how this node gets attached to the beginning of the table. Current size plus plus. So current size becomes 1. Then I compute load factor, so which is 1 upon 7. Is it greater than 0.7? The answer is no, right? So if it becomes, then I will trigger rehash. I will show rehash method also, right? So this is about the insert functionality, right? So I hope you're getting it. Let's say I'm inserting one more node which at the index 4. So I just want to show you how the chaining is going to work. Let's say I inserted noodles, and for noodles also I got an index 4. So noodles comma 120. I created a new node called n, right? Then I said n dot next is equal to table of index. Table of index is storing this value. So noodles starts pointing to this value, right? And table of index is equal to n. So this connection is broken and this starts pointing to this node, right? So you can see in a way we are forming a chain in which noodles is getting inserted at the head of the linked list, right? So this is nothing but insertion at the head of the linked list. Current size plus plus. So current size is 2, load factor is 2 by 7, which is again less than 0.7. So hence I do not trigger rehash at this moment, right? So I hope you understood the insert method. Next I want to show you the hash function that I've used here. So hash function, I've made it as a private. So what I'm doing, I'm simply multiplying the numbers. Let's say the word is dosa. What I'm doing, I'm iterating over this and I'm multiplying it with powers of 29. So it is 1. So initially it is multiplied with 1. Then in the next iteration, power becomes into 29. So into 29. Next time it becomes, power becomes again power into 29. So it gets multiplied with 29 square. And again it becomes 29 cube, right? So in order to avoid overflow, I'm doing a percentage mod at each step, because if you take mod at the last or if you take mod at each step, we know this is the property of mod. So mod can be taken at each step as well. So this is a better thing to do because it helps us to avoid overflow, right? I'm taking a mod with power also, and I'm taking the mod in the answer also. So I get an index which is in the range 0 to table size minus 1, because I'm doing a mod with table size. So I hope you understand the hash function as well, right? Now what I need to do is I need to understand the rehash method, right? So if we understand the rehash method, our insertion will be complete. So I have written a rehash method as well, which is actually a private method as well. So what I'm doing in my rehash method, that suppose I have a old table, like the actual table. In this I have inserted some keys. Let's say A, B is there, C and D is there. What do? I say, okay, old table is going to point to table. So this was my table. Now old table is pointing to this table. I create a new table, okay, which is almost double of the previous size plus 1. I'm just making it as an odd number instead of making it as a prime number. So I'm saying this is my table now, which is also the data member of the class, right? So what do? I initialize it with null. So all these values are set to null. And then what I do, I copy elements from the old table. So I iterate over the old table. And how do I do the work? Let me show you. So I do it like this. I take a temp variable, which is the ith row. So temp starts from here. Okay. Temp is referring to the head of the linked list. And while temp is not null. So I copy the key, I copy the value. So I say, okay, give me this key value pair, and I call the insert method. So insert method, we know by default it acts on the table, which is the data member of the class. So it is going to insert automatically in the new table, right? And temp goes as next. So temp comes to this node. Again, I copy B, I insert it in the new table, right? So once it is done, I make a destructor call. If old table of I is not null, delete old table of I. So in Java, there is a concept of garbage collection, but in C++, we have to use explicitly, we have to invoke the destruction of this entire linked list by saying delete old table of I. So I initiate a destructor call from here, which makes a call to A. A is being a recursive destructor, A makes a call to B. This way, this entire row is deleted, right? And then I go to the next row. So my I is increasing. So I go to this row, this row, this row, this row, this row. I do the same work and all the nodes are inserted in the new table. And finally, I say, okay, I want to delete the array that is old table. So I also want to clear up this memory. So I say delete old table. This old table is gone. And since it is a local variable, this is also destroyed, right? So till now you have seen the insert functionality, and we discussed that the function rehash will be triggered from the insert whenever load factor exceeds the threshold. Okay, so we basically double the table size here, right? Now let us talk about searching a little bit. How do we actually do searching in a hash table? So searching is pretty easy. So if you have a hash table, right, and you want to search for a certain key, let's say dosa, so that key will go through the hash function. The hash function will tell you the bucket. So maybe this is the index of the bucket. And in this bucket, there might be a chain in which dosa could be one of the item, right? So maybe this is some X item, some Y item, some Z item. So you need to iterate on this chain linearly, right? So I start temp from this node. While temp is not null, while I do not hit the end of the chain, I compare is the key of this node matches with the given key if I'm searching. So if that happens, I return the value. Otherwise, I go to the next node. If I hit end of the chain, that means I did not found the key, so I return null in that case, right? This is how searching is done, right? So on an average, what we are saying that this chain length is so small, right? Because of the rehashing and the load factor that we are maintaining, right? So we can say, okay, iterating over a very small linked list will take order one time on average. Okay, so we are not talking about the worst case. A worst case scenario might be like this. A single bucket has all the n nodes inside it, right? So basically chain length is of the order n. But this is a very less likely scenario because this can be only possible if your hash function is too bad. It is producing the same bucket for many different types of keys. Okay, in general it's not going to happen. So that is why we say on average it's going to be order one most of the times, right? So I hope you have understood the search functionality as well, right? On a similar lines, you might have to do erase as well. You might want to delete a particular key as well, right? Now how you have to do it? Now this is pretty simple. If you know how to search, then you can also know how to delete, right? So suppose I want to delete a key that is y. What I will do, I will pass y to the hash function. It will give me the index. I'll find this linked list. Now the problem boils down to deleting this node from the linked list. Now you have to handle these cases. This node could be the last node in the linked list. It could be middle of the linked list. It could be beginning of the linked list, right? So if you know deletion in a linked list, you can easily handle the code to erase a particular key value pair from the hash map as well. So I hope you have understood the fundamental methods associated with the hash map, insertion, deletion, and searching.
Okay, so today we are going to study a very important data structure. This is going to be very handy, which can reduce the time complexities of many problems significantly just by adding a little bit on the space side. Okay, and this is called a hash map or a hash table. Okay, and the whole process is called hashing. In today's class, we are going to study some basics of hashing, how a hash table functions, and we'll also discuss some problems which have been asked in the interviews, and we'll see how you can solve these problems optimally using a hash map or hash table. Okay, I have a question for you guys. Have you ever encountered hashing in your real life? Hashing, have you ever faced any practical scenario where you have used hashing? Let's talk about those days when there was no corona, or let's call it the pre-COVID era. Let's talk about the pre-COVID era. So during the pre-COVID era, we used to go out on holidays, right? We used to go for trekking. We used to go to visit different places, right? And whenever you go to a different place, you need to stay in a hotel, right? So let's say that if you go to a hotel and if you want to look for a room, right? You go to the receptionist and ask whether a room is free or not. Now the job of the receptionist is that he will take all your preferences. He will ask you what type of room you want, and then based on your preferences, he will just check whether a room of those preferences is free or not, right? So you go to a hotel, and in this hotel you have a receptionist, right? And you go to the receptionist and you ask for a room. Give me a room which, let's say, is a single bedded room, has a AC, has a balcony and all, right? And this guy will just check whether a room is free or not. Now this guy has got two ways to check the room. First is that he can actually go and he can visit all the rooms of the hotel and check whether such a room is present or not, right? He will go, he will knock each and every door, he will check whether the door is closed or whether the door is open, whether the key is with him or whether the key is with the person who has taken the room, right? So this is one way. Now, as all of you can see that this is a very, very unoptimized way of finding a room, right? Because if there are, let's say 200 rooms in this hotel, if this is a very big hotel, then he is going to check each and every room for each and every customer, right? So if there are n customers and if there are m rooms, then how many checks is he going to make? This unoptimized receptionist is going to make n into m checks. This is not going to be profitable for the hotel business. Whoever is the owner of the hotel, he will fire him the next day, right? The other way that this guy can use is he can maintain a map, right? He can just against each and every room, right? Let's say room number 101, 102. He can maintain whether this room is occupied or whether this room is empty, right? Or he can also have the keys in the key holder itself. He can also have the room number written, right? So now whether he has the key or not, that is also visible here. Whether the room is empty or not, that is also visible here. He can also have the type of the room written here. So he can have that 101 is a single bedroom which is empty. 102 is a single bedroom which is non-empty. Let's say 202 is a double bedroom which is empty, right? So he can have each and every information regarding the room stored against the room number. Okay, is this going to be a better choice? Yes, right? That is why each and every receptionist actually does this. You must not have seen any receptionist who actually go and check all the rooms, right? But this is something which you all must have seen, correct? Let's talk about another example. Okay, so let's say that in those days we also used to go to shopping malls, right? So this was an example when we want to stay on a hotel. Another example would be that if I want to go to a shopping mall. Okay, now if I want to go to a specific shop in the shopping mall, again there are two ways, that either I go and check each and every shop in that mall, right? So there are going to be multiple floors in that mall, right? Each floor will have different shops, right? And let's say I'm looking for a specific shop. Okay, let's say I want to buy the magical drug Coronil. Okay, I have a perception, I have read on WhatsApp that if I take Coronil, then Corona is not going to catch me, right? So what I would want is, I would want to search this shop which is selling this drug Coronil, right? Now again, I have got two ways to do this. First is that I go to each and every floor and I check each and every shop one by one, right? Or some of the malls who have a logical owner or who have a logical management, what they do is they put a board or a map of the mall, right? So what they do is they put shop number, they give the complete address of the shop, floor wise. They will say that in the first floor, these are the shops which are there in this order, right? And in the second floor, these are the shops. So what I can do is I can use this map and I can find the exact location of that shop, and then I can go to that shop, buy this drug, and then I can make sure that Corona is not affecting. But since this was a knowledge that I gained from WhatsApp, this might not be true, right? But this way of searching the shop, this definitely is a better approach, right? Instead of visiting each and every shop, what I'm going to do is I'm going to check this map and then find the exact location of the shop. Okay, does this make sense to everyone? These are two examples which all of you must have used, like these or something like this in your real life, right? Where you have to keep track of things and you just create a table or you create some entries and you just mark true false, or you just the attendance register that we have that we used to have in our school classes, right? That was also an example of hashing. if let's say a teacher wants to know whether a student is present in the class or not, right, what he will do is he will just do a linear scan on all the students, and doing this linear scan while taking the attendance, he also marks the attendance, right? So if there are students, let's say in our class we have Aman, then we have Monica, then we have Anmol, right? So if I have to check whether all of these guys are present in the class or not, what I can do is just before beginning the class, I can just mark their attendance, right? Now, if let's say after some time I want to know who all were present in the class, I will not do another scan. I will just check whether Monica is present, whether Aman was present or not, right? So this again is another example of hashing which we have been seeing from the school days, right? Okay. Is OYO also used concept of hashing? Yes, OYO must also have used this same concept, right? Okay, so this is the general idea of hashing. Now let us see how it actually functions in the world of computer science. Okay, so let's try to understand this whole process using an example. So let's say that we are given an array, and this is just to understand how hashing is going to function. Okay, this is going to be a very easy example to understand the working of hash maps and hash tables. Okay, so let's say that you are given an array, and in this array you have all the numbers from range 1 to 1000. So you know that any number in this array is going to be from or let's say from 0 to 1000. Okay, so you're given an array of size n, and each and every number of this array ranges from 0 to 1000. Okay, you have to return the frequency of every number. Let's say you have got queries about the numbers. Okay, so you have this array, and now you are getting multiple queries. You have to answer these queries, and each query asks you the frequency of a number. Okay, so for example, if the array is something like this, okay, if this is the array, after getting this array, you will get multiple queries, and you have to answer what is the frequency of the given number in that query. So for example, if your query has 58, you will return 1 because 58 occurs only single time. Then if let's say you get 3 in the query, then you will be returning 2 because 3 is occurring twice in this array. If you get 2, you will again be returning 2 because 2 again occurs twice in the array. Okay, is this scenario, is the problem clear? How can we solve each and every query in the most optimal time? Okay, let us start from the brute force. Okay, what is the brute force way to solve each and every query? The brute force way to solve each and every query is that whenever you get a number in the query, you iterate over this complete array and you count the occurrences of that number, right? So if I get 58, I will do an iteration over the complete array, which is going to be an order n operation, and then I will return 1. If I get 3, I will again do another order n operation over the complete array, and I will return 2. Okay. So what is the total time complexity of, if I go by this approach? Let's say there are q queries. Solving each query takes order n time. So the total time complexity is going to be q into n. Right? Now this q can be very, very large. Okay. So this is something which is not optimal, right? Any other approach that we can use in this case that you might have studied in the previous classes? Can we optimize this order n factor here? Let us say if I do some pre-processing, okay? If I sort the array, what happens to the order? Now the order is the array sorted in ascending order, right? Now can I find the frequency in a more optimal time? Can I reduce this factor of n? Yes. Now how can we count the frequencies? Now we can use binary search. You must have studied this, you must have learned it in the previous sessions, that given a sorted array, you can count the number of occurrences of any element using binary search, right? You can just find what is the first occurrence of that number using the binary search. Then you can also find what is the last occurrence of the number, and then you can get the length of this subarray, right? So if you use binary search after sorting, then each and every query is going to take how much time? Only log n time, right? So now what is the total time complexity of finding all the frequencies. So if you have q queries, then solving all the queries is going to take you q into log base 2n time. This much is the time that you will invest in resolving each and every query. But before this, you have also sorted the array, right? So that amount will also be counted. Now, whichever is the greater of these two will be the overall time complexity, right? This still is a lot because again, n can be very large, q can also be very large, right? So can we further optimize this? Right. So as many of you have already suggested, what if I have another array, right? So I can see here, if I focus on the constraint of the problem says that any array value is going to be in this range strictly, right? Any array value cannot be more than 1000 and it cannot be less than 0, right? What if I just have another array where each and every index of the array represent the numbers and the value in the array represents the frequency of a number in this original array? So what if I have another array and just call it a frequency array, right? And store and count the frequency of each and every original array element in this array, right? So I can have another, let's say, frequency array of size. What should be the size of this array? What should be the optimal size of my frequency array? If I know that all the numbers are going to be in the range from 0 to 1000, I know that the maximum number that I can have is 1000. To have 1000 as an index, I need an array of size 1001, right? 1001. This array is going to be, this array can accommodate all the numbers from 0 to 1000 in index, right? So now what I will do is, whenever I am iterating over this array, so initially I initialize this complete 1000 sized array by 0. So in this array, initially I have 1000 zeros in every index, right? And then whenever I visit a number, I will just loop over this array. And whenever I visit a number, I will increase the value here, right? Because this denotes the frequency. So initially I am assuming that frequency of each and every number is 0. Whenever I encounter a number, I will increase the frequency, right? So I will just loop over this array. I will say for I equals to 0, I less than n, which is the size of the given array, I plus plus. And I will say frequency of a of I plus plus, right? If I just do this, what will I get? In this array, frequency of 1 will be increased to 1, right? And then frequency of 2 will also be increased and it will be 2. Frequency of 3 will also be 2, and so on, right? So now, after I have built this array, if I have to return what is the frequency of any given number, right? What is the operation that I have to do? After I have built this array, for any number I, for any given number I, if I have to return what is the frequency is nothing but frequency of I. So if I have to return what is the frequency of 58, I will quickly do frequency 58. If I have to return what is the frequency of 2, that is going to be frequency of 2. And that's it, right? So what is the time complexity of this operation? Time complexity of this operation is constant, right? This is a constant time operation. I'm just retrieving a value from the array, right? So this is going to take order 1 time, correct? Now I have q queries and each query is being solved in order 1 time, correct? So what is the overall time complexity of solving all these queries? Overall time complexity becomes order q, because each and every query is taking how much time? Only order 1 time, right? So this is the time to resolve each and every query. And then we have also built this array, right? So we have iterated over the given original array, and then we have also built that array. So this takes order n time. Order n plus q, whichever is greater will be the final time complexity. Okay. Does this make sense to everyone? How we have solved this, like optimize the time complexity from n square to n log n plus q log n to order n plus q. Okay. Now, one of you just asked what happens when array elements range from 1 to 1 raised to power 10 raised to power 18. Okay. What if, so in this problem, it was given to us that the numbers are going to range from 0 to 1000. That is the reason why we are able to create an array, right? I can create an array because I know that indexes can be in this range, correct? Now, what if the numbers are going to be very large? Okay, A of I, as asked by Lucky Movies, what if the range is this? Can I use the exact same approach? So now I cannot use the exact same technique because I cannot have an array, I cannot create a frequency array which has a size 10 raised to power 18, right? Because this is going to cost me a lot of memory, right? How much memory is it going to cost? If this is an array of integers, one integer takes how much memory? 4 bytes, right? So if you want to create an array of size 10 raised to power 18, this is going to cost how much time? How much memory? 4 into 10 raised to power 18 bytes. Can anyone quickly tell me how much is this in GBs? 4 into 10 raised to power 18 bytes. How much is it in GBs? So if you want to create an array of that size, you need to have this much of memory. You need to have this much of memory in the RAM, right? So this much of memory in the RAM is definitely not going to be possible for an ordinary computer, right? So what we are going to do is, now we'll have to be a little more logical and we'll have to apply a little more mind, right? Unlike Mumbai police. So let us be a little more logical and let us try to see if we have an upper limit on the memory, right? If let's say, let us take a smaller example and let's say that the numbers are ranging from, just to understand, let's take the smaller example that the numbers are again ranging from 1 to 1000, but the largest array that I can have a size of 100. This is the upper limit on the size of array. Okay, similar example. So what we are doing is, numbers are ranging from this 1 to 1000, but the maximum size of the array can only be 100. Right now, again, I cannot use the exact same method. Why? Because having an array of size 1000 is not possible, right? So if I want to store the numbers as an index in the array, then I can only store till 100. Is there a way using which I can map all these numbers from in this range from 0 to 99, because the maximum size that I can have is 100. So can I map all these numbers in this range? Is there a way? Have we seen any way? Or let's say that all these numbers are ranging from 0 to 1000, right? Yes, what can we do? We can simply take modulo, right? Is everyone familiar about what is a modulo operator? This gives you the remainder, right? So if I take modulo of any number ai with 100, which is the maximum size of the array that I can have, can I say that this number, which is ai modulo 100, will always lie in the range from 0 to 99? Can I say this? Yes, correct. So I have got one way to map these numbers which are in this range from 0 to 1000 to a range which is very, very small, right? This range has a length 1000, 1001, and now the resulting length is only 100. So I am mapping these 1000 numbers to 100 numbers. Okay. If this is the case, how am I going to store the numbers? Let's have an example. Let's say I have 492, 5, 8, 23, 15, 142, and some random numbers. Okay. And now if I can only afford an array of size 100, right? How can I map these numbers? I will first take the modulo of these numbers with 100. And then whatever number I get by doing this operation, I will store these numbers in that index. So I get the index by taking modulo of these numbers by 100. So first number will be stored against index 92. This will be stored against index 5. This will be against 23, 15, 42, 54, and 64, right? So if I have these as the array index, 54 and so on till 99, Then at 0 is going to be empty, 1 is empty, 2 is empty. At 5, I am going to have 5. At 23, I will be having 823. At 42, I will be having 142, and then 654, 764, and so on, right? So now, is this going to work? Is this going to work correctly? If these are the indices and these are, and I keep the values in array element mod 100 index. Okay, now some of you are saying that this is going to work, but there can be collisions, right? What are collisions? Okay, so let us say that in the array, in the original array, I have these numbers 100, 201, then I have 302, then maybe 300, 401, 200, right? If I have these numbers, right? So in which index should a number belong? In index 0, how many numbers am I going to have? In index 0, I am going to have 100. Then I am also going to have 300, and I am also going to have 200, right? All these numbers will try to get inserted against a single index, right? These are called collisions when there are multiple prospects candidates for a single index, right? So index 1 will try to accommodate 201, then 401. Index 2 is going to have 302, and then 2 also, right? So there is no one-to-one mapping, right? A one-to-one mapping does not exist, correct? If a one-to-one mapping does not exist, is this even possible to use this technique? Are we going in the wrong direction? Is this a correct way? Is this the correct path that we are taking? Maybe, right? We have also studied a data structure called linked list, right? If you know about a linked list, what if we have an array of linked lists? If I keep an array of the linked list nodes, right? Can I say that this can work in that case, right? So currently, if you are only storing a single element, if you are only trying to store a single element against one index, then since there is no 1:1 mapping, this will definitely fail. We are going to lose some data, right? Because every time you have a collision, the previous number will be overwritten. But what if I use a linked list? So instead of having these integers, right? If at index 0, I have this complete linked list stored. So if I have to create an array of linked list, what do I need? I only need the pointer to the head stored in that correct index, right? Only if I have an array like this where I have this head pointer, then using this head pointer, we can have the complete linked list, right? So we don't need to actually store this complete linked list in the array. We only need to store the head pointer, right? Similarly, at index 1, we can have the head pointer of 201. At index 2, we can have the head pointer to 302. Does this make sense to everyone? So we can still manage doing hashing in this case. Even though the range which we have to store is very large, the size of the array is very small, but we are making sure using the modulus operation that we are mapping these numbers to the available size. And then using a linked list, we can also make sure that we are not losing out any data, and we are storing all these numbers using the chaining. Okay. Now, if I'm storing the values like this, now if I have to find what is the number of frequency, or let us say if I just want to check whether a number is present or not, right? What is the worst case time complexity of this case? If I'm going by this approach, if I'm storing linked list, if I'm having an array of linked list nodes, what is the worst case time complexity of finding whether a number is present in the array or not? Worst case is going to be if all the numbers are mapping to a single index, right? So if let us say that the numbers are these 1, then you have 401, then you have 101, then you have 601, right? 701 and 501, correct? If I take mod of all these numbers with 100, all of them are going to take the exact same key. So all of them are going to map against 1. So what will happen now? If I have to search whether a specific number is present in this array or not, I will be traversing this complete linked list, right? So first, let us say I get a query. I get a query of, let's say, 801. I have to check whether this number is present or not. So first of all, I will try to see in which index is this number is stored. So I will just do 801 mod 100, which is going to be 1. So I go to index 1 of my array. And now I have a linked list of size n. I will iterate over this linked list, and since this is also not in sorted order, right, I will have to check each and every element, and I will then figure out whether I have 801 or not, right? So this is going to be a order n time complexity operation. Does this make sense to everyone? This is the worst case time complexity of checking whether the number is present in this list or not, right? Okay, so this is the worst case. What could have been an ideal case? When can I say that this is the best thing that I want? What is the ideal case in this scenario? The ideal case would be that if all the numbers are mapping to different index, if all the numbers, if I have a data and like if I have the data in such a way that all the numbers are distributed evenly amongst all the index, right? So if I, let's say, have 401 against 1, then I have 2. So let's say I have 702, and then I have 23, so I have 823, and I have exactly one element for each and every index. This is going to be the ideal case. And what is going to be the time complexity in this case of just finding whether a number is present or not? Since the list size in each and every case is exactly 1, the time complexity is going to be constant, right? So this is the best case time complexity, and this is the worst case time complexity. Is everyone clear about these two? Okay, great. So the aim is that the mapping function that we are using, right? Currently the mapping function is mod by the size of the array, right? So the aim should be that whichever mapping function we are using should try to evenly distribute the load amongst all the possible indices, right? So this function, the mapping function that we are using, this is called, what is it called? Anyone knows what is the name of this function? This is called the hash function. Okay, and hash function is a very, very big topic in itself. There is a lot of research going on. There has been a lot of research already done on what could be a better hash function or for what case, right? So you can just go and Google up and read about hash functions. There are multiple publications on these. You can read, you can go through some of the publications if you are interested, right? But taking a mod, this is the most simple hash function that you can have, but not the most optimal. Right? This was just for the example. You have very complex, very optimally written hash functions which try to distribute the load evenly. Okay, so you can just go back and read about what are hash functions, and you can also read about some of the common hash functions. Okay, cool. Now, if I write one of the best hash function, even which is the best possible hash function currently present in this world, can I say that hash function will guarantee zero collision? Can there be any hash function which can guarantee zero collisions? No. Why? Why no? You have got a very big range of numbers, right? You have to map numbers from, let's say, 0 to 1000. You have got only 100 slots. Do you guys, are you aware about the pigeonhole principle? You have 100 slots and you have to put 1000 things. When you put the first 100 things, and if your hash function is guaranteeing zero collision, 100 slots are filled, right? Now when you pick the 101 index number, this is definitely going to collide with at least one of the pre-existing slots, right? So since you are mapping a bigger list of numbers to a smaller list, you will always have collision. So there cannot be any hash function which can guarantee zero collisions. Okay. However, there are hash functions which try to distribute the load evenly. That is possible. There has been a lot of research done on that. You can Google and read. Okay. Cool. So this is the basics of hashing. Right? You can read about hash functions. You can also read about hash tables. Hash table is nothing but key and value. right? So you must have seen what is a dictionary. If you use Python, you must have used hash maps. So hash maps or hash tables, they are nothing but a key value pair. This key is the result that you get from the hash function. This is a hash code of any value, and in the value you can store anything, right? So the key, as you all now should understand, these keys in this case are the index from 0 to 100, right? So keys are always and always going to be unique. Values can repeat. You can store the values in list or maybe in some other data structure, but keys are always going to be unique. Okay. Now there was a question that if you are using a list, is there any specific reason of using a list, or can we have any other data structure here? What do you guys think? Can we have any other data structure in place of list? So Surit is asking why we use linked list. Is there any specific criteria? Correct. So Komal has got a good solution to that. If I'm using a list, what is the worst case time complexity of searching a list in if you have a list which is not sorted and which is a linear linked list, what is the worst case time complexity of searching in this list? Worst case time complexity of searching in list is order n. Okay. Now, do we know any data structure which provides a better searching time complexity? Is there any data structure which can store the numbers maybe in some order and then can give us a better time complexity? Do you guys know about binary search trees? In a binary search tree, all the values on the left subtree are going to be less than or equal to the value of the root. All the values of the right subtree are going to be greater than the value of the root, right? So just by using a technique like binary search, it can always discard, while searching for a number, it can always discard half of the search space, right? So what is going to be the time complexity to search a number? It's going to be log base 2n. If you are using Java 8, if any one of you who is using Java 8 must know this, that in Java 8, they optimize this worst case time complexity of retrieving from a hash map using a balanced binary search tree. In a normal binary search tree, in worst case, you can also have a time complexity of n if the tree is skewed. But if the tree is always balanced, then you are always going to have a searching time complexity of log base 2n. So in Java 8, what the hash map does it, if the size of the list is till a threshold number, which I don't remember correctly, I guess it's 5 or 6, till then it maintains a list. If the size exceeds the threshold value, then it converts the list to a balanced binary search tree. So the worst case time complexity that we have seen to be order n will reduce to order log n. Okay, cool. So guys, this is in brief about hash maps and how they work. Okay, let us quickly solve a problem also. Okay, in which type of questions can we blindly use hash functions? Okay, in any question where it talks about the frequency or counting the numbers or maybe checking whether a number is present or not, or checking the presence of anything, then you can use hash function, or then you can use hashing. Okay, let's quickly solve a problem and then you will get a better idea of when to use hashing. Okay, so the problem says that you are given an array and you have to check whether there exists a subarray which has sum equals to 0. Okay, so for example, if your array is this, in this case, does there exist such a subarray? Yes, right? If you see the sum of this subarray, what is the sum of this subarray? It is exactly 0. So you can return true. If there exists a subarray which has a sum equal to 0, the subarray can start from any index, it can end at any index, it can have any length which is possible. But if there exists any type of subarray which has sum equals to 0, then you can return true, else false. Okay. Modify cadence algorithm. Okay. How will you do that? Remember that the subarray can start from any point. This subarray is starting from this point. There might be an input where your subarray which is causing a zero sum can be present, let's say here, or the subarray can be present here, or maybe the complete array can also be the subarray. What is the brute force way? If you are not getting any solution, can you quickly write down what is the brute force way? Okay, the brute force way is going to be that you actually try to calculate the sum of each and every possible subarray, right? So you first check all the subarrays of size 1, then you can check all the subarrays of size 2, then you can check all the subarrays of size 3, and so on, right? How many subarrays are possible? N square subarrays are possible. To calculate the sum, what is going to be the time complexity? For every subarray, you will also run another loop to calculate the sum. So it's going to be an n cube solution, right? Which is highly unoptimized. How can we come up with an optimized approach? And we have also studied hashing. Hashing doesn't seem to contribute in this question, right? Okay, let us assume that there exists a subarray. Okay, there exists a subarray which has got sum equals to 0. Okay, so let us say this is the initial array that we have, and there is a subarray, let's say this part, which has a sum equals to 0. How do we define a subarray? We always define a subarray using a range of indices, right? Because as I said, the subarray can start at any point, it can end at any point, right? Let us say it starts at a point L and ends at an index R. And I'm saying that we are just assuming that the sum of the subarray starting from L to R is 0. Okay. Now, if this subarray has got sum equals to 0, right? If I also have the sum of all the subarrays starting from 0 stored with me, okay, what can we say about this part? This part which is in the blue dotted line. What is going to be the sum of this part? The sum of this part is nothing but sum from 0 to R, right? And this sum from 0 to R can be broken down as sum from the range 0 to L minus 1, right? Plus sum of the range from L to R. Does this make sense to everyone? Right? So sum of any subarray can actually be written in terms of this prefix sum, right? I can write sum from L to R is equal to sum from 0 to R minus sum from 0 to L minus 1 index. I can write the sum of any subarray which starts at index L, ends at index R in the form of the sum of subarray starting from 0, which is nothing but the prefix sum. Everyone here understands what is a prefix sum, right? So if I have a prefix sum array P, then I can say that the sum of the subarray starting from and ending at R is nothing but P of R minus P of L minus 1. Does this make sense to everyone? Prefix sum is nothing but, prefix sum is the sum of all the indices till that index. So if I have an array, right, prefix sum at any index I is nothing but, it is the sum of all the elements including the ith and all the elements before the ith. Okay. So if let's say I have an array 1, 2, 3, 4, the prefix sum array would be 1, and then this will store the sum of these 2, which is 3, then this will store the sum of all of them, which is 6, and then this will store the sum of all of them, which is 10. So this is the prefix sum array for this array. If I have all these numbers stored with me already in this array prefix, now I can represent the sum of any subarray in the form of prefix sums, right? And if I'm saying that this sum is equal to 0, if this sum is equal to 0, can I make any comment about these two values? If this sum is equal to 0, this means that prefix sum of R should definitely be equal to prefix sum of L minus 1, right? Let us visualize this in this diagram and then it will be more clear. So I have these two parts, right? Now I am saying that this blue box represent the prefix sum of R. This is the sum of all these elements from 0 to R. Okay, this green, this yellow box, this represents the sum of all the numbers in the range L to R. Correct. And what about this green box? This green shaded box represents the prefix sum of the index L minus 1, the sum of all these numbers. Can I say that if this is going to be 0, right? If I'm adding the sum of all the index from left to right, and if this part is equal to 0, then whatever sum I get at this point, the exact same sum will also be present after this, because the contribution of this is 0. Does this make sense to everyone? Right? So if I have an array, right, and if I'm just calculating the sum of all the array elements till that index, and then there is a part which is contributing exactly 0 amount, right? So this will give some sum, right? Let's say S, this gives S dash, and then if I add this as well, this gives S double dash, this gives S triple dash, and then this gives something. After I am here, I will again get S triple dash, because the overall sum of this part is 0. Does this make sense to everyone? Let us take the example as well, and then this will be crystal clear. So I will just copy this thing. So if I just calculate the prefix sum of this array, I will be getting 4, right? 6 minus 3 again is 3, then 4, and then 10. Okay. Now what I was explaining is, since the sum of this part is exactly 0, this part, the contribution of this part in the sum of all these numbers is going to remain 0, right? That is why whatever number I am getting here will also be repeated here, right? So whatever sum I am getting at this point, which is, this point is L minus 1, right? Because I am assuming that this subarray starts from L. So the previous is L minus 1. And this is the R. These two have to be equal. If these two are equal, this means that this subarray, the contribution of this subarray was exactly 0. All the values cancelled out each other, and we are remaining with whatever we had before starting this subarray, right? So how can we now solve this problem? If we calculate the prefix sum of the array, and then if we observe that there is a number repeating in the prefix sum, can I say that the contribution of all the elements between these two numbers is going to be 0, which means that this subarray is adding to 0. Okay, is the idea clear to everyone? Guys, is the idea clear? Right, let's take another example. Let's say I have 4, 2, 0, 1, 6. Okay, now if I take the prefix sums, I will be getting 4, 6, then again 6, and then 7 and 12. So again I can see that a number is repeating in the prefix sum, which means that whatever comes in between these two, this is, if I said that first number should be L minus 1, this is L minus 1, right? And this number is R. So whatever is from L to R is going to give me a sum equal to 0. L to R here has exactly one element, which is 0. Now one of you asked, what if same number is repeating twice, right? That can also be possible. You will have to understand what is the physical significance of this thing, right? So even in this case, if I just modify this array, here I got 4, then I have 0, then let's say again 0, then I get 2, and then minus 2, and then something, right? Now what will be the prefix sum here? Again 4, 4, 6, again 4, and then 5, right? So this means that all these numbers which are repeating, they all are forming a subarray which is going to give a 0 sum. If these two are repeating, this means that we have a sum 0 here. If these two are repeating, this means we have a sum 0 here, from this plus 1 to this, right? Because this has to be the L minus 1 index. So even if you have multiple repetition, that points to only one thing, that the subarray between them is giving a 0 sum. Okay. Now, how do we solve this problem? So one thing should be clear to everyone, that the first step is that you create the prefix sum array. How can we create the prefix sum array? This is very easy task. You can have P0 equals to A of 0, because the first number is going to be exactly the same. And then for building the rest of the array, you can just keep calculating. You can just keep adding the current value to the previous prefix sum, right? Prefix sum of I is nothing but the previous prefix sum, whatever is the sum till now, plus whatever is the sum of the current element. So now we can run a loop from I equals to 1, I less than n, I plus plus, and then you can say P of I is equals to P of I minus 1 plus A of I. This gives you your complete prefix sum. Now in this prefix sum, you just have to check whether there are two numbers which are repeating or not. Is there any data structure that we know which can solve this problem very optimally? You just have to check whether there are two numbers which are repeating or not. How do you check for a repetition of a number? You can have a hash map, right? Maybe you can have an integer here and a boolean, right? When you get 4, you store true. When you get 6, you store true. When you get another 6, you know that 6 has already occurred. If 6 has already occurred, this means that there is a subarray which is giving a zero sum. If you also want to find what is the length of the subarray, instead of having the boolean, you can try to store the index here. This also becomes integer, and now you can say that 4 occurs at index 0, 6 occurs at index 1, then 6 again occurs at index 2. This means that from this index, this plus 1 to 2, we have got a subarray which is giving us sum equals to 0. Okay, let's take this example which we initially had, this one, right? You can have your key and value. Key is the sum, value is the index in the hash map. You get 4 sum at index 0, then you get 6 sum at index 1, 3 at 2, and then you again get 4 at index 3, right? Now we had discussed, right, that keys are going to be unique. So once you get another same key, you can just check that this key is already present in the hash map and the starting index was 0. This means from 1 to 3, I have an array which is giving sum equals to 0. Okay, does this make sense to everyone? What is the time complexity of this complete problem, of this complete algorithm? First of all, we have calculated the prefix sum. This costs us order n. While calculating the prefix sum only, you can just also enter in the hash map, right? Here only, what you can do is you can do your map dot put, or first maybe you can check if map dot contains pi. This means that you have found a subarray, you can directly return true, right? Else you can say map dot put pi and comma whatever you are storing, whether it is index or whether it is your true or false, right? And this is going to solve the problem. Overall time complexity here is order n. Okay, so guys, I will now end this session. Please do solve all the problems. Thank you guys.
Hello everyone. So today we have the topic as hashing, and I am Paridhi. I am a software developer at InterviewBit. So today I have selected two questions basically that I'm going to discuss here, and it's basically how important they are from interview point of view. So I have selected them, and so today we are going to do first question is anagram. So let's quickly dive into that. Okay, so today we are going to do our first question, and that problem is anagram. This is a very famous problem. This has been asked in Amazon, Microsoft, Goldman, as you guys can see. Very important from the interview point of view. Let's quickly see what it says. Okay, so given an array of strings, return all groups of strings that are anagrams. Okay, so represent a group by a list of integers representing the index in the original list. Fine, so we are given a group of anagrams, and basically we have to group the anagrams together. Okay, so let's see the example for clarification. First of all, what is an anagram? So it's a word, a phrase or name formed by rearranging the letters of another, such as spar is there, formed from rasp. Okay, so basically anagram is a word in which two strings can be said as anagrams if they have same characters, right? And the frequency of the characters is also same, but their order is different. Okay, so here as we can see that S is present in spar and S is also present in rasp, then P is present in spar and P is present in rasp. Likewise, A is present in spar and A is present in rasp, and R is present in spar and R is present in rasp. Fine. And these are the only characters. So these characters are basically jumbled, right? So these are known as anagrams. Now, given the example, we have cat, dog, god, and TCA. Fine. So these are the anagrams, and we have to group the anagrams together, right? Okay, fine. So we have cat, and I can see that 1 and 4 are anagram. That means cat and TC are anagrams. Okay, fine. They have same set of characters and frequency is also same. Makes sense. And dog is there and god is there. They both are anagrams. Fine, makes sense. So they have same basically characters and frequency is also same. Fine. Okay. So what do you think we can do? What is the first thing that comes to your mind? So what I can think of is that these two anagrams, as given in the example over here, the spar and rasp, right? They have same characters and also the frequency same. So maybe if I like sort them, they should give the same result, right? So if I sort spar, I should get the same result as if I sort rasp, right? Does that make sense? Exactly. So you guys have started to reply and you are on the right track that we can sort them. And after sorting, what is the thing that we are going to get? Let's see. So let me share my screen first of all, the notepad screen. So here we have, so in the example, we have, fine. So let me just copy it down. So we have cat, dog, and god and TCA. So I'm just copying it down on here. So, okay. So if I sort them, this will become ACT, right? And if I sort, so if I sort dog, I will get DGO, right? If I sort god, I will again get DGO. And if I sort TCA, I will, okay, so wait a minute, it just got auto corrected. DGA, sorry, DGO, and this will also be DGO, and this will be ACT, right? So that means here we know that CAT, as in the example, CAT and TCA are anagrams, and when we sort them out, then ACT and ACT we have got the same string, right? Okay, that means anagrams will have the same string, makes sense. And likewise in dog and god, DGO and DGO, they have the same string. Now, what can we do to group them up? So as someone of you has have said that we can hash them up correctly. That perfectly makes sense that basically here the sorted string can act as a, so here the sorted string can act as a the key, right? The key is the sorted string and the value are going to be the indices of the anagrams. Does that make sense? So here let's actually number them up. So we have 1, this is 1, this is 2, this is 3, this is 4, and we want the indices only, right? So indices are starting from 1 in this case. So basically the key here for CAT is going to be ACT, and here we are going to have the value will be a we can say a vector where we can store the indices of the anagrams. So ACT is a string and CAT is an anagram for that. So that means we can have in a vector we can have 1, and also this TCA is also, if we sort it up, we will get ACT, right? So that means the same string, and so the value is going to be 4 over here, right? So that means we have actually paired up the anagrams, the main task, right? Now the second string is DDO, right? And we can pair the strings that are forming the anagram. So that means 2 and 3. Does that make sense? So, right. We can do it in various ways. We can even hash them up in various ways. We can use frequency arrays as well. So you can do it in any way, right? So let's just code it up. So I think most of you are ready for this. Let's code it up. So here we have the screen and let's quickly code it out. Right, okay. So basically we will be keeping, first of all, we need a vector of vector for the answer thing, for storing the answer. Right, so vector of n. And also we need the map, sorry, we need a map, unordered map. So we'll basically do int, comma, okay, no, sorry, not int, we need string, right? We need string and we need a vector of int. Let's call it maybe group, right? These are the groups. And now the task is that we have to basically iterate through the vector of strings that is given to us. So let's iterate through it. So I will go from 0 to a dot size, right? And I plus plus. Now, okay. So we will take the first string. Let's take it in. Let's say we will actually have to generate the copy of the string because we have to sort them up, and also we need the original string, right? So therefore we are maintaining a copy. So let's take it in here and this will create a copy. Now let's sort the string. So let's sort the copy string. So cpy dot begin, then cpy dot end, right? So we have sorted, and now the task is that we can actually hash it. So that's what we are doing. So let's hash it. So the groups is the map that we have taken, and this is copy, right? So string is copy that we have sorted. Okay, so we have sorted it, and let me see if there are some comments. Okay, so now what shall I do? May I get it in the comments? What shall I write? So basically I can push, if that copy is present, I can push the index value, right? So after sorting this copy string, the string at AI, if after sorting we get a string which is there in the hash, right, which is present in the key, we can actually push I plus 1 to that. It's exactly what we have done in our notepad, right? So we will do it for all the strings, and finally after doing it, we actually have to iterate through the map. Does that make sense? That we have to iterate through the map. So let's do it. Groups is the map. Iterator, let's say, is IT. Now we will simply move through it. So that means IT equal to, that is groups dot begin. Then IT is not equal to groups dot end and IT plus plus, right? So so we have to just take the value, right? So here we have actually maintained an answer variable, answer array, and we have to basically push the entire vector that we have created in our answer, in the main answer, right? So basically we will be pushing back IT, that means the iterator dot second, and here we can simply return the answer array, right? So does this look fine? Please check, everyone. Are you guys coding with me? Yes. So basically for that, we are actually storing the indices only, right? So Nilesh, we are storing the indices only. We actually have taken the string in the copy string, that means the extra string. Then we have actually sorted this copy string, and here we need not maintain the main string. Basically we just want the index of that, right? So here we are pushing the index, right, just as we have seen in the notepad. So that's what we are doing. Let's try it now. Let's see if it passes. Oh, sorry. So this should be pushed back. Great. Let's see if it gets submitted. Cool. So we have done a good job, and we have scored 338 out of 350. Not bad. Okay, so have you guys got it? Have you guys got it? Are you guys with me? Is it clear? Shall we move to the next question, guys? Cool. Do submit it with me, right? Be here with me. Okay, so now let's do the next question of the day, and the next question is, so here I am taking the longest substring without repeating characters. So here is our question. Let's proceed to it. This question has been asked in Amazon, and not only Amazon, I have heard previously, as in recently, that it has been asked in various other companies as well. Can't remember the name right now, but yes, this is a very important question. So let's get to it. Okay, so Ashish says he has a question. In interview, are we allowed to use inbuilt function? Okay, so basically, it's like when you are asked to implement something, which is, let's say you are asked to implement a substring function. In that case, you cannot, use it. Or let's say you are asked to sort the array. So the trivial question is that, so the main question here is that you have asked to sort it. So how can you use a given the inbuilt function, right? In that case, you have to actually perform the sorting with the various algorithms you have. You can't use inbuilt function in that case, right? So here the question is different. You can use the inbuilt function in this case if it's not mentioned. If it's mentioned that you cannot use, then you cannot use, right? So it actually depends. You can actually ask your interviewer about it, that if you can use it or not. Make sense? Cool. Okay, great. So guys, let's move on to the next question. And the next question is longest substring without repeat. Okay. So let's see. So the question says that given a string, find the length of the longest substring without repeating characters. Okay. So here we are given a string. This is the string, let's say, and here it says that ABC is the longest string and the length is 3. That means ABC is the longest such substring in which there are no repeating characters. As you can see that, okay, ABC has unique characters. Okay, so basically we want a substring out of a long string which has only the unique characters, right? Which doesn't have a repeating character basically. In the second example, as you see that we have so many B's over here. And that means here the substring is just a B. That means of length 1 that has a unique character. If we try to extend this up, that means if we try to make the length 2, then definitely we will get BB, and length of 2 doesn't have unique characters. Does the question make sense to everyone? Okay. Could you elaborate more? That what would you do? Guys, please at least come up with the brute force approach. I would like to discuss it with you all, that what do you have in your minds? Can you guys think of the brute force approach for this question? Is the question clear to you all? Okay. So guys, please think on this question, okay? And then in a minute, we are going to proceed with the solution. Okay. So Garima says that please explain the question again. Sure, Garima? So here it says that you are given a string. Okay, you are given a string and you have to find the length of the longest substring without repeating characters. Now, first of all, do you guys understand what a substring is? So a substring is that when you take, so here if I say that this is a string, right? So what are the substrings of this string? So let me actually show you my screen. Cool. So here is my notepad screen, and let's remove this. So here we are discussing the longest substring without repeating characters. Okay, so let's say I have a string A, B, C, D, and or B, C. Okay, A, B, C, B, D. Now, first of all, what are the substrings of this string? So A is a substring, then AB is a substring, then ABC is a substring, ABC B is a substring, then ABC B is a substring. Okay, then starting from B, we have just B, then BC, then BCB, then we have BCBB, right? Then starting from C, we have C, then CB, then CB, C, B, D. And starting from B, we have just B, then BD. And then starting from D, we just have D. Does that make sense that these are the substrings of this string, the consecutive characters? Garima, is the question, so the question says that once. So basically you have to find the longest length of the substring that has unique characters. Here such a longest length is just ABC, because if we consider any length which is beyond 3, then that has a repeating character. So if we have let's say ABCB, right? So in this case also we have 2 repeating characters, as in one repeating character, that is B, right? So B occurs 2 times, which we don't want. So the question says that you have to find the longest substring without repeating characters. Am I clear with the question, guys? Am I clear with the question? Okay, great. Okay, so let me clear this up, right? Okay, so let me actually build your solution, then you will be more clear. Okay, so the brute force approach that comes to my mind is that we can generate all the substrings, right? We can generate all these substrings, and we can check if these substring consists of unique characters or not, right? So how to check if a substring consists of unique characters or not? So basically for that purpose, we can maintain a hash map. What's it? So we can maintain a hash map that will tell us that if some character is already present in our string or not. Does that make sense? That we can use a hash map because it tells us in just order of one time that okay, if some character exists or not, already exists or not, right? So this is the brute force approach. So does anyone know that how many total substrings we can create out of a string? How many total substrings are there? Okay, so total substrings are n into n, wait a minute, n into n plus 1 by 2. Okay, these are the total number of substrings that we can create, and where n is the number of characters in the string. Okay, now so once we generate all the substrings, and then if we check with the help of a hash map that if that particular substring has unique characters or not, then the time complexity for first of all for generating the substring is going to be order of n square. Okay, because total we have n into n plus 1 by 2 number of substring, therefore the time complexity of generating these many substrings is order of n square. Now we also have to check it with the help of a map if it consists of unique characters or not. So for that it's again going to take order of n, because why? Because the for maintaining the hash map it's going to take again order of n. So the total number of time complexity, the total time complexity is going to be order of n cube. Does that make sense to everyone? Cool. So the time complexity is going to be n cube, but it can be further optimized if while going through our second loop, we can actually check on that pace only if we are getting the unique characters or not. So what I'm saying is that while maintaining the second for loop, in the second for loop itself, we can check that substring from I till j has unique characters or not. And this we can do in our for loop only, the checking part. We don't have to do it separately for checking the unique string. Okay, so then the time complexity will reduce to order of n square, right? Because here we will be doing it in our second for loop only. We will be checking it in the second for loop only. Does that make sense, guys? Is it clear now that why n square? So n square is because while generating a string, let's say I am at A, so the string is, wait a minute, let's say the string is A, B, C, D, D, right? This is our string. Now I'll keep my I pointer here, and initially the J pointer will also be here. Okay. Now we will also maintain a map side by side, and we will put the character in the map that if so for checking if it's unique or not. Right now in our map A is not there, right? So we will put that okay, A is not there, that means A is unique. Let's put it in our map. So first we will check that if some character exists in the map or not. If it doesn't exist, that means that character is unique. Once we get to know if that character is unique, then we can add that character in the map. Okay. So okay, now we have done it. So we have checked for string A. Now we will move. So now we have AB. So we have in the map, we just have A till now, right? Now we will check that if the character at B is in our map or not. If it's not present, that means it's a unique, right? That means it's unique. But once we have checked that if it's unique, we will add it to our map because we have already taken it. So are you guys able to relate that how in the second loop only, that is while moving our J, we are able to check in the map. That's why the complexity is order of n square. Okay. Do try to dry run it on your own, right? And then I am sure that you are going to get it. And if you are still confused, then you should definitely try to code that up. Now I would try to, so here we are now. So the time complexity of the brute force solution is order of n square, right? Or I would say a little optimized solution is order of n square. But here we are generating all the substrings. Do we really need to generate all the substrings? So let me make my point clear from here. So we have A, then AB, then ABC, ABCB, ABCBD, right? So here we are actually generating all the substrings. Here I am trying to make my point here that we actually don't need it. So I can figure it out. Let's see if you are able to. This is our main substring basically, and here we have all the substrings. Okay. So if you see here in the third also we have to maintain the length as well, right? We have to return the length of the longest string. So when we had 1, the length is equal to 1, right? When we had AB has unique characters, length become 2, right? Then we have ABC, then length become 3, right? Because ABC has unique characters as well. Makes sense, right? Then we have ABCB. That means it doesn't have unique characters. Length is still 3, right? Then again ABCBD is there and length is equal to 3 again because it doesn't have unique characters, right? So that's how we will keep on going on, and the length will remain 3 entirely. Now the point that I'm trying to make over here is that if you carefully look, then here we have ABC, right? We have ABC, and once we got this fourth B, we come to know that okay, this string can have a length of 3. Then as soon as we are moving to B for length of 4, for checking for length of 4, the strings doesn't have unique characters. Now if you see, then in the second step, we are generating A, B, C, B, D. Do we really need to do that, guys? Do we really need to check for A, B, C, B, D once we have checked for this? No, right? Why? Because here we have already checked that A, B, C, B is non-unique. Then even if we add D, that doesn't make any sense because here till this point, this is not unique. So in any way, if we try to add more characters, that will still be non-unique, right? So that means this is redundant. So why are we doing something which is redundant, right? So we can ignore that. So this is the first point that I tried to make. Now we can actually, now the second point that here to be seen is that once we have got this B, right? Once we have got this B, so here from this A, I am sure that my substring having a unique characters starting from A more than of length 3 is not possible, right? Does that make sense? That starting from A, if I have already got the repeating character and if I had any more character, now it won't create a unique string at all because here I have a non-unique character. That means starting from A, I have just ABC as a length, right? Now here we have, the point here to be seen is that even from B, if I start, I can get at most 2, I can get the length of 2, right? Where the string length is 2 of the unique characters, right? So that means from A, I can get the maximum length of 3. From B, I can get the maximum length of 2. But starting from C, starting from C, there is a chance that I get a length of unique characters, a substring of length, a substring of unique characters which is more than 3. Does that make sense? So now here comes the point to do what I can feel is we can do sliding window, right? As suggested by Nilesh in the comments, we can do sliding window. So let's see how can we do that. So let me just remove all of this. We have A, B, C, B, D. Now in my sliding window, I will keep a window. I will start the window from A. Okay. In the sliding window, we have 2 pointers. Okay. One is left pointer and one is right pointer. So I'll keep both the left and right pointer at 0th position, which is A, right? Okay. So A is unique, and that we are going to see it from the, we are going to do it from the map, right? So we are also keeping a map. So let's keep a map. A has a, so we can maintain an index, okay? So we can maintain an index. Let's also put the indices 1, 2, 3, 4, right? We can put an index over here. That means A is at index 0 and A we have already taken. Now let's try to expand the window. Before that, we will also keep a length variable which will keep the track of length. Length right now is A. Now we will move our R. So now the window has become from A to B. B is also not present in the map. Let's make the length 2, right? And add B to the map. Index of B is 1, right? Now let's increase R. So R is at C. So C is not there in our map. Let's include C in the map with the index, right? Also the length has become 3. Now let's move R. Okay, as soon as we move R, we saw that now we don't have any unique characters. So that means length will remain same. And now we will move our left pointer so that we can actually remove the previous occurrence of B, right? We will move our L till the point the B, the occurrence of B becomes 1 only, right? Does that make sense? That we will move it till the point the occurrence of 1 becomes 1. Okay, so let's move our L now. So as I move my L moves to B, right? L moves to B and R is still at 3. Okay, L is at 1 and R is at 3. Now we will, so A has gone out of window. That means L to R is the window. A has gone out of the window. So remove A from map. Okay, we will be removing A from map. Now we will check that still is the element, is the character at R still present in the map? Well, yes, it's still present. It means that it's still the part of the window. And in that case, we will again move our L. So let's move the L and L comes over here and B will remain at 3. Now B will be gone. That means here. So we actually remove this B from the window. Let's remove it from here. Now we will check that, okay, is B present now? Is B present in the map? Well, yes, it's not present now, right? It's not present. That means we can include this B in our map now. We can include this B with its current index, which is 3. Okay, which is 3. Now we can start moving our R again. So let's move our R. Now R comes to 4 and B is not present in the map. Length will remain 3 only because L to R, the length is still 3. Let's include D in the map. Now D becomes, so D is at position 4. Okay, and now let's move our R, and now R, there are no more characters, therefore we will simply stop, and whatever will be the length, we will simply return it. So this is how we can process it using sliding window. The time complexity of this approach is going to be just order of n, because we are iterating to each character not more than twice, because one with the left pointer and one with the right pointer, right? So as we are moving our left pointer and as we are moving our right pointer, so we are not coming to any character more than twice. Therefore, the time complexity is going to be 2 into n, which is nothing but order of n, right? We don't consider constants. And the space complexity is order of n again, because here we are using a hash map. Does that make sense? How we have beautifully come across a good, just by building some, observations, we have come to this solution. Does that make sense, guys? Shall we code it? Great. Cool. So let's code it up. Here we are. Now let's quickly do this. Okay. So first of all, I have to maintain an answer which is, let's say, at present int min, right? We want the maximum value, so we will initialize it to int min, or we can initialize it to 0 as well. It doesn't matter, right? Okay, so we can, the left pointer we will keep, which is initialized to 0, and also we will keep a right pointer, right, which is initialized to 0. And also we will keep a length, right, which is again 0. Now we will be iterating through our string. We will be iterating it with the help of right pointer. Right pointer, so let's keep the right pointer in the loop. So let's initialize the right pointer here only to make it more readable for you guys. So right is less than a dot length, then right plus plus. Okay, and we will, okay, so we have to take a map as well, right? So we will take a map, and that will be map will be of char comma int, because we will be maintaining the index. Make sense? We will be maintaining the index with each character. Now, okay, so if the character, at right is present in the, so it's not present in the map, right? So how we will check that? M dot find, right? M dot find is equal to m dot end. That's how we will be checking that if character is not present in the map. So if it's not present, we will simply do what? We will simply do m at a of right is equal to I. Sorry, right. Here we are actually assigning. So here we are doing nothing, but let's say we have A, B, C, D, D, right? So here we are doing nothing. In the map, we will be storing A mapped to 0. That means the index of A. Okay, that's how we will be storing it. Now, after storing it like this, what to do? Let's increment the length, right? Because we have actually found a new character we have included in our map. Let's increment the length. So after incrementing the length, we are done till this point. Now, what if the character is already present, right? So for that, we will use a else block, and in the else block, we will be actually moving a left pointer. We will be moving the left pointer till the point. So let me just write it, and then I'll make it clear maybe. Okay, so let me make it clear first. So here, what my point is that I have, let's say, L here and my R is here. Okay, and now A, so let me actually change the map. The map will be A, for A it's 0, for B it's 1, for C it's 2, and again B comes, right? So I will be moving my L till this point. That means the index of previous B plus 1, because we actually have to remove the first occurrence of B. So we will be moving our L till the index of this B, right, plus 1. So here let me write it. So while left is less than equal to m at A at right, we will be moving our left pointer, and what more do we have to do? Moving our left pointer, and we have to erase the occurrence of whatever is left behind, right? So that means m dot erase A at right. Okay, and also we have to do one more thing. So we have to reset the length. Okay, we will be resetting the length. We have maintained a global variable. That means this is, let's say this is the answer, but as our left and right shifts to this place, that means L comes over here and R comes over here, again the length, so we will also maintain a variable length. So now it will become 2. Okay, it will become 2. That means the current window size, and that is given by what? That is given by right minus left plus 1. Okay, and also we will be updating our answer to max of answer comma length, and finally we will return the answer. Let's see if it works. Are we missing on something? Does this look fine? Okay, so we actually have to do one more thing over here, and that thing is that we actually have to write the new index, right? So here, let's say A was gone, and now the new index of B is equal to 3, right? So that means it's equal to nothing but M at A at right is equal to right, and that's all. Let's test it. I'm really sorry I didn't see that. Let me share it again. Don't worry, I will explain the code. Okay, so you guys want me to just explain it. Cool. It's good that you have understood the logic, and I'm sure that you will all will be able to code it. Let's see. So here I am maintaining the answer, which is initialized to int min. Okay. Then we have a left, that is the left window, and this length is basically the to keep track of the length we have, right? This length is actually from left to right. Okay. Now we also have a map that is from map to character to int, that character map to the index. Okay. Now we with the help of this right pointer, we will actually be iterating through our string. Okay. And while iterating through the string, we will check that if the character is already present or not. So here we are actually checking if the character is not present. Okay. So the character is not present. So we will actually put the character with the index in the map. Okay. And also we will increment the length. So this is when character is not present. But if character is present, in that case, we will be moving the left pointer. Okay. We will be moving the left pointer till the point. So actually I have shown it to you in the editor. I think you have seen it there, right? You have seen it there. So we are actually moving our left pointer till the first occurrence of the repeating character in is gone. Okay, it's gone. So then we will do left plus plus, and we will erase the character that we have left behind. Okay, and then we will do it till the character at right pointer which we found repeating in the current window. So till the repeating character is no more repeating, we will then add the new index of that character in our map. Make sense? We will add the new index of that character in the map. Does that make sense? So okay, let me complete it and then I'll get back to your questions. Okay, so here we have the character with its new index, and also now we will reset the length to the length of the current window, right? To the length of the current window, and then we will update our answer. We will keep on doing this, right? So length will have the size of the current window, and this answer is the global answer that we have. So whichever is maximum, that will come in our answer, and we will return the answer. Okay, we will return the answer. Let me try to submit it. Let's see if it gets submitted. Okay, it failed. Where did it fail? Okay, sorry. We need to erase the left, not right. Okay, and let's see it now. It's still not passing. Let's see if this works. Yes, it worked. So first we have to basically erase, and then we have to do left plus plus, right? Okay, so there was just a little bug. Okay, so is everyone fine with this thing? Okay, so basically you should use set when you just have to keep track of that particular character only, or I would say that particular data only, as in when you don't have to map anything, right? So here we see that we actually map the character to the index, right? So that's why we used a map, because keeping the index also was necessary to move our left pointer, and therefore we preferred map over set, right? Does that make sense? Execute now that why do we need to keep map over here? Why not set? We actually made a streak today, right? So Pavandeep, I would say that yes, maths is important. But competitive programming is more than maths Olympiad, right? So it's more than maths Olympiad, that I would say. But yes, it will definitely help you, right? Because in competitive programming, we can see maths a lot. So yes, that's a good question, Pavandeep, that you brought up. So this was it from my side.